Hallo.
Hi, Lorenzo. Some people are going into the old Zoom link, so I'm just sending out an email on that.
Okay.
Hi, Lorenzo. Some people are going into the old Zoom link, so I'm just sending out an email. It's always funny when you have the streaming turned on because it's Hi, TJ.
Morning, James.
Hello, Bobby. Thank you for joining us. Could you possibly do me a favor and go into the hackathon document and pull out a list of the names for the breakout rooms and just put that in the chat back to me so I can create them? One small problem with the Zoom is that they don't let you rename breakout rooms once they're open. So you have to close them before you can change the name.
Sure. Let me see if I can find this list real quick.
Some people gave us names. We can ask for them again in a little bit, but just wanted to make sure that people had names. They had the names. 3 people made suggestions, but I think you could probably create a rough name. I mean, people, for example, somebody did muscle regeneration. So. But the other ones will probably have to. And then maybe if you could put the name of the person as well who's listed as the lead. Something like this.
So we wanted to create a room for every person or?
Each project.
Okay.
Some of them may not get used, and we should probably have breakout rooms for you and the I'm not sure if can you edit the breakout rooms? If you click on breakout, I think you may only the host. So if you like, I can make you host and you could do that while I talk. How about that?
That's fine.
Okay. Give me one more second. We'll get started in just a second. Sorry, let me do that. Let me switch the ownership meeting to. Hello, there was a question. Paolo, when registering steppables, can I register as many steppables as I please from different source codes? Does the order matter? You could register as many steppables as you like. So in principle, you could build modules that have different, that are steppables that operate independently of each other. There was a recent paper by Reinhard Labenbacher in Florida talking about trying to build a modeling framework around that kind of idea. Ideally, you want to make sure that the steppables are able to operate independently. When we first start out, we often write everything in one big steppable, and that's much easier and simpler when you're starting because you don't have to worry about where data are stored. But if you want to build modular models that are extensible, it's better to modularize the steppables. And TJ has done a lot of work on how to do that. And he'll talk probably maybe a little bit about that later today. We certainly often will do a steppable that does, for example, you can have a cell growth steppable, a cell mitosis steppable. You could have a cell death steppable, or you could have a steppable that operates only on particular classes of cells. All of those are possible. When you do that, the kinds of things that Jim Sluka was talking about at the very end, it was a little bit rushed, about putting your parameters in separate files become quite important because you need to know where the parameterizations for your data, for your models are. So, but TJ is an expert on that kind of modularization. But absolutely, you can have as many steppables as you like. The order of execution actually is specified in that main Python script that we don't usually look at. It tells you the order of execution, and ideally, you should design your steppables to try to make sure that you don't have problems if the order of execution is reversed. If your time steps are small enough, that should be all right. TJ is putting up some nice comments on that. So let me give people just another minute. I see people joining. Great. Okay. Thank you, Paul. TJ. There's building models of this kind is complicated both biologically and mathematically and computationally. And a week seems like a long time. Maybe spending 30 hours together is a lot. But in fact, when you start teaching it, you realize we have to leave a lot out because there are all sorts of important questions like the ones that you ask. And what we really need to do, of course, is make some more videos about that. And when we see these kinds of questions, we can try to build some videos explaining. All right. Are there any other quick questions before we do our orientation here this morning? I'm glad to see so many people here this morning. TJ, are you okay on the breakout room situation?
Yeah, I'm setting them up now. For groups that have in our information, some groups have multiple names listed, and I am just naming the corresponding breakout room by whoever happens to be the first name listed in our information.
Okay, that's fine. I would suggest putting some descriptive name at the beginning of the breakout room name, and then a contact person's like vascular development Matamanchi, and that should disambiguate it. But I wanted to make sure that if people are looking for projects to join, they have a descriptive name so they can jump in and take a look.
Okay.
Does that make sense?
Yes.
Now we should probably have 1 or 2 breakout rooms for named for you or for other organizers to have sort of discussions outside of the breakout. I mean, outside of the main breakout. Okay. Well, thank you everybody for coming back. Appreciate seeing so many people here this morning. We hope that this is productive. I know people are probably pretty tired by this point in the week after 6 days of classes. We're going to be live streaming parts of this meeting. I realize that some people may have material that is proprietary that they don't want to share. So I would ask you to not present that material in the main session, which will be streamed. If you ask us to stop recording, we can do that, but it's harder to not stream because it's rather difficult to stop the live stream and then restart it. Tomorrow, if there are a significant number of people who do not want their final reports shared, then we will not share those. Although I would encourage you to try to make the material that you present shareable, because I think it will help everybody out in terms of recruiting and in terms of model development. So today we're starting now. We're going to have a very, very brief orientation. I'm going to, can I do it now? Let's see. Can I do polls? TJ, could you make me co-host, please? Oh, Priyam, thank you for joining us. Appreciate it.
Hi.
So Priyam is an expert in epithelial modeling. She's worked on rosette formation, collective migration, a whole variety of things. She's now a postdoc at Duke and is going to join us for a couple of hours and help out. She can't be here for the whole weekend, so if you have specific questions about those kinds of things, I encourage you to ask her as quickly as possible. I'm going to lead off today with a simple poll, which is, do you already have a project or are you looking for a project? If you're still looking for a project, that would be very helpful to know. So it looks like most people already have a project, are committed. So please let us know. If there are only 1 or 2 people who are looking for projects, I guess the question then is it, well, let's go ahead as is, and we'll see how it works out. I'm not going to change my agenda. Okay, so the schedule today is as follows. I had originally blocked out an hour for people discussing your ideas. But if we don't have too many people looking for projects, we can do that really quite quickly. In other words, you could just come in, state in a word or two what your project is and what the name of your group is. And then people who are looking for projects should go and talk to those groups. And you'll have the ability, you should have the ability once the breakout rooms are created to join a breakout room freely, to leave a breakout room freely. I will stay in the main room because the person running the meeting has to do that. But everybody can move around freely. It's not the Zoom breakout rooms aren't the most convenient way to do that, but it's probably most familiar to people. So that's what we're going to do. Once we have finished the discussion of lightning review of what the projects are, we're going to create the breakout rooms, go into them. People will work in their teams. The instructors will be able to move around. Remember that one issue with the breakout rooms is that when you're in a breakout room, communication up and down is not trivial. So please use the Slack and the other communication channels for doing that. If you need to, you could always come up into the main meeting room and ask for help or send a message another way. Around 1 o'clock, we will have a quick check-in session in the main session to make sure that everybody is okay. If a team decides that it doesn't want to continue, it wants to join another team. If people want to move around, that's fine. If you don't want to come out and have a check-in, that's all right too. Then we'll have a work session from 1:30 to 5 in the evening. And in the afternoon, we're going to have a series in the main room of short topics that we didn't get to cover during the main meeting. There are no guarantees on these. It's possible that the times will change slightly. We'll broadcast those to the main rooms when they're going to start. I'd encourage people not to take too much time away from the hackathon work. But if you want to learn about a particular topic, we'll do that in the main room. TJ will talk about that Python API for CC3D and modularization, which we had a question about just a few minutes ago. Giuliano is going to show people how to convert these applications to NanoHub applications. So if you wanted to have a project that was uploaded to NanoHub and run as a freestanding project, the way that COVID simulation that we showed earlier in the week worked, you can learn how to do that. Giulio said that he would talk about the subcellular chemical modeling of planar polarity. There were quite a few people who were interested in modeling chemical migration within cells. And Giulio could talk a little bit about that. And Gilberto has volunteered to talk about his 3D cell crawling demo, which is a very beautiful simulation, a little complicated for a class demonstration, but very interesting. He can share that code as well. And then at 5 p.m., we will have reports, if possible, from people. I would like to know everybody to come up and share their progress and frustrations. I remind you that we had some guidance documents, one pager on thinking about modeling strategies, a slightly longer document on how to think about developing models, a bit more detail, and then there was a worksheet for doing that. I apologize that those documents aren't in the most polished form, but those are available. And if people would like to make suggestions for how to improve them, that would be much appreciated as well. So those are the main things I wanted to talk about. We have the usual people involved. Priyam is helping out today as well. So we thank everybody who's helping out. And today, I wanted to say a few words. This is a slide that Bobby put together last year. One of the things that's hardest, I think, in all of modeling, in some years, we've taken a module to talk about principles of modeling, is actually trying to define the biology. What is it that you're trying to do? What are the inputs for your model? What are the outputs, quantitative outputs for your model? What are the biological components you're going to model? What are your hypotheses about how they work, what their behaviors are, and what their interactions are? In our experience, actually defining the biological questions and the outputs and the structure of the model is the hardest. Once you've done it, actually turning it into code isn't that hard. It's not easy, but it's actually not as hard as the biology. So my slogan that biology is the hard part, it may not be meaningful when it's packed that densely, but I'm trying to explain that. We hope this exercise today helps people improve their familiarity with CC3D. We definitely hope that people are able to learn from each other, which is why we have these check-ins and reports. If one group is having an issue with something, please use the Slack to communicate on that. If Giuliano and TJ can post the Slack information in the chat, that would be very, very helpful. I think there's a lot of overlap between many of the projects that have been discussed. There was a good question about importing experimental data. That's something that CompuCell could use some improvement on. We'd like to talk to you about that. And we hope that at least by the end of the today and tomorrow, you have something that's useful for you. Last year, we had a 3-day hackathon, which is why this slide says 3 days. This year, we realized that that meant we didn't have enough time for the main lectures of the course. And so we've gone to a 2-day format. That means that it's going to be a little tight to get things done. And I don't want to take more of your time than necessary. TJ, yes. I would just say for informative room titles, use a few words like glassy epithelia or a lateral line, something short. That's it's tricky. TJ is making a comment that the breakout room names are going to be pretty short, and so we have to be compact on that. If you have a suggestion for breakout room name for your group, please put that into that shared Google Doc. Today, if you don't have a couple of people still who haven't found a team, please do try to recruit members. Bobby is really good at helping people define models, and I hope he'll circulate through all the teams and work with them. He's expert in this. I hope by the end of the day, most people have the basic components of their model done. I know some groups have already made a lot of progress. With that, I'll come back to the list of projects that we had in our document so far. I see the numbering wasn't quite complete, and I'll call on people just to say a word or two about their project if they would. We don't need some slides because I think, again, most people already know what team they want to be in. But if there are a couple of people who are still looking to join teams. And so if you could give us, just run down the list, and if you can tell us in a few words what your project is about. And if you're looking for an extra team member or two, that would be great. And do please, after you've done that, send us a suggested very short name for your team. I see one or two of these are already here, so that we can put those in the breakout room. Okay. So, Javid, would you like to say a word if you're here?
Hello, everyone. About the project, you mean, Professor?
Yes, just a word or two in case somebody would like to check out what your project is
Yeah,
about.
it is about the endocellular to mesenchymal transformation, and my team members would be Naushin Fatima and me and Tony West. So yeah, that's it.
Okay. That's fine. That's fine. So if somebody finds that interesting, please go talk to them. The next one is our lateral line team, which I know has been working hard. And and you are here now. They asked me if I could start the meeting early because they wanted to get started early. I know you're very well along. So can you just say a word or two about your project?
Yeah, so we are a group of 3 people right now who are working on this project. The lateral line primordium is a group of about 100 cells that migrates under the skin along a very well-defined path. And as it does so, the cells change their organization to form these little rosettes, which are going to get periodically deposited by the migrating primordium to initiate the formation of a part of the nervous system of the zebrafish, which is called the lateral line. And in the past, we've worked on modeling how signaling specifies where these little rosettes form. But in our project this time, we are focusing on trying to understand how mechanics, primarily adhesion and spring-like interactions between the cells, contribute to the organization of cells, and how that organization can be influenced by the manner in which the cells are pulled apart by migratory forces. So we had already, I had in the initial talked about how we're going to try to recapitulate what we had done in a net logo model. Since listening to all the different tutorials we had, we've actually added a small additional project where we are trying to model the behavior of the cells by using these hybrid cells where there is a basal, lateral, and apical part, because the primordium actually has two types of cells. There are polarized cells that form these rosettes, and there are also very flat cells that form a sheath around the primordium, which I didn't get into in detail. And they work together to allow this whole system to migrate under the skin. So we have a second project that we've articulated, where we will use these hybrid cells to model both the mesenchymal style cells and the more epithelialized cells. So that's what we're doing.
Okay, lovely. I don't think David is online. If you're here, please speak up. If not, that's fine. The next is it Megan? Do you want to say a word or two?
Yeah, so my team and I are working on an agent-based model of muscle regeneration, specifically looking at an acute injury. We're looking at how different fields like cytokines and growth factors impact the inflammatory response, and also potentially incorporating some hormones such as estrogen to see how that impacts muscle regeneration. So we currently have a team of 4. If anyone is interested in joining, please reach out to me because we could always use another hand on our team. Yeah.
Great. I don't see, let's see. The next one is Farnoosh.
Yes, thank you. I'm here. Yeah, and the idea of our project is to model immune response following immunogenic cell death in pancreatic ductal adenocarcinoma, as it is a very, very complex phenomenon. For example, PDAC or pancreatic ductal adenocarcinoma has one of the most complex tumor microenvironment. So we decided that for this 2 days hackathon, we just try to develop a very simplified, basic, generic model for immune response in tumor microenvironment. And if you have time, we probably try to add other elements to that. But it is now a very simple, generic model. Our team, in fact, Paulo and Matesh, Tahrim, and Lucas asked me to join the group, but unfortunately, Tahrim and Lucas are not online now. So at least now we are 3. Yeah, that's it.
Great, wonderful. Well, I hope people will. I hope you could communicate and work with them. You certainly don't have to work only during the time that we're scheduled to meet. I hope you're able to make that work. That's a great project. The next is Hamed online. No, okay. Yajun. Not now. So Arana, did you join another group, or do you have a second project?
Hi, no, so hi, can you hear me?
Yes, go ahead.
Great. Yeah, no, so the project I was proposing was about apoptosis and Wnt signaling in the zebrafish embryo, early zebrafish embryo during epiboly. So I've agreed to help Megan during the hackathon, but I will definitely be running this project in the near future. And I've already been in touch with a few people who want to be involved with that. Anyone else who does want to be involved is welcome to. I'm also going to be trying to do something in CC3D with fungus in the near future. So anyone who's interested in that can also get in touch.
Great. I hope we can stay in touch too, because early development in zebrafish embryo is something my group personally is very interested in as well. So we'd love to talk more about that.
Absolutely. I
Okay.
enjoyed the tutorial on convergent extension. It will definitely be very useful. So thank you.
Is Janos here?
Yes, I am here. Welcome everyone. Currently, I'm working with Conor Johnson on the yeast colony formation. It's about, you can find the slides at the slide deck of the hackathon. And we try to make some simplified model of a complex, realistic yeast colony growing when the cells are growth by some nutrient and they not form just a blob, but they form some more complex structures. So yesterday we had some discussion, and probably we should start from the nutrient limited growth model and this model with the links from yesterday. So we will see in more details these two models and try to find out what we need from this model, what we should modify, how could we combine them.
Great. So let me give your...
Yes, the name of yeast colony would be great for the breakout room. Thank you.
Okay. Iman, are you there?
Yeah, hello everyone.
Okay.
Yeah, my project is about modeling the degeneration in articular cartilage matrix, and what I will develop here would serve as an input to a bigger model that shows the difference in light propagation in a healthy and also in a pathological tissue.
Again, I think cartilage is a great subject of investigation. Quite a few years ago, we had a team that got a long way with the cartilage degeneration model. It's really quite a long time ago. It was back in, we did a version of this workshop in Leiden in the Netherlands. And I don't know what happened to that. I think probably people got distracted, so it wasn't finished. But I know it's a good topic and would be interesting to do. I think Maria decided not to do this. Is that right? So we'll take that one out. Okay, is Marco here?
Yes. Can I share my screen just to show show you some things that because I already started shipping something, but I cannot.
Sorry, actually, TJ, you own the meeting, so you have to do the reshare. I think.
Your host now, James.
Or you put me back.
Yeah, the breakout rooms are set up and information is in the chat.
Okay, so go ahead, please.
Okay. Am I sharing?
Yep, we can see your screen, yes.
Okay, so yeah, I started shipping something about my project of cancer cell invasion, and well, the model foresees two molecular entities, oxygen and extracellular matrix. The extracellular matrix is shaped like this, and there will be like a hole in the center of the simulation for the cells, and then once the cells will sense the extracellular matrix, they will start. They will trigger one of the nodes in the Boolean network. The Boolean network will be handled by MABOS. The MABOS model is ready, is here, and so basically I will link some of these output nodes to certain cell behavior. I'm still not sure if I will link to certain cell behavior or if I will create different cell types, and each cell types will have a very precise behavior. But this is something I will study today. And yes, basically each cell will be able to grow and divide, will be able to die. There are several death models, and then the cells will be able to attach to the extracellular matrix, degrade the extracellular matrix, and forming lamellipodia to escapes and degrades. And the normal state of the cell will be a quiescent state that will change according to the states of the Boolean network. And that's all.
Okay, great. Thank you. So let me come back. Let's see.
Yeah. Okay.
Hold on. That's good. So I see a number of people have joined us since we started. So okay. And the next one was Suvik. Are you there?
Yeah, hello. Can you hear me?
Yes, that's fine.
Hello, can you hear me? Yeah.
Yes.
So, yeah, so I'll be working independently. So, but anybody is welcome to my work. So, in this project, I'm going to study this collective motion of cells in a confluent monolayer in the context of active matter. And I would like to characterize the glassy dynamics in this type of system, since experiments has the evidence of having the glassiness in this type of confluent cellular monolayer. And so in the context of so I will include the cell cycle events, and also I will include polarity, and I will try to see that this polarity and these cell cycle events like the cell death and cell division, how the rates and how the magnitude of the polarity magnitude of the polarity vector, and that affects the glassiness. Thank you.
Sounds great. Okay. So, and then the Lorenzo.
Hi all. So my project is about multi-scale simulation of endothelial cell monolayers. I have a preliminary project that is already ongoing, and there are some bits to put in place to make it all the way through the parameter scan, etc. So one thing I will try to do in these 2 days is to refine the initial part where cells start adapting and find their place for the initial disposition, which is now a little bit rough and slow. And then I will need some help to refine the implementation of my antimony model into CompuCell. And finally, I will try to generate an initial parameter scan for the simulation and see what data I can grab out of that. And then out of my, beside my project, I will probably help Jonas, which is following for his oropharyngeal squamous cell carcinoma thing.
Okay. And is it, so Jonas, did you have are you there, and did you want to say, okay, great, thank you.
Yeah, so for my project, we'll be trying to model the radiosensitivity of the oropharyngeal cancers. So looking at mitosis as well as the tumor infiltrating lymphocytes. So we have, so far we have the spatial maps of the cells from H&E biopsies, which I've been trying to import into CompuCell as a PIF, but I had a bit of issues getting multiple cell types, but I think so I'll just be trying to figure that out. And in my team, so Lorenzo will be helping us as well as Jordan and Roham. Yeah. And anyone who likes to join is welcome to as well.
Okay. So are there any other people who have ideas that we haven't had presented? Anybody? I think people are probably rearing to go. So we'll do that. I'm just trying.
Hello. Hello.
Yes. Hello.
Yeah.
Hello.
Hi, James. This is Vignesh.
Yes.
Yeah. So I only joined yesterday this workshop, so I didn't know about it. But I've been already working in CompuCell 3D. So can I share my project?
Sure. Please go ahead.
Sure. Hi everyone. So I'm working on wound healing. So what my project is about, like if you see in wound healing, scarring is one of the major problems. And what I plan to do with CC3D simulation is to, make different topography design, that is geometries, which will, play a role in contact guidance of the cells. And it will, to see how the cells are aligning. So in that way, we can see maybe the ECM alignment will be changing in case of wound healing, and this way we can prevent scarring. So my plan is to design different geometries in CC3 2D simulations and see how the cells are, alignment, the overall orientation of the cells doing wound healing. So we want to measure the coherencies and stuff like that. So plot some kind of vector field. So that is the idea. Thank you.
Great. So if you want to add that if you want to put that into the chat, I can add it to the slide and also to the discussion.
Yeah, that would be nice.
Okay, great. So,
thank you.
Wonderful. Okay. So sorry if you could mute if you're not. I'm going to mute everybody just for a second, and then we can. Okay, great. So I think that is everything I've created. Breakout rooms for the breakout rooms I've created are EMT, Javid, lateral line, Ajay, bronchial epithelium, David, muscle regeneration, Megan, immune response, Farnoosh, calcium waves, Hamed, GRN of neurons, Yajum, yeast colonies, Janosch, cartilage, Iman, breast cancer, Marco, glassy monolayers, Suvik, endothelial cells, Jonas, wound healing, Vignesh. I've created 2 rooms, one for TJ and one for Jim Sluka. And I've created a couple of open breakout rooms where if people want to go to meet to talk, they can. And you're welcome to move around between those. And those will just be called open discussion. And you can use those for anything you want. Is there anything else that we need to talk about before we create the breakout rooms and get started? I'll remind you just that for this afternoon, you don't by any means have to attend, but if you're interested in these topics in the main room, TJ will be talking about CC3D Python, calling CompuCell from other applications and modularization of CompuCell, which was asked about building CC3D, building NanoHub applications, Juliana will talk about later today. Subcellular chemical modeling of planet polarity, Julia will talk about, and 3D cell crawling demo, Gilberto, I think you're on. Now, it's possible that those will get canceled or rescheduled. And so what we'll do is just 5 minutes before the person is ready to start presenting those things, we will send a broadcast message to everybody. With that, I think I don't want to take up any more time. We've gotten through half an hour of your valuable time. So create the rooms and people should be able to move into the rooms and get started. And I'd ask our team to join rooms one at a time and try to help out. Good luck, everybody. Any questions before we get started? No? Okay. One question I have, TJ. What's the status? Do we have a push out of that fix for the Windows version of CompuCell?
Yeah, I'm told that an update has been posted on SourceForge, which is available on the CompuCell website, that has an updated distribution with all of the proper dependencies that we're missing for 4.2.5. So if you go to the CompuCell page, same place where you downloaded the Windows local installation package, you can follow that link again, download the updated version on SourceForge, and that will have everything. Sorry, 1 second. That'll have everything for doing ODE modeling in CompuCell, and that should also have the MABOS extension built in as well.
Okay, wonderful. So please, if you're running locally and you're on a Windows machine and you had trouble and you're going to be using the subcellular models, please download the patch, the new version of the installer and reinstall. And that should fix we hope that'll fix your problem. If it doesn't fix your problem, please let us know right away. I can't believe we actually have 39 people on this. This is wonderful. the two people who are looking for projects, I hope you had enough information that you can explore and find a project. And we will get started. If anyone has any trouble joining a room, please let me know. You should be able to join rooms freely.
Yeah, I have a little problem. Like I was supposed to work with David, but I didn't find him like since Thursday. So I'm happy to join other project.
Was there a project? There was a project on the which one was it?
Bronchial. Yeah.
Right. But I guess what I was going to say was there was this project on immune response that might be interesting to you.
Yeah.
Or you could join. Well, I don't know what I can't tell you what to do. You have to decide.
So I
what
actually
appeals to you.
have another problem I work on for a couple of times. So I used to work with Ramrevat on that project. So I can continue that one myself as well.
Okay. So do you want to have a breakout room for that, or did you?
Yeah, sure.
What shall I call it?
You can call it homeostatic decision.
Sorry. I'm sorry. Say that. What? Say that again.
It homeostatic decision.
Okay. Actually, the only problem is that I can't rename the breakout room right at the moment. So I can give you a description.
I'll take any of them. That's fine.
But you decide when we come in at the noon check-in.
Yeah.
When I close the breakout room, I can create a new one. If you want to use the open discussion, I can assign you to. You can use open discussion, and I can let people know that that's available.
Okay. That sounds good.
Okay. But you could also look around and visit some of the other rooms and see if something is interesting to you too.
Yeah.
Can you move me to the list of those breakup rooms so I can click on them and join?
If you go, so you should be able to do that without.
I know,
so you
but
should be
I'm a little bit slow. You said it's on the Slack, but right now I don't have the Slack, so I don't see the Slack.
So if you're in Zoom,
I am in Zoom with you.
Right. So if you if you go to the bottom, you should have in the control of the Zoom, you should have an option somewhere called breakout rooms.
Oh yeah, I'm right. You're right about that.
And now if you scroll through, the names may not be completely.
No, that's okay. Breakup rooms, I found. Okay, thank you so much.
Okay, and some of them only have one person.
A slow learner.
No worries. It takes some time to get used to these. Okay.
Right. Okay, fantastic. Thank you.
Thank you.
So here we are.
Ah, so David. So David, are you there?
Yes, sir. Can you hear me?
Yes.
Yes.
So Tyrone was just here looking for you.
Oh. I switched Sorry, I switched what's it called? Time zones. So I kind of like lost track of the time zone. So, but yeah, I'm here now.
Okay, so are you going to be working on your project?
Yes, sir.
Okay, so why don't so let me mute and
Sure.
I'm sorry, I'm going to mute and then can you unmute, please?
Okay.
So David, if you could, so Tyrone, did you see that David is here now?
Yeah. Perfect.
Okay, so David, I've created a breakout room for you called bronchial epithelium. So you should be able to join that with Tyrone. And then I hope that works for you. Okay.
Hi, James. Would
Yes.
you prefer that I get back in touch with you a bit later about this initialization problem, or are you available just now?
Hold on 1 second.
It's not a problem if you're busy just now.
No, just let me make sure everybody is assigned and just give me 1 second. So Alexa.
Hi, I'm actually with Aaron.
She's on the same project with me. Yeah.
Okay, great. Okay. So I think maybe we need TJ on this one. So
Okay.
TJ, if you could stay in and we can have this conversation here for a bit. Pedro, Gilberto, and Jim, let me make sure that I have you just let me make sure that the permissions are all right. Pedro.
Okay.
Okay. So could I ask you, Jim, Gilberto, and Pedro, can you please look through the breakout room, see who is either alone or doesn't have somebody from the assistance team and join them and help them out?
I'm already helping Jonas with a problem with the beef initializer, so I'll be hanging out here for a while.
Okay, that's fine. Whatever works. You can also use the open discussion rooms that I've created as well. Jim, I don't know what can you help join a group and help out?
Yeah, I can wander around. Do you want me to start off with whoever's alone?
Yeah, I think that would be good. Marco looks like he's on his own.
Yes, I will do the same.
Thank you, Gilberto. And you're scheduled, Gilberto, you're scheduled to present your cell crawling model this afternoon.
Okay, I saw already.
Okay, great. Thank you, everybody. Gilberto, if you have any trouble moving around, let me know. I can move.
Okay.
Okay, so why don't I unscreen share and then we can go ahead and tell us what the issues are, Aaron, and then we'll see what we can do to help out. TJ, if you're there, we should see what the issues are.
Yes, I'm here.
Yeah, so it's kind of an interesting problem. We have a CSV file, and Lexi, feel free to correct me if I go wrong. Megan and Tian are also on this project.
Okay, so. Great. Okay.
So yeah, we have a CSV file where it's essentially a two-dimensional grid, obviously, and where we have ones, we want to put muscle fiber, I think, and where we have twos, we want to put ECM. Is that the right way around?
Yeah.
And we were just wondering if there's a way in CompuCell to get the cells to arrange themselves into these spatial regions without us having to do it manually. So I know that Lexi tried doing it manually, sort of pixel by pixel, and it crashed after, running through the file for so long. So we were wondering if there's a way that we can even do it outside Multicell and import it. We saw that there was a PIFF import, but I don't know how that works either. So yeah, we're open to suggestion.
So PIF is a terrible format. It's one of these things. There are many things that are legacies. You don't think you're going to compare. You throw them together as temporary things, and they become permanent.
Yeah.
So PIF is simply you draw squares or rectangles, or in 3D parallelepipeds, and you give them a cell name, a cell number, and a cell type ID. And you can read that in as an initial condition. And it's a very verbose way of specifying things, because you have six ASCII coordinates plus the ASCII for the cell number and the type.
Right.
So if you have millions of cells, it doesn't work. If you have a few thousand cells, it doesn't matter that it's a big file.
Yep.
So in principle, if you have the positions of your cells, you can certainly write a simple Python routine outside of CompuCell that will convert it.
So I think the problem
isn't
is
anything automatic at the moment for it.
Okay, so we would need to simply convert so they're like ovular shapes, let's say, the cells.
But do you have a picture of what the data set looks like? Do you have a screen? Could you screen share the?
Can you
That's
see my
part of it,
screen?
at least.
Yeah, so this is like part of it. So this is like the ECM. So things really aren't rectangular, which kind of makes it an issue.
Right. Well, that's one of the reasons that you can make the PIF single pixels. So each of your rectangles could be one pixel.
Yeah.
Okay. Is
in
there
which case you
generally
just-
like an upper limit on how many pixels?
No.
So with what we were just looking at, so the green that you had in there, that was ECM, is that correct?
Yes.
Yeah.
Okay, and then for all of the space in between, were those individual cells?
Well,
Right
yes,
now,
but we want to break them down, I think, right?
Yeah, because that, I mean, the only tough part really is just identifying the simply connected domains within the ECM. I mean, with the data that you're working with, I mean, is it segmented in the sense that you actually have all the locations where each particular cell is?
Yeah,
We
so
could
like,
probably.
go ahead.
I was just going to say we could probably get that quickly with a MATLAB script or something.
Because I mean,
So what are you starting with? Are you starting with an experimental image of a histology slide or something like that? Could you show us one of those? Because that would help us understand what we're trying to do.
Megan, do you have the slide?
I mean, we've needed importers for a long time, and you're trying to do this in 2D to begin with?
Mhm.
Yeah.
Yeah.
Histology is 2D, right?
Yeah, so like like the previous one that did it, this is like the histology image that you would start with, and then like it would
Right.
import into like that.
Oh, yeah.
So
Right.
yeah.
Yeah.
Okay, and one question about the ECM. Is the
Oi.
ECM...
Escuta, tu tem o demo do 3D?
If we do this again next year, we'll use a fancier conferencing system, but everybody's familiar with both. Well, I don't know everybody. Most people are familiar with Zoom, so it makes it a little bit easier to use it when okay. Sorry, if you could leave that slide up for just a second, that would be great. Sorry. So where was I? So I was going to say, so is the ECM solid like or fluid like?
Yeah, so like the ECM would be built up of like individual like ECM like elements or like ECM agents, and same thing with like the fiber.
Right. Okay. Okay, and you're
I
actually
think
in your
it's the-
go ahead.
I was just going to say, I think it's the solid collagen that we're particularly interested in this case.
Okay, so it is a solid, quasi-solid material. But you could do that with a non-diffusing chemical field that repels the cells. Is probably the best way to do that. Because you're also going to want to have, from this picture, you're going to want to be able to have fibroblasts and myofibroblasts crawl around on this, right?
Yeah.
Right.
So one way to do that is to have a quasi to what we call a 2.5D model, where you have two layers, and CompuCell isn't quite as convenient for this as I'd like it to be, because you do it a lot, where you have two layers, where the bottom layer is the layer where your muscle and your ECM is, and then you have a top layer where your immune cells can crawl. That's how we did it with the our virus models. Yeah. The trick is if the muscle fibers can move around, they're not frozen, then you have to play some games to make sure they don't come up into the second layer. That's the issue. But okay, good. So this is a question of importing. And you have if you've created this kind of thing for your other methodology, how did you do the segmentation for your other model?
Yeah, for that one, so we took the histology and like read it through MATLAB, and it would like assign each element either like 1 or 2, and then when that got read in, it would it was in repass. So if it was like a 1, it would add the ECM element to the context.
Right.
And similarly with the fiber.
So I don't know, TJ, and I don't know how you decide to do it here. What I would do is well, I'll let TJ, why don't you give some ideas, and then I'm trying to think about the I know what I'm going to say, but I'm trying to think of how the simplest way to describe it. So you talk for a bit while I'm trying to think about the simplest way to implement.
I can tell you what we did. We did something similar to the for the beginning of the 2D migration, where you kind of give the pixels to the different cells. And that works up through like 8,000 lines of the CVS file. But after that, it just crashes my CompuCell.
And how does it crash? Does it does CompuCell disappear or something else happen?
Like the CompuCell disappears, but like the terminal and the twidit stay up, but then the twidit goes away if I try to do anything with it.
So it's a Python crash.
Okay.
And so do you want to share your code and maybe we can look at it together?
Yeah.
I mean, there are a lot of ways of doing this. So you're reading in a CSV file.
Mm-hmm.
And then based on the CSV file, you're running through the CSV file pixel by pixel.
Yeah.
And you're converting the cell, the cell lattice to being the type that you want based on those pixels. Is that right? Okay. And you created, and is the ECM now a single cell, or is it many small cells?
Originally, I had it as a bunch of small cells, but I was worried that there were too many cells, so I turned it into one. Either way would work fine. It just needs to not crash.
Right. So okay, read it in, all right, but the read in is okay. And you put that into, okay, so let me just look. So line 10. Okay.
So real quick, one thing that I see is that in operations at like line 40, so you can set and get things in the cell field just using it like a NumPy multidimensional array. So you can actually replace the dot set and then with the two arguments. Instead, you can just say self.cell field and then square brackets and X, Y, and Z, for the coordinates, and say equals cell underscore ECM. That's probably not the issue here, but we have some built-in checks in these operations. And in this case, so it'll be one set of square brackets with all three coordinates. Yeah.
And so how big is the array is 120, 140 by 140, right?
It's close to that. It's a little uneven. I think it was like 107 by 148 or something.
So it shouldn't be crashing. It's not, it shouldn't be an overflow type error for that. Sorry, that's not quite the syntax though, is it? TJ?
Oh, no, so I put it in the chat. There's a code snippet.
No, sorry.
And so when the crash happens, does like the terminal close and everything? You just get no feedback whatsoever?
I get some feedback. It's an error that says, let's see, copy it down. Abort trap 6.
Oh, that's not helpful.
So I wonder if the issue, and how many, and it gets halfway through before it does it, is that right?
That was me just tinkering with how many it would successfully do. And it was somewhere between 8,000 and 9,000 lines. And the file is a little bit over 14,000 lines.
Well, I guess, could you run it for us and let's just see it? I'm sorry to be dumb, but
yeah.
Oh, and that's Z, yeah.
So let me just see it. So you do.
Okay.
I wonder.
Okay, there's that. And then let's try bumping it up. Oh, it's working now. Great. Let's try doing the whole thing.
I wonder if it's reading one line past the end of the field or something like that. If there may be a one line of your data set that's different structure.
Cool. Well, that works. I wonder if it was that one line. We'll do this too.
It's a good sign.
Okay. Well, what I've always had very mixed feelings about Python, because Python's an extremely powerful language. It's also possible to write code that is impossible to debug. Right? I mean, any language which allows you to define an arbitrary string and then execute that string as code. And of course, the lack of typing and these things. all those things that make Python so wonderful also make it a little harder to debug. So, and then there are the additional issues in CompuCell of scoping, where sometimes the data you think are available in a place aren't. So, but great. Okay.
I have another recommendation for you for operations like what you have on line. It'll be, I think, 17 now. When creating cells, try replacing self.pots.create cell with just self.new_cell, and then pass as argument the name of the type that you'd like to create. So yeah, exactly.
Cool. Is there a reason that the fiber is not getting within the ECM? Do you have to define cells as completely connected?
Sorry, say that again. I missed.
Here, let me try something real quick.
I see what you're doing.
Megan, is there fiber within these regions? There should be, right?
Yeah, so what it should look like is like that red like fiber should be within the ECM, like where it's currently black.
Okay. I'll look at the CSV.
Hey, Tyrone, what can we do to help out?
David is disconnected again. So let me see. I'm waiting for him actually.
If it's okay, we're good. We're helping. We're debugging this project. One of the projects. If you're welcome to stay here, or you could join. I guess Vignesh seems to be on his own. Why don't you go talk to him a little bit, since you know a lot of you're an experienced modeler. You'd be willing to do that, and then
which one? Which one you said?
Vignesh at the end on wound healing.
Okay. Yeah. I can join him. Okay.
Okay. Thank you.
Thank you.
You're welcome to stay here too.
That's fine. Yeah.
I think there might be 3 types of cells, Alexei. 3 types of. It seems to have 1, 2, and 3. I think 1 is a boundary type. So try type equals 3.
What should type equals 3 be? What kind of cell?
Should be the fiber.
Yeah.
Oh, okay. So we'll just do 1 or 3.
Did that work?
Yep, that worked.
Perfect.
Cool.
All right. Thanks very much for your help.
Yeah. Yeah.
Seems to be working.
Can I take a look, see what you got? My internet dropped for a second. So I'd like to talk to you a little bit about the model before you get going too much, because I want to just understand a little bit about the model structure that you're building.
Yeah, that'd be great.
So are the myofibers going to be moving around, or are the things that are going to be moving the immune cells?
Yeah, so the immune cells will move around. The fibers themselves, they'll become damaged and then they'll be regenerated. So in that sense, they're not really moving per se, but just being rebuilt. And then TJ, in terms of each region, so those like fiber sections that we're seeing, they should be like made up of individual fiber elements, and that's how like little portions of it will be damaged. So like the whole fiber in and of itself won't like become necrotic. It'll just be like individual elements within that.
Okay.
So I might think about whether you actually want these things to be cells.
Okay.
In other words, typically we use the cell object. So this is why those exercises that I should have introduced at the very beginning of the week, those documents about how to think about model construction, might have been helpful. Which is, you usually want to define as CompuCell cells things that are going to be moving around. In particular, things that have active motility or things that are going to get pushed around a lot. And if the things are not behaving actively, if the things are not behaving actively, sorry, David, Tarun was looking for you. If things are not behaving actively, then it's usually better to use a chemical, what we call an auxiliary field or chemical field to put them in. And then you could have your immune cells be a cell type that moves around actively and does things to the field. In other words, if the stuff that you're showing here is passive and the things that are going to be moving around are immune cells, you might want to think about using an auxiliary field for this stuff and reserving the cell field for the immune cells. And so you could do exactly what you did here, except instead of creating a cell, does it matter that the cells, you're drawing little individual myofiber pieces, the fibers. Do those actually have to have unique identities? Are you going to be counting them as individuals? Or do you care about the area of the biofiber?
I mean, I guess we would care about like, in terms of like output, we would want to know like what percentage of them were like damaged and what were healthy. So that we could track the progression of like regeneration. And then also in terms of it, just like how the satellite stem cells would like add to it to help it regenerate. That like would need to be tracked.
Because one of the things that's going to happen here is that there's an excluded volume. You can't have two cells in the same place. And so let me just, sorry.
Yeah, so that would be one of the problems of having all the cells on the pixel level as well, right?
So yeah, you don't want to, so conceptually, a cell is a cluster of pixels.
Yeah. Right.
And you could divide, if you were going to do this officially, and you really want to have your myofiber compartments, what you would do is you would create each one of those myofibers that you're sectioning would be a cell. And each one of those little myofiber fibers would be a subcell, a compartmental cell within that cell. And so each one of these circles then would be defined as a big cell with lots of subcompartments.
Because that's technically what they are, right, Megan? Each one is a cell that has individual myofibrils.
Right.
Now, the only issue with that is that now do you care about myofibers in terms of their individual identity, or do you care about the area occupied by myofibers, for example?
So it's strange. We need them to be able to change. So each of the individual myofibrils needs to be able to die, but it also needs to exclude the volume while it's dead.
So are you going to have some situation where the overall geometry changes, where the tissue collapses, for example? Or is it going to stay fixed? Sorry. Go ahead.
Yeah, because we want to look at like cross-sectional area. So like when it has like necrosis, like in theory, we would see like some of it like gets a little bit smaller and then it would regenerate back up. Or that's how the
Right.
previous model had worked.
Okay, since I haven't seen the previous model, I guess I don't know if I know what you, if I'd see, maybe you should show me the previous model because that would help.
I'll show you like that screenshot again. So we see that like we have like this pre-injury and then you have like your muscle fibers and then some of those like individual elements are turning necrotic. And then like as it goes on, like the ECM and like the fibers are like kind of moving or like reshuffling as it's like regenerating and like the overall CSA of like that section like decreases. And then we'll like build back up slightly as like it regenerates.
Okay. And the ECM has what kind of mechanical properties here?
Yeah, so the ECM can have like different levels of collagen. So when it's the fiber is necrotic, it'll get cleared and then it'll be replaced with like a low collagen density ECM. And then like the fibroblasts can go around to like help build that back up.
Okay. So I think I would, and so how did you represent that in your current, in your existing simulation? So what's, I see your myofibers getting shrunk here at day 28, for example. I see the ECM seems to get bigger and then smaller again. How is this?
Like,
I'm just
Yeah. So, no, go ahead, Megan.
You can go ahead.
I was just going to say the basic way that it works is that these cells shrink because they're intoxicated. They're intoxicated and part of the cell dies.
Right.
And they shrink. So the ECM expands to fill the space. And then it's the job of the immune system to rebuild the muscle over time.
Right. Okay. So what I would suggest then, now what does the ECM, right, again, since I'm jumping in the middle, there's a lot to process because it's a very complex model.
We're there with you.
The zeroth order model I would have built would have been to say that I model the extracellular matrix as a field because you don't need to have subcomponents of it. And that's not a diffusing field, it's a static field. And that ECM has the property that it repels, that there's a chemotactic repulsion to the myofibers, which effectively makes it a solid. And then if you want to model the myofibers as agents the way you've done it, you could now the problem is, yeah, okay. So you could make them compartmental cells. And then when you're creating these little blobs of myofiber, instead of making it an independent one, you make it part of a compartmental cell. But to begin with, that may not be necessary. It may be okay. So you're creating, when you showed that picture, you're creating thousands of little myofiber cells. Each fiber is a separate cell. Is that how you did it?
In CompuCell?
In the thing you just showed, in the simulation you just showed, yes.
Yeah, so each of them was individual.
So each one of those little squares is a separate cell.
Yeah.
Okay. That's okay to begin with. I guess it's not a problem. And then you're going to want to kill some of those. Okay. So what are you going to have? What are the properties of those myofibers going to be? They're not going to be moving actively, right? They're not going to be very motile.
Right.
They're going to have a more or less constant, each one of those fibers is going to have a constant volume or nearly constant volume. So they'll have a high, the way to get cells to be non-motile is to have a very high lambda volume. Have that volume constraint be very large. That makes them non-motile. And then you'll have other things that'll come in and kill them. That's easy. And then you have to have some sort of rule about what happens when they're killed. Are they replaced by some, what are they replaced by?
We talked about, so like, oh.
Go ahead.
I was gonna say, like, we talked about like the injury would be like a field. So like, say it was like a cardiotoxin injury, so that would like spread out, and then those like fibers that were in that area like would be replaced with like a different cell type, so like a necrotic agent.
All right, sorry, I got distracted for a second. So I say that again. Somebody sent me a message about.
No worries.
Sorry.
Yeah.
Again,
so we would have
running the meeting and talking at the same time are always a bit difficult. I appreciate your patience.
Lots of multitasking, I'm sure.
No, I'm trying not to because this is a complicated problem. So I want to make sure. Okay, so go ahead. Say it again.
Yeah, so we would have some injury that would be like a cardiotoxin like field that would like spread out to like a percentage of the myofibers. And then those that were like impacted would be replaced with a necrotic agent in the same like space.
Okay. And how do you get the collapse of the actual myofiber? That because you see in the simulation that you show that the volume of red goes down as the simulation runs. Is that right? Or is that being just because those are being replaced by, in the total perimeter of the tissue also changes?
Yeah, because that's like an output that we would want to look at. So I would say like the reason you're seeing like the shrinkage is so like you have the necrotic elements, and so at first it's all like the same size, but then as those inflammatory cells go in and they'll like remove that like necrotic agent, and then it replaces it with some amount of like ECM, but it wouldn't always be like the same volume is taken up by that amount of ECM, so it's like getting somewhat smaller.
So there are a lot of different ways you could represent this, and that's I think one of the complications here is depends what you want to do with it. I mean, you could make the whole each muscle fiber cell, myofiber, a single big cell with low motility and change the target volume. And of course, that will shrink and grow, but they won't keep the shape that you want. They won't have that stable shape that you want. Another thing you could do would be to actually use a auxiliary field to represent those myofibers. And those would keep the shape, but you wouldn't have a count. The myofibers wouldn't have an independent identity. It would just be a cluster of myofibers. And you could go in and replace the value at a given place, but it wouldn't have it would be a countable identity. You wouldn't have a number of them. You'd have an area of them. The third thing you could do is what you've done, where you've given each little fibril its own cell identity. There's nothing wrong with that, certainly. And those could either have a very high lambda volume so they don't move, or they could be frozen. And then you could go in and create and destroy them, which is the way I guess you did it in your previous simulation. The only disadvantage of that is you're going to have a lot of them. So the simulation will be a little slower, but there's nothing wrong with that. And then the third question, and then if you go that way, you have to decide if you care which cell you're in which case you should use a compartmental cell where you define the cell as being that whole pink connected region, and then you define subcompartments with the myofibrils. And that's going to be a slightly trickier with the with the initialization, because you have to have some idea of which cell you're in, because you're going to have to give each cell a unique identity. And TJ probably could help us out with how to do the subcellular definitions. As far as the ECM goes, you also want to think about whether you want to make that a cell type or whether you want to make it an auxiliary chemical field.
Mhm.
And the advantage of making it a cell type is that you have material which you can move around.
Mhm.
The disadvantage is that you won't have any place for your immune cells to go, because the space is already filled up with the ECM. You can't have co-occupation of space. Now you could do a 2.5D model where you first do this layer, and then on top of it you put the ECM, the immune cells crawling around. So those are possibilities, and which of those you choose is really going to be a convenience decision, but it's going to have relatively long-term consequences because, well, I mean, at the moment at this level, changing those decisions may be an hour, 2 hours worth of work. If you build a very complex model and then you discover that at the beginning you made a decision you don't like, it's more work to change. And so I think one issue you might have to think about early is when you're going to be modeling these immune cells and the other cell types. You have satellite stem cells, myocytes, and so on, is how big are they compared to everything else? Because one practical matter in CompuCell is that if you're going to have cells that move, they can't be fewer than about 8 or 9 pixels in volume. If they get smaller than that, you're going to have problems where they disappear on you when they move around. And so if you want to have actually spatially extended objects which represent those cell types and they move, then that's going to set a length scale. So you may have to do something where you take your simulation and every pixel that you've drawn so far, you replace with 3 pixels. So you zoom in a little bit so that you can get a scale where those those immune cells are big enough that they can be represented spatially.
Megan, do you know what the grid square size is in this model that you're showing us?
I can look. It should be. It's a 150 by 190.
I'd say it doesn't look very high resolution. So,
but you can always simply say that each one voxel in your source turns into a 3 by 3 square. Multiply everything by 3 or 4, make it bigger. But you may have to think about that. I'm just thinking about trying to give you some of the things you might have to address when you go through this. TJ, you've thought a lot about representing quasi-solid ECM as a field. Do you have any ideas on this?
I mean, my go-to is the work I did in my dissertation, but I'm not entirely convinced that it's
relevant.
Yeah, in this application, and the amount of work it would take for them to even try it out is not worth it, given that I'm not at all confident in it for this problem.
So I think again, I'm not trying to be discouraging. The issue is that you've got a lot of things you might want to do, all of which are possible, and so I think that the trick is going to be, I mean, the way. So you've got your initial condition that you've defined. what would the next thing you'd want to do be?
So like from pre-injury to like day 0.
Well, you've created a picture which shows me myofibers and ECM.
We probably
And now
need to
you're going. What do you want to do next? What would you add to that simulation next?
Yeah. So like the next step after that, we would start to like define some of like the other like cell behaviors. So we had talked, like you said, about like if we had it on like different planes, like how that would work. Because like one thing that we were unsure about is like the satellite stem cells, they would help rebuild that fiber. So could they be on like a separate plane, and still help regenerate that?
because they become fiber. That's the thing. And so, yeah.
Well, so what you could do, so when the tissue collapses the way it does there, are the position, is it very important that at least at the beginning that the positions of the fibers as a whole move, or is it only the area of the individual fibers relative to the I don't know, you have to help. So fibrils are the individual filaments within the myofiber, and the fiber is the whole cell. Just make sure I'm using the right term.
Yeah.
Okay. because if I want the tissue to be able to collapse as a whole, that's going to be a little bit more work. If you're comfortable with the myofibrils being frozen, so I could destroy them and create them, but they don't move, then that makes things a lot easier to begin with. You can undo that later, but to begin with, it makes it a lot easier. So tell me what the other cell types do. So we have the muscle fiber, and we have now you have fiber membrane shown here. What does the membrane do?
Yeah, so that was kind of like the fiber border. So the idea is like when it regenerates, it's not regenerating from the center out, it's regenerating from the like border. So it's like adding on to like the border side. That's how it like recognized it in the old model.
Okay, so does it do anything else, or is this simply the place where regeneration happens?
Yeah, that, and it helped prevent like the fibers from merging together, so there was always like some ECM in between.
So you use some kind of repulsion between, okay. So basically you have the fiber, because you have, everything is motile in your existing model, is that right? Everything can move around.
Right.
Okay, got it. And then tell me about myofibroblasts.
Yeah, so they start as like a fibroblast agent, and then they can like transition into a myofibroblast, and that's what helps rebuild like the ECM from like that low collagen. So it can help it like build up to like a healthy collagen level, or if it's like prolonged inflammation, it can turn into like fibrosis, which with an acute injury, like I don't think that's going to be a big part of our model, because typically that's something that you would see in like a disease like muscle regeneration state. But like the fibroblasts would be important for like rebuilding the ECM.
Okay. And in your simulation, as you've got it, it's a 2-layer model, is that right? Your existing
It's all, the existing one I believe is all just on like it's one 2D layer.
Okay, I'm just, when I see the picture, I'm not sure how to interpret it. Okay, and then you have stem cells. And so the stem cells are the cells that are going to rebuild the muscle fiber, is that right?
Yeah, so they have their own like cycle that they go through where they'll like proliferate, and then well they'll have to be like activated, and they can like proliferate, and then eventually they'll like go through and become like a differentiated myocyte, which will then fuse and like help regenerate the myofiber.
Okay, I get it. All right. And how is the ECM created and destroyed?
So I guess in terms of it being created, so when the necrotic element is removed, it's replaced with a low density collagen.
Okay. And the collagen basically repels the myofibers, it pushes on them.
So like the collagen is like just an attribute of the ECM. And then like, yeah, the ECM would like prevent those like fibers from coming together.
Okay, so I'm trying to understand. So the density of the collagen would basically correspond to the compressibility of the element of the ECM, if you did it that way.
Right. So like the collagen density, yeah, it kind of like before it was representing like the amount of like fibrosis that was there. And like the strength of like the ECM, like biologically, I guess.
Okay. Because again, the issue for me, I mean, we can certainly emulate the model that you've written, and I just want to understand. Okay. I'm trying to, the better I understand it, the more I can help. If I don't, I mean, it sounds like you understand what you're doing very well, so it's not that you need help. But if I'm going to try to help, I need to understand.
Yeah, we'd love help because this was done like previously, and I mean I'm fine with like making simplifications on this to incorporate like more of the spatial aspects, because this didn't have like growth factors or cytokines spatially, which I think is like an important factor that needs to be included, as well as like the macrophages and neutrophils weren't spatial, and that's something that like we want to include spatially.
Okay, so the thing that you're going to have to do quite a bit of, I think, is you're going to be creating a lot of auxiliary fields that are going to define spatial information. And so again, if the ECM is fundamentally solid-like, you're going to have again, let me give you some options about thinking about this, and from the simplest to the most complicated. The simplest one would be that each of your myofibers is just a cell. The ECM is a field in the medium that repels the cells. And then damage happens, the myofibers shrink, and the medium fills in the space. Now that's not very satisfying because it doesn't have the mechanical preserved structure that you want to have. The second easiest one to do would be to make your individual fibrils independent cells the way you've done it, and then still have the ECM be a field. And in that case, you'll be able to have the individual fibrils collapse and grow back. The myofibers collapse and grow back by creating fibrils. But the tissue as a whole won't change shape. The thing won't, the whole tissue won't collapse because the positions of the fibrils are fixed in space. And then the third one would be doing something more like what you've done in your old simulation, which is both the ECM and the fibrils are composed of a lot of little elements. And if you do that, you'll have the advantage that the tissue has some mechanical properties that you like. The difficulties with that will be, one, that you'll have a lot of cell elements. And so that makes the simulation slower. And two, that you have to have some way of getting your other cell types to interact with the system. And so those other cell types would probably have to get put in a second layer. And we may run into some issues with them keeping it flat, basically having your two layers behave properly, which sometimes happens.
The first things that I can think of, so in terms of like comparing like the model output, I know that we would typically look at like the cross-sectional area. So for me, like thinking of how that would be done if the ECM isn't changing would make that hard if it's like a static cross-sectional area for like that fascicle. Right.
Well,
but
the
then
ECM area will change. The ECM area will change, but what won't change would be the outline of the tissue. The tissue as a whole won't change area. The fraction of the area that's myofiber versus ECM will change.
Okay.
And that's but okay, but I think, I mean, we can build this. I don't think I don't see anything, again, I don't see anything fundamentally complicated here, although there are going to be a lot of decisions to make. The one thing that I think you do have to think about, perhaps, the thing that maybe is going to be a little trickier, and maybe you want to make a decision earlier, is if you're going to do these. Let's come back to your myofibers. So you were drawing, was all space when you drew your picture, was the whole space there filled within the cell boundaries? Was everything filled, or were there gaps?
It was all filled, but now we're adjusted so there's gaps around the edges.
Around the edges of what?
I can just
Let's come back to the simulation the CompuCell simulation, and let's take a look.
I think she just means that the tissue isn't square, so
okay,
around the edges of the tissue.
Yeah.
Okay, so here, okay, so each one of those little squares is an element of ECM. Is that right?
The green ones.
I'm just trying to understand. Yeah. So you've defined the ECM as a lot of little blobs, and the myofibers is a lot of little blobs. Is that right?
Mm-hmm.
Right.
Okay, that's all right. Okay, and then let's run with this. All right. So okay, so and what cell types do you? The only thing that you might want to do, and you can come back and do it later, is if you could somehow identify the myofibers as the myofibrils as part of a cell,
mm-hmm.
and put them as subcellular elements rather than cells.
Yeah.
And TJ, you'd have to help me out on how to do that. I don't remember. I'd have to look up in the manual how to do it. So I don't do that one very often. The thing that you would have to do, though, is have some kind of ideally, you'd like to have some kind of counter that says which cell is which. So you created a cell type ECM? That's fine. Did you have a necrotic cell type or something else like that?
Yeah, we were talking about adding in that as a different cell type. Because we had talked about like maybe having like that be like a dictionary like or an attribute to the fiber, but I think it would be easier to just have it as its own agent.
Okay. Yeah, if you want to do it that way, that's how I would do it. I would create a new type. All right. And what are the attributes you've given to these components at the moment? Have you? In other words, if I run this simulation now, what happens?
We didn't get that far yet.
Okay, well now it seems to go. Now it seems to actually load the initial model. What happens if you run it? All right. Well, it's not totally crazy. It didn't crash.
That's fair.
So what's happening there? First, what is the gray color? Is that the ECM?
That's the ECM, yeah.
So what's happening there is that things aren't first the ECM and the myofibers don't seem to repel each other very much because they all have uniform energy. And the second thing is everything is too motile. So you probably want your ECM and your myofibers to have a high contact energy. And you better make the contact energy of everything medium high, or well, you'll see what happens. Try that. As experimentalists, you should change one thing at a time. So let's try just change that one thing and see what happens.
I'll undo this one.
I mean, the advantage of doing see now the medium is coming. Okay, that's not too bad. So the problem you're going to have at the moment is that if you want the myofibrils within a cell to stick to each other, then you're going to tend to get the myofibers are going to want to stick to each other too, because there's no way to know that you're part of a different cell versus the same cell at the moment. And when you did your segmentation, did you do identification of the fiber that you were in? Is that something in the data set or not?
I know there were extra rows, but I don't know if I don't think they were used in the previous model to like identify which ones that they were like in a fiber group with.
Okay, because that would be very helpful. If those numbers were available, that would make your life a lot easier. Because grouping them, I'm trying to think about the best way to do that. I mean, I have some workarounds. I have some workarounds that I could suggest, but they're sort of kludgy. So one thing you could do would be to read in the ECM field. And one thing we'd have to figure out is, okay, read in the ECM field. Find just the ECM part of it, create that. Now you find medium. And you put a cell in the medium, you freeze the ECM field, you don't let it move. And now this is all going to be creating a new initial condition. Now you create a new initial condition, which is that skeleton of ECM. And now I go through my image and I find a point which is medium. And I create a cell there. And I now have that cell grow until it fills all the space up to the ECM. And so now I know that space belongs to that cell. And so now I have a spatial region that goes to that cell. I now do the same thing again. I find a new mixed medium pixel. I grow a cell around it until that's filled. I go through that, and this is a kind of image segmentation. We actually published a paper decades ago on how to image segment this way. And now you've filled up all the medium with all the space between the ECM with cells. And now I can identify that. And I know this is the region of cell number 1, this is the region of cell number 2, this is the region of cell number 3. Now, it's not very elegant. I write that out. And now I can go back and now I can read in my field again, and now I find your myofibers, and now I replace those myofibers, the cell with the myofibers as part of that cell. And I would have to look up how to do that creation of subcellular elements, because it's not something I do very often. It's in the manual. It's all in the manual somewhere. But we could do that, and that might not be a bad way to do it. And then once you've done that, you'll have what you want, which is you can then define a different contact energy between the fibrils within a cell and the fibrils between cells. Because in your old simulation, you created that membrane around it to prevent the things from merging. We could do that here too, if you wanted to, or we could go this way. They're both possible. But you'll probably want to identify the big domains as separate. So let's come back to the simulation that you just showed. And let's just do some quick things that we could maybe do to make it look a little bit, make it behave a little bit better. Okay, so let's run it again and see what we've got. And I incredibly strongly urge you to, so let's actually step it rather than running it. Well, let's actually step it and see what's happening. Let's start it over. And if you want me out of your hair and you want to play with it yourself, just say so. I talk a lot. Okay, so the first thing that you see there is what do you see happen? What are the black spots?
Is that the medium?
Yeah. So how did you define the target volume of your fibrils and your fibrils and your are the fibrils okay, great. Are the fibrils one by one? Oh, their target volume is 1. Wow. Okay. So target volume of 1 is really going to cause you problems.
I think they start as a volume 1 though, right? So I think it might be a cell death mechanism. I'm not sure.
So the problem with having a cell target volume of 1 is things can't move. Because remember that things are we move things by creating and destroying pixels. And so if you have a target volume of 1, the only way you're going to be able to get things to work is going to be able to the only way when the cell moves, it disappears. And so that's going to be a bit of an issue. So I would suggest that to begin with, you double or triple the size of your lattice, and you draw squares, 3 by 3 squares, instead of 1 by 1. You might just make a comment on that for the moment.
Yeah.
And then if you want the things to basically not move around, which I think is what you want, you're going to have to make that lambda volume pretty big. 100 is already big, but you may have to add a 0 to it to make things very stiff. And I think that will help out quite a bit with what you want. So why don't you try doing that? And then why don't you also look do you want to try to do the identification of the fibers and the components?
Yeah.
Because okay. So why don't we do very quickly? Oh, so Kato, is it Kato or Kato? Are you? Did you need? No, she didn't. I just don't. So what I would do is first I would figure out how to draw 3 by 3s and so increase the spatial resolution of your image.
Mm-hmm.
I think that's important. I think you'll have a hard time with 1 by 1. The second thing I would look at is just keep doing what we've done. But let me just show you quickly how you might do a simulation where you do the thing I suggested. So let's go through this. Let's do this again, but only draw. Why don't we version this and we'll say it's a test or something like this. Or you don't have to. Let's look at the code. Let's go through the code and let's read in the data. And in the XML, let's make the ECM frozen cell type.
How do I?
Let's see. I think it's /frozen, and I don't remember where it goes. I have to look that one up. TJ, if you're there, maybe you remember where the frozen tag goes.
Yeah, it'll be in the. So it'll be a third attribute in. Yeah, so you can erase the slash. And then after frozen, yep, just an empty quote or empty string.
So let's try that. And the volume is defined in, okay, fine. So this should work. So let's run that and see what happens. Let's actually, okay, good, okay. Something is odd because if it's frozen, why is it not?
As I say, I think cell death is activated, so I think that's what's going on.
Yeah, but it
Yeah,
shouldn't be.
but if the cells are frozen, they shouldn't be moving. Let's see. The ECM type. Are we sure we saved this?
Yeah, because they would be
Okay.
Reddit support saved.
Okay, so hit stop and restart your. Occasionally, player doesn't reload the latest version of the code, so let's just make sure that it's loaded in place.
I'm sorry, I told you wrong. It should be freeze, not frozen. My bad.
Okay, that would explain it.
Yeah, there it is.
There we go. That's better. All right, good. Much better. All right.
Oh, that's weird.
So now, and you've got some of your myofiber leaking out into the surrounding.
Yeah. So.
Okay, but that's more or less actually, okay, so this is what I wanted. So probably the issue is the interaction range is what's doing that. But all right, so now let's just do this. We're going to actually have to do some of our creation of the simulation in the step function rather than the start function.
Can you explain, like, how do you know, like, where to put things if it's in, like, the start or the step or, like, the initialization, like, when you're looking at the stepables?
Okay, so typically when you're creating an initial condition, you put in the start function.
Okay.
But the start function doesn't run all of the solvers and everything else. So sometimes you have to cheat. The step function is called every Monte Carlo step, or you can make it actually called more than once per Monte Carlo step, or every 10 Monte Carlo steps or something like that. But in general, the step function is the thing that does the evolution of the system. But this is something that in a sense is a convenience. Just the way you can create multiple stepables or put everything in one big stepable. You can use the start function, which is called before everything else, or you can do things in the step function. You could have in your step function, if MCS equals 0, do this. And then that'll be called once at the beginning. And that's not very elegant, but for certain purposes, it's useful. So what you've got there is, here's what I was going to, and again, you don't have to follow my advice, but my suggestion was, if you want to identify the cells by region, let me just show you something that you can do that I think would be sort of fun. Yeah, so you want to do, you're going to want to upscale things. So let's to begin with, only draw the ECM. And I wouldn't, you can just comment it. Yeah, there you go. Okay, and let's see what happens when we do that. Okay, good. So now nothing is going to happen. It's going to be boring. So now let's, in the start function, go do something a little more interesting. Let's go in to the start function, and let's do a while inside. I'm sorry, not the start function, the step function. Let's go in the step function. At the moment, I don't think you have much in your step function. Is that right? It's basically empty.
Yeah, I mean, of the steppable, there isn't even a step function.
Okay, so why don't you grab just the def step line there? Okay. All right. Okay, and let's do the following. Let's do a while. Let's pick two random numbers, which are coordinates of within my lattice. So you probably have to import. I wish we had pre-imported NumPy and random, so we didn't have to keep doing it. But okay, so let's pick a random number between 0 and xdim, and a random number between 0 and ydim. And do the same thing. What I want to do is I want to find a spot that's medium. I want to create a cell. I want to grow it out until it fills my space. All right. And now, and I'm going to have to check. I'm going to have to iterate over. So let's create a flag which is found space or something like this. Found space equals false. Or and then while not found space, colon, we grab our position, great, and now we're going to check. We're going to check if the pixel at the position x rand y rand is medium or not. So we have to do. So yeah, we want to check that. Yeah, x rand y rand. Good. And now equals. Now we have to be a little careful about that because TJ, you're on. We have to actually do a type, right? We have to check on the type. If we do, can we get? If we do, what does self field object return?
That's
returns the cell.
That's the actual POTS cell field where the cell IDs are stored.
Okay, and if I do type on that and it's medium, will it cronk or will it be all right?
Yes, it'll crash.
So medium doesn't have a type?
The type, well, it's the none type.
So if I want to know whether I've got pixel of medium, what's the fastest way to do it?
So you could do, to start at line 58,
Yeah.
declare that, say like cell equals self.cell field. Yeah. And then in the next line say
if not cell.
Yeah, or if cell is not done.
Well, in this case, we want it, if it isn't, what we care about is if it is, we want to find a medium pixel.
Okay, yeah, in that case, just if not cell or if cell is none, either would work.
If not cell, okay, good. So now we've got a medium pixel. So you need a colon after your if. Okay, and so we're not going to create, let's use one of your other cell types for the moment, because it's going to be, it's going to be something temporary. It's a convenience thing. So let's create a new cell. Let's create a new cell. Actually, it can be type fiber. That's all right. That's all right. Doesn't matter. Good. That's perfect. Now, let's make the target volume for that cell. Target volume for that cell to be something large, and lambda volume for that cell to be something large. All right.
Do you want this to be happening every step or just on the first step?
Let's just do this, and at the end of that, if you're in our if statement, we want to turn found space to true, so we don't do it again.
That's fair.
And then let's see, will this work? Do we have to do a break? I'm trying to remember.
We shouldn't have to do a break, but this will try to make one every single step, which might cause issues if you initialize multiple cells.
Right.
Within this.
We only want to do it once to begin with. I want to see that it does it one time correctly. So yeah, so we should actually, that works too. Yeah. Or you could actually no. Or you could have used, no, that should do, I think that'll do it. Let's try it. No. Oh, double E.
Yeah.
Indent. Oh yeah, those two lines. So that'll be it. Did it create a cell? Input object is not attribute. Self.x. What is it's the syntax? It's the let me look that up. TJ, you know these things by heart, and I always have.
Is it just
What's
about,
the? All right.
I don't know.
No, let's see. Where is X dimension stored?
The self.dim.x.
Thank you.
Oh, it's doing the thing. It's like trying to.
It's weird though, because it's like turning into ECM.
Let me see. Sorry, I lost my screen. Okay, good. So, all right. So what cell type did we create? Let's see. Why is it not doing what I expect? Let's see what happened. Let's see what it's doing. Let's go back and take a look at it. Why is it generating multiple cells? How are we picking the cell type that we're generating? That's interesting. Huh. Very interesting. Let's take a look at the code again. So it should only be nucleating once.
Yeah. I mean, I think it is only nucleating once, and then actually, wait.
Oh, I suspect. Let's see.
It's going up to, there's a second layer. But
Oh,
I don't know.
you set it up as a 2-layer system to begin with. Okay.
Yeah.
That's helpful to know. I didn't know that. Okay. Let's look at your code again. So we created a cell type fiber.
Oh, okay. We just like made this code with the wizard, so we haven't changed anything yet, but we included like growth.
Oh, yeah, you better get rid of lines 82 and 83. That's going to make a mess.
Well, we want, oh, you're right.
And you'll need to put a pass in. No, well, okay. All right, fine. Okay. That one shouldn't matter. Well, actually, you wanted not, in line 103, make that 500 or something. Okay, good. Okay, and try that now. I didn't realize you had the rest of the stuff.
Yeah.
You've got everything laid out already because you know what you want to do. I should probably get out of your way.
No, you've been super helpful.
Okay, so why is it not there? There we go. It's creating a cell. So the one problem is that the interaction range is crossing over the. Yeah. This is going to be an issue. As I say, 2.5D is a little complicated. So let's. Are you doing anything in that second plane at the moment?
Nope, not right now.
Okay, so can we have two options. Either we temporarily have to fill that second plane with something that is blocking everything, or we're going to have to, can we just reduce the thickness to 1 and let's get this working?
Is there any way to restrict the movement of those, like the fiber to not go up?
No, that's what I was saying about 2.5D. Yeah. There are games you can play by changing the adhesion with medium. TJ's is good at that, but they're sort of there are tricks that you have to. Okay, so now I think what's happened is we've set the target volume to 100 and back to 100. So let's make that target volume bigger than that. Okay. Okay, and it's jumping because the interaction range is larger.
Yeah.
Okay, so but it's still, to begin with, that's not too bad. So what we could do is you can inquire think about how to get it to not jump. It's going to be a bit of a problem. What was the interaction? What was the interaction range you used in your XML? 3. Let's make that 1. Okay. And I think that can actually be changed dynamically, although I'm not sure about that. All right, let's see this. Okay, so that does what we want. So now what we could do is we could inquire on that cell inquire on that cell. So now let's take that thing. So we now know how to create one cell and fill one space. The next task, if your mission, should you choose to accept it, would be to do the following. There are a couple of different ways you could define the when you filled the space or not. One way to do it would be to use the neighbor list and ask the question, are there any neighbor pixels that are medium? Another way you could do it is by looking at the pressure in the cell and ask the question, is the pressure in that cell positive? Is it being pushed in? And both of those will work. And what you want to do then is when you figured out how to determine that that cell has reached its boundary, you want to create another cell. Go back and do the loop again that we just did. And what that will do is it'll go in and it'll fill in each one of those regions with a cell, and it'll be a unique cell. And now I can go back and do what you've done from the beginning, which is now I run through when all of the space has been filled with cells, I now run back and now I have a unique identifier. This is basically doing image segmentation, right? So now each of those domains will have a unique ID. And now I can run back and go through that scan that you did originally at the beginning. And instead of creating a cell, myofiber cell at that point, create a myofiber subcell at that point. Is that clear? So now you have a unique cell index for each region of space. And now when I create my myofibril cell, instead of creating a cell, I create a subcell. And so now I can define those regions as being separate from the rest.
Okay. Yeah.
You could probably come up with a more elegant way of doing it, but that would do it. And then I think from there you can go on and do quite a bit. So you might want to actually then write the whole thing out. In other words, this might be you run this with your image first, save it, and then read it in again instead of making it a part of your whole simulation. But this would allow you to build, I think, what you want, which is each cluster of myofibrils is a separate cell.
Yeah.
And now, yeah, go ahead.
If we were to try to save this, what file format would this be?
Well, you can, so there are a bunch of export formats. Again, TJ is the expert on that. You can save it as a PIF, which is not very pretty, but you can do that. There's a bunch of,
or I guess you were saying that.
Yeah, the PIF knows about subcells.
Okay.
And so I think from there you've got pieces that you can build more. And if the reason you might want to save it separately as a PIF and then read it back is that you might want to save it as you might want to do this part of the simulation with nearest neighbor only and really in 2D in a single layer. Save it and then read it back into a simulation that's too high, a level has two pixels deep and has a longer interaction. So this is sort of a simulation that's generating your initial condition.
Yeah.
And I think that does that give you something to work with? Can you play with that a little bit?
For sure.
And I'm happy to try other things, and I'm happy to. I don't want to derail your project. So if you had a strong idea of how you wanted to proceed, I don't want to derail it. But I think you've got enough there that you can now do that image segmentation. You're going to wind up with some problem, which is that space on the side but actually won't give you a problem because there are no myofibrils there. So that will be a cell that won't get converted to myofibrils.
We can also, in the initial simulation, when we're making the initial conditions, fill that in with ECM,
Right.
so that nothing's
That
mixed
works too. Either way. Okay, so why don't I let you guys try that? Any other questions I can answer at the moment? But I think that'll get you a pretty long way towards where you want to go. And it's not very pretty. It's sort of ugly coding, but and TJ is probably sitting there grinning because I give these speeches about not doing what I've just done. Because I always say you should plan your models in great detail before you even write a single line of Python. And here we are coding without thinking. And so TJ is laughing that I don't follow my own rules. But I hope that's helpful. So why don't if you can, actually we're already. What time did we say we were going to have our check-in?
I think 1.
Okay, so 1 o'clock. Okay, so can I ask? If are you? Is it okay for you guys to go and check to try this out?
Yep.
Dr. Glacier, I also wanted to meet with you separately, just like for a project outside the hackathon, but I didn't want to like interfere with time that all the groups needed for help with the hackathon. Is there a time that works for you that I could do that?
Well, I'm available pretty much, but why don't you go and work with the group to see whether you can get this part of it working, and then later this afternoon I'd be happy to meet. The one we could go into. It's not 100% sure about going into a breakout. We'll figure out a way to do that. But this afternoon I'll be available all day, so I'm happy to do that.
Okay, thank you.
Thank you.
Okay.
Thanks, James. Bye for now.
Thank you. Hey, TJ, did you want Tin? Did you want it? I'm sorry, it's a teen. How do you? Oh, well. TJ, what do you think? I sort of made a mess.
About their project?
I mean, it should be possible, given that they've got a cellular automaton version that works. Or probably it's NetLogo. My guess is that's a NetLogo project.
Yeah, looks cool. I'm excited to see what they do.
The pain is going to be doing 2.5D.
Yeah, I don't know. There's a part of me that's inclined to, well, I don't know. I mean, because you're neglecting just about everything that goes on orthogonally to the the plane of the simulation. I'm almost inclined to recast it in terms strictly in 2D. And just
the trick then is how do you get the fields to are you willing to go help somebody, by the way? Because poor Vignesh is sitting by himself.
Sure.
Or did you want to?
Well, I've been working on finishing up my I got a little inspired to add to my talk for today.
Oh, okay.
So I've been finishing those in the background.
Could I ask you just to go in and check on Vignesh? The yeast colony people and Vignesh need somebody to come and give them some attention. Everybody else seems to have help. So could I ask you to check those two groups? They may be fine, in which case you can come right back, but I need to run. I'll be back in a second. Okay.
Okay.
Jim, I have a question.
Okay.
Okay, so I'm having problems with one, the steering panel, and then two, the dimensions of screenshots that I'm trying to save. I can't get it to save anything other than square screenshots at the moment.
You mean it's like 600 by 600 pixel, as opposed to you want to do some other shape?
Yeah, preferably.
I'm not sure you can do. I know that the parameters are in there. I just have no idea if it will save it that way. If these are screenshots too. Why do you want them not to be square?
Because the system we're dealing with is like very long and thin.
Okay, so it looks like it's ignoring when it says, do you want it to be 600 by 600? It's ignoring if it's not square. That may well be embedded in CompuCell. I think, is there any way around that?
I mean, obviously it's not like disastrous if we can't fix that problem. The only reason that I wanted to do it is so that potentially when we come to talk about what we've done later, it would be nice to be able to make like little videos of what we've done.
Right, right. Wow, so let's see. I've been having a lot of trouble just getting it to do screenshots the way it's supposed to. There's just something really quirky happened. I
mean, we could move on to we could try the other problem and see if that's more tractable.
Okay, well, just a minute. I had a CompuCell running, and I just real quickly tried to get to do screenshots. Let me see if it works for me. Wade through all my folders. $12.35. Just looks like it just worked for me.
By just changing the parameters in the like settings.
Yeah, so where's my Zoom? Nah, that's not the right one. So let's see if I can find out where my, oh, there we are. So I have this simulation. I hope you can see my simulation. So I got set it to 600 by 100. And now here's my output directory. You see it
just worked fine. Is it likely to be different, do you think, on a Mac versus Windows?
It's entirely possible. And the one thing that's absolutely a killer is anything that has to do with graphic or files when you go from platform to platform. Let's see. So when you do this and bring up this window, any change you make here will persist for this particular simulation, but will be forgotten if you don't either stop the simulation or let it run to end. Okay. So one possibility is it's doing it, but it's just not remembering it from run to run. Now let me try one experiment. So this simulation here is still running, I think. Yeah, it is. Let's see if I do. So I just make it long the other direction. And it takes it a while to learn this. I don't know why. And I hit run again. Unfortunately, restarted. Nope, didn't take that change. Am I in the right folder? No, no, it wasn't. There we go. Nope, didn't take it. So I cannot tell if this a Mac problem that you can't change it. I will tell you that if you want to make a movie, you can fix it when you make the movie. You could crop the images.
The problem being though is at the moment it's not even just making like a really small thing. It's like it's already cropping it's taking a square of the middle of my simulation. It's not even.
Oh, so it's not even getting the whole window.
Yeah. Because otherwise I could do it in the movie making process.
So that one's okay for me. I don't know why. Okay, well, I'll put in a bug report. I know that there are issues with saving the configuration, and it's possible that what's being saved is, well, first of all, that it's just not properly saving it at the right time, the different window dimensions. It's also possible that the reason you're only getting the middle of the window is because it thinks it's supposed to have a zoomed window. So
okay.
if I'm saving this window here, if I'm running a simulation, I'm saving this window and I do this to it, it changes what it saves.
Okay.
It'll just change this little piece that's visible. It'll only save the piece that's visible. So, you know, the old trick of using an R in the graph to reset the view. But now this is where the bug comes in about, is this going to save the fact that I changed this window? It's supposed to. If I hit stop and run again, it should come back with the windows laid out exactly the same. It worked.
Okay.
But it was hitting the stop button that forced it to save that configuration.
Yeah. Okay. So that might help. That might work. Okay. So then can I go to the other problem with this steering panel?
Real one. Okay.
I mean, I think I might have just coded the steering panel in wrong. If it's okay, I will share my screen.
Okay.
And it's going to be super weird and confusing because, as I think you've noticed, I'm in this room twice. And it's because I have a lack of screen ability. So I'm on my iPad, and if I want to share my screen, I have to also be on my computer. So let's share. Okay. So if I run, I get a steering panel up, and that's fine. But as soon as I click on it, it just goes to like one value and then stays at this value, and I can't seem to like interact with it in any way. And so the way that it's coded in is I thought the way that it had been done in the cell migration tutorial. But I don't know if there's anything that I need to do in terms of, I've got the steering steppable and then I've got my kind of normal steppable. I don't know if I need to, yeah, I'm not sure what I'm supposed to do. Switch min, val, and max. Oh, yeah, okay.
TJ is quick.
That's embarrassing.
He just scanned 30 lines of code and found that you just had a sign wrong.
Yeah. Okay, I'm gonna see if that's made any difference. Okay, well, that's embarrassing. That's amazing. Thank you. Okay, I can stop sharing that. That's perfect. That fixed my problem. Okay, I'm going to head back to my breakout room. Thank you so much for your help.
Would you wait a second? Wait, we got TJ here. Quick question for TJ. Is there any known problems with saving non-square screenshots on a Mac?
No, I was actually gonna see, Kato, would you be willing to like kind of walk through this process with me real quick so we can see what the problem might be?
Yeah, okay.
Go get your screen share going again.
Oh, yeah.
It's complicated.
It's more complicated than you'd have thought. Like I've got 8 billion things running.
I think the last time we did a screen share, I think that you pulled one screen in front of your camera for me to see what you were doing.
Yeah, I've upscaled on the tech of my of what I'm doing now. But
Yeah,
it does
we
mean that I'm in
definitely
this
upgraded.
meeting twice.
Okay.
Okay. So okay, so I'm just going to start it here. I'm finding this weird thing where to get things saved, I do one single screenshot and then I can run it. And at the moment it's saving every 100. And then the place it's saving to is this brilliantly named file. And it's saving as you'd want, but it's saving these like slightly weird zoomed in square things.
Yeah, so it's a square window. Can you go to your settings in Player?
Yeah, so if I go to my settings in the player, I have it set up at something sensible and it's just not doing it.
What are the dimensions of your lattice?
What are the what of my lattice?
The dimensions.
It's 100 by 800.
Okay.
Can you go back to Player? Go back. That's Player. In that window, your cell field, the big black window with your cells growing in it. Yeah, that one. Click on that. Type an R. It did nothing.
Yeah, it didn't do anything. So I can like resize it and do an.
That's so the R doesn't work. R should make that figure pretty much fill the window. You're still getting the same.
It does work if, yeah, so if I zoom in, it makes it zoom out again. So this is me zooming in manually, and then I press R and it does that. So I think it must be fitting it again to this 600 by 600 box or something.
It shouldn't be, but it's clearly doing something strange. I mean, Player shouldn't be looking at that 600 by 200 or whatever it is in your settings at all. It doesn't really care what those numbers are. It's just how it's going to output the image.
Let's try this. So in your player settings, let's change the image, the screenshot resolution to 600 by 600, or yeah, that's fine.
Back to default.
Yeah, and let's see what that does.
I don't know. Can I turn this off? I don't know what it does.
Nobody does. And that's the VTK save, isn't it, TJ?
Yes.
Okay. Well, CompuCell's just crashed.
Possible the VTK one should be all right. So you might even if the pixel image isn't all right, you may still be able to use the VTK. So we should check if it's rendered properly.
That we could do probably quite easily. I don't know what a VTK file is, and clearly my computer doesn't either.
Yeah, this would.
Open it with a text editor like Notepad. I think this version is a plain text file. Yeah. So somewhere in there, the dimensions at the very top are the dimensions. Yeah.
Okay.
So it says it's 800 by 100. So the VTK looks okay. Well, without actually visualizing it, it at least got the right dimension. So the VTK looks okay.
Okay. So maybe I could find some way of changing the VTK file into something that is usable. Okay.
Well, CompuCell will let you read those back in and render them.
Okay.
Although I always forget how to do it, but you could definitely, it can be done. Oh, so there was a specific question. Sorry, Suvik.
Can you hear me?
Yes.
Okay, so my question is basically in the external potential plugin. So if I use the center of mass based algorithm, so what will be the difference? So in Giuliano, he took pixel based. So what's the difference?
Well, so if you apply a force to a surface, it's not the same as applying a force to the center of mass of the cell. So my suggestion would be trying it both ways, and you'll see very dramatically what the difference is in the way the cells move.
So and one question, so this external potential, will it directly add to the Hamiltonian for the Monte Carlo flipping?
It effectively applies a force in the direction of the potential to the surface or of the cell or to the center of mass of the cell.
Okay, and let's say I have a Hamiltonian which basically makes the cell polar, like some Hamiltonian like n dot r or something. N is the polarity vector, and then r is some displacement vector. So then can I include that term using this external potential?
Hold on. So TJ, maybe I should make you session leader so I could leave the meeting and then go with Suvik to his room. So you can keep working with Kato.
Okay.
I just because the problem. Okay. And Vignesh, did you have something you need? No. Okay. So let me go into the. I don't know why we're getting an echo here. TJ, I'm gonna make you a host for the moment, okay? Okay, so then, Suvik, let's go back to your breakout room.
Okay.
Actually, in 10 minutes, we're supposed to have our check-in, but
yeah, I think it will be done within 10 minutes.
Okay, so I'll join your.
Okay.
Okay, so were these being generated with the different screenshot resolution?
Good. Yeah.
And still.
And it's still doing something slightly weird. Oh, it's gone back. Okay. Okay. Let's try that again then. So I'm going to step it. I'm going to try and take a screenshot. I'm going to go to my preferences. I'm going to try and change it again now. And then I'm going to run it and see what happens. And then where am I looking for? Yeah, it seems to just really like the center of this field.
Let's go back to
double click on that image. Open up that image in something other than the preview. Okay, just want to make sure it's not the preview that was clipping it.
Yeah.
Okay.
You mean this thumbnail?
Yeah.
Yeah.
Okay, here's something. TJ, should we try to reload the VTKs and see if they come up in player with the right resolution?
Yeah, that's not a bad idea.
Okay.
So let's see. So Kato, so go back to player. I don't know if I remember how to do this.
Oh, it says open lattice description summary file.
Yep, open that guy.
Yeah, what this will do, Kato, is it'll set up the simulation that you just executed in player as if you were executing it again, except you're just replaying something that's already been done. So you
Okay,
can
so is this the right one?
Yes.
Yeah, that should be, yeah. Hit open. Just gonna, it's supposed to just reload all those images. You can close, I don't know how you can even have that guy open there.
So do I press play or?
Yes, just like
Yeah.
you would interact with the normal simulation.
Yeah, there we go.
Oh, wow, okay. Okay.
Okay, it's
So
not
that-
clipped, but it doesn't have the right aspect ratio, right?
So which one was this that it was saving? So
That's a good-
maybe this is the one that was saved with, okay, so I'm gonna try and open a different one that I think was saved in the right aspect ratio.
Okay.
I've saved so many of these things.
Oh yeah.
I can't remember which one of these is gonna be a good one. Okay.
If you know what directory that is, you can go and open one of those VTKs with your editor and just see, you have to do it from the operating system and just look at the top and see what it says, the resolution.
Oh
of the
yeah,
file.
that's a good point. I can do that.
Okay, so that says it's 800 by 100.
Okay.
So that's definitely got a non-1-to-1 aspect ratio. So this looks like a Mac bug.
This is my favorite.
Now, if you had, so this image here, if you had, if your PNGs look like this, it'd be okay because it's easy enough. And there's all kinds of automated tools to crop a PNG stack and then make a movie out of the crop stack. And that would be easy to fix. The problem is your PNGs are totally, not only are they wrong, they're unusable. Right? Yeah. There's basically nothing there at all.
Yeah.
So the obvious solution is to go buy a PC.
Okay, thanks.
I know.
Yeah. Well, okay. So I mean, I am tempted to give up on this for now. It just means that I'm not going to easily be able to make nice videos. I mean, yeah.
Wait, TJ, isn't there a Python function in CompuCell for saving a screenshot or saving a window that's separate from the player controls?
Yeah, it's part of the Python API. So Kato, for now, you can set up your simulations and do all of your modeling stuff. And there are some other ways that should be independent of Mac to generate these figures. I don't know exactly what the problem is because last I checked, we've not had this problem on Windows or on Linux. So I'm not exactly sure how to go about fixing it for now. But if you absolutely needed to generate some figures, like, in the very near future, there are other ways that we could do that I'd be happy to help you set up.
Okay, cool. Thank you. I'll have it keep saving the VTKs then. I mean, it was mainly so that if anything came of this hackathon, like during the demonstrations that potentially we'll be doing later today, I could show what we've done. And actually I could do that by sharing screen and just using the VTKs. So
so just be mindful of that the VTKs can take up a lot of storage. So yeah.
It's an ASCII format image. It's not even a binary image. Hey, Cater, can you put your email in the chat? I will see if I can find a better tool that would let you render movies from the VTKs. I know there's tools out there. I just can't remember what they are. Okay.
I gotta step out for a minute.
Okay, cool. Thank you very much. I'll head back to my breakout room.
Sure.
At least, yeah, we got one of the problems sorted.
Yeah. You're at UCL. My daughter's at UCL.
No way.
Yep. She's in anthropology.
Okay, that's exciting.
I don't think she's actually been on campus more than about 10 minutes in the last year, but I mean, it's probably par for the course.
Yeah, I'm in a similar position.
Yeah.
Undergrad, postgrad?
Pardon?
Is she doing undergrad or postgrad?
No, she's a grad student. She's finishing her PhD. She's supposed to finish this year, but she was supposed to have been going to Turkmenistan and Afghanistan, not Afghanistan, Turkmenistan and Uzbekistan to study rugs. But you can't go anywhere, so she's kind of stuck. Anyway, okay.
Yeah.
I think I'm going to drop off. I will send you an email if I find anything to do with VTKs. Cool.
Perfect. Thank you.
Bye. Sure.
Well, everybody, I guess I've worked with a few people. Some people are still busy working, so I don't want to interrupt people too much. I just really wanted to have this time available to check in with people. How is it going? Maybe we just run down our group list again and see if we can get quick updates from people. Giuliano is available. TJ is going to be giving a talk in a few minutes. I don't know who else is available to help out, but we'll do our best to support people. Let's give people just a minute or two to rejoin. In particular, if you need specific help, I encourage you to. I was talking, Giuliano. I was talking to Vidyash, and he was looking for some help using the external potential plugin to do directed motion, and I didn't know if you might be able to help with that a little bit later.
Yeah, I should be able to.
Okay. Give it one more minute and then assume people are busy doing things. I don't want to take time away from your projects. TJ, are you there? You may have stepped out. Okay, so why don't we do just a quick update? How is the EMT group doing? They look like they're all still busy working, so maybe they're not. So they're not here. How are our lateral line project going?
So
Is there anybody?
It's going okay. Yeah, I'm
Okay.
here. I'm here.
Okay.
Yeah, we are trying to do kind of two models where I'm looking at kind of modeling the motion from the top, and then we're also doing a side view. I mean, at the moment we're just using external potential to get kind of movement, but we have some cells moving along. Yeah, it's going okay.
Okay. So I know you were having some trouble with saving the data sets. Did I know Priyam could only join us for a short amount of time. Was she able to talk to you about how to do rosettes at all?
Well, yeah, we did have a bit of a discussion about that, using both the contact the contact tensions and the potentially adding in some links to do that as well.
Yeah.
So yeah, I think that's what we'll try and have a look at next.
He did suggest that using the features for not just necessarily an internal link that defines the length, but just the length constraint itself can help make cells longer. Well, one of the things actually I was playing with the model that Cato made, and I realized already is a little bit, the outcome is different from what I expected. So we started with the column cells.
Yes.
And in the NetLogo model, what I had was I changed the strength with which the springs work in one domain versus the other. And where it was stronger, you made rosettes more easily. In this case, it doesn't translate to the exact same thing when you change the relative contact. You get more of a Steinberg experiment happening where it determines what engulfs what rather than determining which domain is going to be more constricted versus. So I think we have to think a little bit about that and potentially see some differences by putting FPP links in it.
Right. Well, that logo structure is much more like an FPP link. It's like a contact energy.
Yes. So I think that's what.
So
maybe we'll try that next. And Abhishek, do you want to say something? I don't know whether you're there.
Yeah. So I used FPP links and can I just share my screen to just show?
Yes, you should be able to share.
Oh, okay. Can you see my screen now?
Yes.
Okay. Yeah. So these are two in 2 layers. I use these cells. I mean, this is from a side view where the red cells are FGF dependent and blue cells are wind dependent. And I used FPP links to get the red cells to actually form rosettes or become more elongated in an apical basal manner. But some of the problems, I mean, some of the cells are getting a bit elongated, but some of the cells, blue cells are actually moving on top of one another, although I mean, is it something to
That's
do
all
with?
right. That's all right.
Okay, so these cells here, they look elongated,
Yeah.
but can you just see? I mean,
But they're not forming stable. Oh, they are forming some aggregates. So I guess the trailing.
so I'm using FPP links for these. Sorry, this is something which keeps occurring. So any thoughts about these?
Well, I'm not sure what you're trying to do, so.
So I'm trying to get these red cells to come together to form rosettes, or actually come together and then elongate. So which they are doing. The target distance is actually reduced, and but the blue cells are so they are supposed to move at a higher speed than the red cells. I'm using just external potential for these cells rather than chemotaxis. So status.
So maybe after the check-in we could work more detailed together. But there are a couple of things I'd say. First, using the elongation plugin, you can't get the cells to elongate very much because there's a limit to how elongated you could get a cell. If you want very elongated cells, you have to use compartmental cells.
Okay. I'm not using any elongation.
The second thing.
Okay.
Sorry.
So I'm using the FPP plugin. I'm not using an elongation or length constraint.
Okay. So then, but you don't have compartmental cells. Is that right?
No, I don't have compartmental cells.
So then you won't get. Then your cells will be isotropic. You're not going to get any cell elongation.
Okay. So I need to create these compartmental cells.
Yeah.
Go ahead.
I think that what I'm realizing as we play with this version is that in the side view, it is very hard to get a situation where they will rise to form clusters with any kind of geometry that resembles a rosette on its own. It's more likely to make a multi-layered thing in which context a rosette is a meaningless thing in side view, because the rosette is defined in a slightly different way when you're looking from the side view. So I think we may, from the side view, learn less if we don't implement the compartmentalized cell version. So, looking from the top view, we can see things happening which are potentially interesting. But from the side view, where it's an asymmetric situation, I think you do need the compartmentalized cells. Otherwise, the asymmetry doesn't exist to create the kind of geometry one is looking for.
Well, I think I'll have to spend some time with you looking at the details of how the simulation, what you expect to see. But in general, if you're going to get something like a rosette, there are a couple of things. One, you're not going to be able to use the automatic creation of links. You're going to have to create the links by hand because you're going to need very specific geometries. And also rosettes are intrinsically asymmetrical. The cells have to be polarized to get a rosette.
Right. That's exactly.
And so that means you're going to have to either define a polarization vector on the cell, or you're going to have to use compartmental cells. And and the other thing is you're going to have to make the cells bigger. Although of course, early on, you may want them small so it runs fast. Because you're not going to have enough voxels essentially to be able to build the cell shapes that you want. But
bigger cells is a good idea.
But I would encourage you strongly to look at I would encourage you strongly to look at Priam's papers on apical constriction, a recent one, and then Julio's paper on ectopic somites, because both of those use polarized cells with apical constriction to get rosette-like phenomena. Now, I don't know in this case what's happening in this particular example, because I haven't seen the video. I'm not sure which video it's supposed to be looking like, so I don't know. But I mean, but the basic structurally, you see the model works, which is good. You're getting migration, which is good. But to think about actually how to get this reorganization within these clusters of cells, that's something we'll have to work on a little later. And I want to talk about it more, but I also want to make sure we get through everybody quickly, so that we could, and then we'll come. But now we know that there's an issue. Giuliano probably could help with that. Unfortunately, Giulio said he was going to be on the call, but I don't see him. Maybe Giuliano, you could send an invite to Giulio again, but we'll do our best to help you out with that.
Thanks.
But at least, but it looks like you've made some progress, which is good.
Yeah.
Let's just go through the list. Is David here?
So I was discussing with my group about what the best way to model our network, and one of the issues that came up. We were trying to debate: should we use a Boolean model or should we use an ODE? Because what I have right now is I'm mostly interested in is basically using an ODE model to get a more accurate view. We feel it's more accurate in terms of simulating our cell signaling pathway.
Right.
So we were kind of like using Tellurium, to sort of like, model our reactions. And we're trying to see if we can extrapolate those simple reaction pathways to a much more complicated reaction pathway of 500 or more, or 500 or more reactions. So that's pretty much what we're trying to figure out. It took us a while to like come up to, we're debating between, okay, should we use Mabos for Boolean or should we combine both of them and try and use both of them at the same time? Well, pretty much that's where we are right now.
Well, I think you definitely would rather not run 500 ODEs simultaneously if you don't have to.
Yes.
So I'd keep, if the gene regulatory networks, then probably the Boolean models work pretty well. If you've got protein accumulating on the cell membrane, then you probably want that part to be an ODE, so you have a graded expression. But those are tricky. But are you having any issues with the computationally? Is the simulation structure working, or you're talking about modeling ideas mostly and haven't started coding, which is fine. Just to catch up.
We've been doing some coding, but we have been doing some coding, but we got to a point where we were like, okay, what do we focus on now? Do we go the qualitative route and focus on the Boolean, or do we stick with the ODE that we're doing? So I'm guessing if we do both, it will be too complicated. It will be way too complicated. So we're just like, okay, let's stick with the ODE now. Then whatever model that we need to approximate, then we might just stick with. I'll just figure out sticking with a Boolean model in that situation.
Okay, well, you were working with Tarun, right? So
yes.
He
Tarun and
knows.
Stefan, yeah.
Okay, so Tarun is certainly knows this kind of modeling very well. So.
Yes, he's very.
Is there anything?
Yes,
anything else? If there's any expertise in the room that can contribute, you should please speak up. I'm not the only. There are a lot of people who know a lot of things in the room besides me. So please.
Yeah, I'm kind of new to this, so I'm kind of new to this, so it's kind of like it's kind of been like a learning process to me because I mostly use a different software completely. So, and when I got into this class, I was thinking, they have so many tools. Let me see if that is another way. There's another way besides what I'm using right now to be able to model these pathways.
Right. Well, MapBus is very good. So even if you stick with your Boolean models, going into MapBus is a nice way to do it.
Sure.
Okay.
Excuse me, Professor
Okay.
Glazer, please, can I
Yes.
just ask a short question? When mixing ODEs with logic networks, there's one principle you said that if gene regulatory networks, then probably it's logic and it's protein accumulating its ODEs. But are there other principles too, like, I don't know, ODE logical switches switching on and off whole blocks of ODEs or something, or vice versa, or the top level logical, bottom level ODEs, or vice versa? Or are there rules like this?
Well, I remember when the Boolean models first were introduced, I was very skeptical that they'd be useful because I thought they were, everything we do is this oversimplification. And they were especially used in modeling Drosophila genetics. And after all, gene transcription, well, there's some things that change the rate of transcription, but in general, gene transcription is mostly Boolean. You're either transcribing or not. And so what matters is the fraction of the time that the gene is being transcribed. And of course, if the gene turns on and off frequently, then that can change things. When you go further downstream, then you get more graded expression.
I see.
But I don't have a good answer for you. I don't think there is really any principle that tells you. I mean, that one clue is to look at it in the experiment and ask the question: do you see a graded pattern or not? If the gene product is either present at a high level or not present, then a Boolean model is likely to work very well. If you see cells with very different continuous gradation of the level, then probably it's important to include that. I come from a background where we by default use reaction kinetic, what you call ODE models. But in fact, ODE models require a lot more parameters than for the same network, a lot more parameters than a Boolean model does. And if you don't know what those parameters are, you may be introducing complexity without gaining very much. And so I think it's important to be able to go back and forth and explore that. I wish there were a simple answer to that question. Other people may have strong opinions, but I don't have a simple answer.
Thank you.
Yeah, so for my model, we have just very few parameters. We have the reaction weight, we have the activation factors, and just very few time constants. But we don't have, like, in terms of just basic, initial reaction and final reaction. I'm sorry, initial concentration and final concentrations. That's pretty much it with the Hill coefficient. So I didn't know whether that was enough, or we should just stick with a Boolean that just gives us just a rough approximate, because the model I'm using in my research is a hybrid model of both the ODE and the Boolean, because the Boolean is more scalable. Because we can run 500 reactions. So that's why we just combine with the bomb to just give us a better understanding of it.
Right.
Yeah,
well, I would encourage you to begin with to re-implement the model you have.
Okay.
And make sure that it gives you the same answers using the different solvers.
That's exactly that's one reason why I enrolled in it. So if it will give us the same or something similar, then at least we know we're on the right path.
Yeah. So I think that's sensible. I'd start with if you've written your Boolean model in something else, import it to MapBoss and see that you get the same result. If you've written the ODE models in something else, pull them into antimony and make sure you get the same result.
Okay.
It's before you once you've done that, then you can play. But it's not an easy problem. You've got a very complex model, an impressive one, but complex. Okay, so let's see who is next. Farnoosh?
Yes, I'm here. May I share my screen?
Sure.
So sorry. Yes, this one. I'll just keep it very short. In fact, this is the cartoon of the model that we have in mind. As I explained earlier, we try to make a very simple, basic model. What we have is two state for the cancer cells, 2 or 3 state. We are discussing this still, and also for the T cell, we have at the first stage 2 state. And our strategy, now we are 6 person in the group, so the strategy was to divide in 2 different groups. We are now in one group, we are working on the cancer part, so we model the cancer growth, and the idea is that because the time scale of the immune response that we are modeling is much shorter than the time scale of the tumor growth, the idea is that to try to have a stable tumor with the stable size, and then we are now working on that, and then we will model the transition to the dying state. And the other group is working on the T cell part. They consider that they have now rigid cancer, and then they try to model the T cell part, the T cell dynamics. For the cancer growth, we are building a model very similar to what we had in the exercises for the avascular tumor. So we just changed it a little bit, and I think now we don't have any issue in this part, but maybe Polly from the T cell group has something to say, because as far as I understood, they need some help. Polly, am I right?
Yeah, it would be nice for me to kind of explain where I spent the last hour or so. So maybe can I share screen?
Yeah. Please.
Thank you. So I was kind of adapting the multi-cell migration in order to kind of specify where our effector T cells would initially be kind of randomly scattered, because most of the simulation has been done where we either have a blob or like a square bunch of cells stuck together, but really we want our T cells to be scattered. So right now I'm using sort of a random number generator, but I do have 2 main concerns, and maybe one of them is asking for a hint. My concern is what happens when cells overlap like this, because I think in reality cells shouldn't be kind of sitting on top of each other, and I am a little worried about like what that would do to our model. And second, is there actually an easier way to implement random scattering of cells? So that's kind of where.
So this is something that may come up repeatedly with the muscle regeneration people. If there's anybody from muscle regeneration who wanted to talk, that's fine. I didn't mean to skip you over. So one of the things that you can do, first, if the cells overlap partially, there's no problem. They will, as soon as you start running it, they will simply reorganize to fill the space properly. The only thing you have to worry about is if you completely overwrite a cell. So if you create a cell that completely clobbers another cell, then what happens if you run that simulation?
Well, the simulation doesn't really matter because I haven't coded anything else that would make sense. So if I decide to run it, like it's just random interactions. So
right. But you see the cells, so the contact energies aren't defined. But the cells are designed so that if they overlap, they'll move apart from each other.
Okay. So that means I really should kind of form a ring and push outward for the T cell. Because at first I was like, can I just do uniform random and just have T cells even in where the cancer cells are?
So you can do that too. I mean, typically what I do is I pick my random numbers from my place. I look at the location and I ask the question, is there a cell there already?
I see.
And if there is, I throw the number away and I pick another random location.
Okay, so probably I will do something like this where maybe I'll write a class to kind of omit T cells and make sure they don't go near the cancer cells initially.
So you could always do, I mean, you could do something where you pick your random number and you say it has to be outside of some circle. So you measure the distance from the center of the circle, and you say my initial position has to be x minus x0 squared plus y minus y0 squared greater than something.
All right.
And then you say, okay, at that location, I check, is that location already occupied by a cell? If it is, I throw that number again, I pick another random number, and I loop until I've created as many cells as I need. That would be my way of doing that.
All right, thank you.
Thank you. And what we usually do that, when we usually do that as well, at least we initialize the cells with 1 pixel, but set their target volume to be what we want, and they will grow to that over the next couple of MCS. It's gonna look strange for those couple of MCS, but
okay, so there should be no problem if they're initially 1 pixel then.
No, as long as you set the target volume and the lambda volume appropriately.
Got it.
Then they grow and fill. In fact, with the muscle people, I was proposing them to do exactly that, to do some image segmentation.
Got it. I will try it then. Thank you.
Okay. Janosch?
Yes, thank you. With Kona, we did the conceptualization of our model. We defined what kind of cells, what kind of fields we will have, what kind of interactions they will have. And I think in the end, with the help of Gilberto, we got some good ideas how to implement it. And in the next work session, we start the coding part.
Okay, if you want to show anything or discuss, that's fine. Otherwise, let me just if you need help.
I think in the evening final check-in. I think at that time we will have something to show. Now only the concepts we have.
That's fine. If you just to be helpful. Iman?
Yeah. Well, from my side, I have built the first model that I was expected to build during this hackathon day, and most of the input came from Giuliano, and thanks for that. And the way we built the first model was to have 2 components, one healthy ACM and the other one a damaged ACM. So the mechanism that we defined for the generation was based on using the chemical field plugin, and we defined a protease such as trypsin to actually degrade or degenerate the healthy ACM and turn it into a damaged ACM. So in the initial version of the model, trypsin would only target the healthy ACM, right? But now what we are trying to achieve is to define like binding molecules in order to like make a junction between healthy ACM components, and then in trypsin, instead of targeting the main healthy ACM, will target the binding molecules. And based on that, we will define some sort of cartilage tissue being loosed according to loss in like binding molecules. Yeah. So
okay.
Well, that's it pretty much from my side.
That's a lot. Do you need any special help? Is it okay?
Well, actually, so far Giuliano's help was a lot, and I think that's enough for me. Yeah.
Great. Okay, I guess Marco.
Yes. So we share my screen so I can show you.
Please.
What I did until now. Yeah. So thanks to James, I was able to develop a lot the code. Still, there are some errors. I still have to handle the Mabos part here in the steppable. and I think I will ask to TJ for some advice. But thanks to James, I came up with some ideas. So first of all, I introduced 3 cell types in the simulation: quiescent, move, and def. So those 3 cell types, well, the quiescence one is like the base state of the cell. When the cell reaches will reach the extracellular matrix, which I define here. When it reaches the extracellular matrix, it will trigger one of the correspondent nodes of the MABOS network. Then MABOS will operate the possible trajectories, and according to the output, it will trigger a certain behavior. Also, as you can see here, I'm collecting this part here of the code will collect some information from neighbor cells or oxygen or extracellular matrix, and will trigger the correspondent input of the MABOS network. While in this in this steppable, I am linking some MABOS variable. In particular, I'm connecting the phenotype quiescence and the phenotype apoptosis to a cell type. So if the network somehow reaches the apoptosis phenotypes, then my cell type will switch to the death type, and then it will trigger the death of the cells. Same thing with quiescent, and same thing with move. So when a cell is not dying and is not in a quiescent state, it is moving. And then when a cell is moving, basically will follow the gradient of oxygen, and so it will try to escape through the extracellular matrix and so on, so on. So this is what I did until now. And when I will fix the MABOS part, I think I'll be done. I have also to add some nodes to connect other behaviors, but I think I'm in a very good point.
Okay, well, I think for MABOS, TJ's our expert. So, but you of course you come from that community, so you're the other expert. So
yes.
Okay. So okay, great. Let's see quickly, Suvik.
Yeah, hello. Can you hear me?
Please.
Yeah, so right now, till now, I have developed the code for the CC3 code for the confluent cellular monolayer with T cell division and apoptosis. And whenever the area of a cell exceeds it comes closer to a low value, it basically the cell goes away, which is the apoptosis or cell death. And whenever the area that area of a cell basically grows to exceeds a particular value, it will divide using this mitosis random cell orientation. And I also implement the calculation of mean square displacement in the CompuCell 3D, and then I calculate this mean square displacement of the cell, and with different rate of cell division and apoptosis. So I have characterized that thing. So I will like to show that towards the evening session.
Okay, great.
Right now I am working on the polar cells.
Great. I know 2 hours isn't a lot of time to work on these things.
Yeah. So that's why I started working from previous days. So.
Okay. Let's see. Lorenzo, did you have anything you wanted to talk about?
Not really. I think I came here because of the talks, but I don't know if I catch the right time. We are working on the cancer model really with my.
The talks will start soon as we get through our list. So okay. Is there anybody from either we skipped the let's see, did we skip the muscle regeneration group? Are they are they here now? radio sensitivity, anybody? Okay, Vignesh, we went through. Has anybody not checked in who wants to check in? Now's your opportunity to speak up. There are a few people I see who are in the call that I don't recognize. Have they been able to join groups or otherwise been able to work with people? Silence. Okay, so TJ, are you there?
Yes, I'm here, James.
So I guess you've got one more chance for check-in. I will broadcast a message saying that you're TJ, you're ready. Are you ready to give your talk?
Yeah, let's do it.
Why don't you do a local record of yourself? I think you're still the host of the meeting.
Okay. So
if you want to hear TJ's talk, please stay in the main meeting. If not, please rejoin your rooms. Instructors, Jim, Giuliano, and company, please join the breakout rooms and help people as much as you can. Hold on, I'm just gonna give me 1 second. Let me type a written broadcast message to the breakout rooms. And then I'll...
Sure.
Sorry. There's a strange note, slightly strange. Okay.
James, we good to go?
Maybe give people 1 minute to respond to the broadcast.
Okay.
TJ, why don't you turn me back into host for a minute? And the Giuliano and Jim, if you can go and help people in breakouts, that would be great. Thank you. Okay. Good. Take it away, TJ.
All right. Hello again. We're in overtime. It's very exciting. This is the second workshop that I've been a part of at the Biocomplexity Institute, and the hackathon is definitely my favorite part. This is an informal talk and maybe a bit technical for some, depending on your interests and your background. So we're going to keep this really informal. Stop me as you please if things are unclear or if something piques your your interest and your curiosity. We're going to talk a little bit about some very current and very recent work with Multicell, more on the software side and in advanced applications, all revolving around what we collectively refer to as the CC3D Python API. Now, the CC3D Python API seeks to expand the scope of usage for CompuCell into lots of new territory. But the concepts themselves, at least in principle, are quite simple. So you can, imagine, the functions that we've been working with now since at least last weekend. For those of you who joined me for the Python crash course, think of a very simple function, or a very simple object like the iterator that we've been working with when we write things like for cell in self.cell list. You think of the importing that we've done using things like the random function from the random library. This work is about taking CompuCell beyond how we've been using it this week, primarily writing our scripts in Twedit, loading those scripts into Player, executing them interactively. I mean, this is a very nice way of building, developing, prototyping, exploring computational models in multicellular systems. This work seeks to go beyond that and enable a different way of using CompuCell, which is to use it in the same way that we've been using other Python objects, like the cell objects, the cell list, simple Python lists. Want to use CompuCell itself, like something like an interactive Python object. And so the Python API in CompuCell enables that. And what I would like to do today, if I had any goal for these next few minutes together, would be to make you aware that this functionality exists in the first place, if not to provide you with at least a general sense of how this works and how it can be used, and to provide some sort of brief notes on how to use these things, set up a Python-based CompuCell simulation, and some of those particularities. So back to the example of something like a very simple Python function. We've written quite a few this week. Oftentimes Twedit has generated them for us. We have things like our step function and our start function. In a very basic sense, just something like a simple function like what's written here for some def of a function called my function. This function just takes some single argument that's called x, and there are some calculations that you can imagine. You can fill in with your imagination, but just believe me when I say that in those calculations, something generates a variable y, and my function takes the argument of x, does those calculations, and returns y, whatever y is. The Python API allows CompuCell to be used in the same way, in that working from a general Python environment, you could take things like data from, we've had some segmented images that we've seen today with one of the projects, taking experimental images and turning those into cellular distributions in CompuCell. That is one of many potential applications that the Python API is well suited for, and especially for doing very advanced applications like developing workflows that can actually move automatically from, say, something like experimental data generation to experimentally derived simulation configurations and things like that. The Python API enables those sorts of workflows. That's a very advanced example, but you can also think of much simpler examples of doing things like optimization, where you use CompuCell itself as some sort of feedback mechanism in an optimization workflow, and do simple things like parameter calibration, say using something like SciPy's optimization package, or what I would like to do using something like PyTorch, and using artificial intelligence, so turning machine learning on learning simulations that we've written in CompuCell. This can all be set up with the Python API. And one of my favorite things and one of the goals of this project, doing this is actually quite simple in the sense that we can take something that we've been working on in the traditional sort of development workflow with CompuCell. We start with Twedit, we open up our wizard, we generate our simulation, we fill out our steppables, we choose our plugins and configure them. All of this is already, this is well established, with usage in CompuCell. Using CompuCell simulations in a workflow that employs the Python API requires no modifications whatsoever to everything that's generated with those traditional workflows. So you can take a simulation that you may be working on right now, or that you will work on after the hackathon this weekend. You can take everything as it is and then build some stuff around it and actually convert your simulation into something that could be executed in a Python environment, and also plugged into some sort of workflow for doing lots of very advanced things. And so what this looks like, if you were to open this up and say something like, a file explorer on your computer, by now you're probably familiar with this sort of file structure where we have, the CompuCell simulation structure as it's generated by Twedit, with the CC3D file that we load in Twedit and Player for editing and execution respectively. And then our steppable script that we spend a lot of time in, XML, where we specify our plugins, and the main Python script that we tend to not work with very often, but it exists. And then you can actually write a Python script in, say, some other location on your computer, whether it may be at the same level as where your actual simulation scripts are stored, but generate a Python script somewhere else on your computer that can actually load everything as it is, as you were developing it before you even knew that the Python API was a thing. So this requires no modification whatsoever. This is completely plug and play, concerning actually deploying a CompuCell simulation in an advanced application like Python API. Now, I don't want to go through this in detail. This slide, to be completely transparent, is mostly for everyone's reference for those of you who may be interested in it. This is also documented in our Python reference manual. I believe it's the very last chapter. So I don't want to go through this here, but there is some, at least in current CompuCell, there are a couple of particularities with setting up an environment to be able to do this, mostly with just setting environment variables. I'm currently working on eliminating all of this. So my goal is that for the next CompuCell release that will also have this functionality, these steps won't be necessary at all. But for now, there are a couple of environment variables to set, a little bit of appending to the Python path. And then after that, you can write an execution script, like a batch script or a shell script that we'll call the Python script that does whatever it wants to do with a simulation that's executed in Python. Now, the way this works, so you imagine we'd like to write a Python script outside of the files that we've been working with when we write our simulation. Instead, we want to write a Python script that will use our simulation in some sort of way, but in a Python environment, and not necessarily within a steppable script that CompuCell itself is operating. And this all happens with this one class that's distributed in the CompuCell core package. It's called CC3D caller. Now, if you've configured an environment the way that's instructed currently, or will in a way that will just be available by virtue of having CompuCell installed in future releases, this is as simple as writing in a Python script from cc3d.compusellsetup.cc3d caller, and there's a class defined there called cc3d caller. And CC3D caller is a class that wraps the entire execution of a CompuCell simulation. This is effectively doing everything that you do manually when you set up, you load and configure a simulation in Player, except that this is all occurring in some other Python script. You know, and in a very, you know, probably the most basic case, as simple as passing the path to the CC3D file that you would have loaded in Player if you'd run this interactively in Player, and then specifying the frequency at which data is output and some output directory to store things. And it's as simple as that. And then calling this function run on the instance that's created, and that's that. If you have some big, you know, 8-hour simulation and you make this call, then this is a stopping call here, which for those of you who aren't familiar, stopping call means that the software will stop, it'll pause here while this command is executed. This command leads to the execution of the CompuCell simulation. So in this case, you know, this would pause the execution of this script for as long as it takes to actually execute the simulation. And that's it. Import CC3D caller, instantiate it by passing things that are particular to the simulation that you'd like to execute, and then call run on the instance. And that's it. Now, one of the most powerful features about this capability is the ability to pass information from the general Python environment into the simulation, the CompuCell simulation, configure the simulation inside of itself using that past information, and then returning information back once the simulation has been executed. Now, I want to go through this a little bit because this, you know, is, I think, both very powerful and also, you know, an interesting way to look at what we've been doing this week. And so I want to dive into the details of this a little bit. So we got a little bit of terminology that we're going to work with so that we can talk about this, you know, in a comprehensible way. So when we are talking about doing things where we have been this week, we have our steppable script where we write, you know, our class definition for some steppable. We have our start function and our step function. When we're talking about things that are occurring in, you know, inside of the simulation, we'll refer to that as the CC3D space. And then when we talk about things that are occurring where, say, we're working in a Python script outside of the simulation, where, say, we import CC3D caller and we instantiate it and we actually run our simulation, we'll refer to that as the Python space. So that's outside of the simulation space. The Python space will invoke the creation of a simulation that's done by CC3D caller. And when that invocation occurs, things will go on inside the CC3D space. Now, as I said, there is the ability that's built into the Python API to pass things, any Python object, including a dictionary, to pass things from the Python space to the CC3D space when the simulation is created. Now, this is done by just passing something, whatever you'd like to have go into the CompuCell space. This is as simple as passing it to an optional keyword argument called sim_input. Now, you'll notice this wasn't written in the call that we showed before, because this is not something that necessarily has to be done for doing things like execution and clusters and things like that, where you just would say like to run lots of replicas of the same simulation. This is not a necessary step to do something like that. However, it is possible to take something that has been derived from some other sort of, say, aspect of a workflow that you may be developing, something like, you know, experimental, like say digitized data of some image of a cell distribution, you can take that and make that available inside the CC3D space when the simulation is executed by passing it to this keyword argument sim_input. Pedro asks, so basically we don't need the parameter scan feature. Yes, that would be the case. Essentially everything in the XML can be at least changed in Python. Believe we reviewed that during the week. If we haven't, I'm happy to share the docs and do a crash course through that. So everything in the XML can be changed in Python. We'll review it in a little bit, that the XML will soon be optional altogether, and can be purely Python, in which case, yes, everything can be set without the parameter scans. Yeah, Giuliano put a link in the chat for some work that we've done that we'll look at a little bit today, and this leverages the Python API a lot. All right, so now this is what this looks like on both sides of, I guess you could call it a barrier. There's not a barrier, but when we talk about moving information from the Python space to the CC3D space, we can send things from the Python space to the CC3D space through the keyword argument sim_input. Now to get it inside the CC3D space, we use these two operations here. The first one is importing what's called persistent globals, which is a core object of CC3D. This is where most important things are stored. And one of the attributes that's stored on persistent globals is an attribute called input_object. And maybe you guessed it, input object is whatever was passed to sim_input. So if you pass an int here, then that int will be available on persistent globals with the name input_object. In the most general sense, probably something like a dictionary being passed to sim_input, having whatever heterogeneous data you like with some predefined set of keys, and then you can unpack all of that in the CC3D space and use it accordingly. Now going in the opposite direction, want to move information then say out of the CC3D space and back into the Python space when a simulation has finished terminating. There is another object defined on persistent globals that will then be used as sort of one end of the pipe to present information back to the Python space. The name of that object in the CC3D space is called return_object. Now this is something that is intended to be set in the CC3D space, in particular because whatever it's set to will be returned in the Python space. So in the CC3D space, say when finishing up the execution of a simulation, this doesn't necessarily need to occur here, this can occur anywhere, but whatever return object is set to when the simulation terminates, it will be available back in the Python space with this returned object that's returned when calling run on the CC3D caller instance. So when you instantiate a CC3D caller instance and then call run, you will have an object returned back to you. And that object is a dictionary. And the value at the key result will be whatever was assigned to the return object on persistent globals. So you can see the whole throughput here. So passing something into the CC3D space with the sim underscore input keyword argument, getting it here in the CC3D space with the persistent globals input object, sending something back to the Python space using the persistent globals return object, and then retrieving it back in the Python space using the return dictionary with the key result. Now I've left this in here as well. We're not going to do this because I want to be brief and keep it informal and get back to the hackathon. So, but I've left this in here for your reference because I'll make these slides available again. So in the CompuCell distribution, we have lots of demos, as you're probably already aware. One of them actually has a demo that shows how to use this in an advanced application like doing very simple model calibration. So this can be found in the demos subdirectory called callable CC3D. This directory has a few examples of how to use the Python API, say in multi-threaded applications for cluster execution. In this case, this is a demo showing how a CompuCell simulation can be connected to the SciPy optimization package. And all this does is it just determines the lambda value for the chemotaxis plugin that produces some desired displacement due to chemotaxis at a certain number of simulation steps. So you can find that there. There's a script called chemotaxis calibrate.py. Execute that, and you can actually see that this works and works, consistently. And you can go through and actually look at that. I put a couple of, questions here to sort of provoke like exploring this script, in particular, observing how this has been configured to pass information to and from the CC3D space iteratively in such a way that the CompuCell simulation is functioning as a feedback mechanism for which there's then an error function that's then used by SciPy to say minimize the error function to produce some desired simulation output. Got a couple things in the chat. I'm going to check in real quick. Oh, there's a great question. Can you move cells between simulations? I believe it or not, I've not actually tested that. But my guess would be that that would result in an error. But that would be a desirable feature. Because in general, what we would really like to be able to do is to be able to work with those cell objects in more of a general sense, as opposed to them necessarily belonging to a simulation. You could argue that a cell should belong to a simulation, in maybe a strict biological sense, that how could a cell from a simulation not exist without the simulation? On the other hand, there are lots of other aspects that are more computational, and we'll have an example that maybe will highlight this. I would say that in some senses that might almost be a necessary feature when, say, doing multi-simulation simulations, say modeling things like migration from one location to another. Now, this is not necessary to do because it's certainly possible to take the data from a cell and then just recreate that in some other simulation. So that maybe not a necessary feature. We backpedal on that, but it would certainly be a cool one. And then Jim says the return, is a Python object. So yeah, it can be a list. Anything that, anything. Of course, there are issues when you're using multi-threading about, whether or not an instance can be serialized. Not everything in CompuCell currently supports serialization and deserialization, but of course, that's just, a matter of work to make those features available as well. So we did this, as Giuliano already pointed out, and again, he provided a link in the chat to actually be able to find this project and see it. We use this extensively. Well, we continue to use it extensively. But one very good example of using this would be in the work that we did on developing the viral infection framework for doing viral infection and immune response modeling. Again, we talked about this, I think, a couple of times this week, but let's think about this in more terms of computing. So this parameter scan did 10 simulation replicas, and that's for each of these little boxes. Now, these simulations took about 15 minutes per simulation on my tower. That is a long time to execute, one after another. Whereas wrapping the entire CompuCell simulation in CC3D Caller and then executing it using multi-threading on IU's supercomputers, we were able to do this in a workday. And that's, necessary for doing this sort of work. We work with stochastic models, as this and many, many other works have shown. Parameter sets can generate lots of variability, even to the extent of producing different terminal configurations. And it's extremely important to be able to generate lots of replicas and to do them, do them efficiently, leveraging like every core at your disposal. And the Python API makes this just a couple of lines of code away from being able to do that. So this essentially takes CompuCell simulation execution and brings it to the level of using something like Python's multi-threading library. And in fact, there's a demo of using the Python multi-threading library with CompuCell. It's as straightforward as I could really hope for. Now, the last bits that I have here are a little bit more for future vision. I was expecting that maybe I would have, with this topic, attracted more of the programming inclined in our hackathon. So I thought that I would take advantage of that and tell all of my colleagues what I've been up to and what my vision is for some of the computing details of CompuCell, and also show some of you who might be interested in some of these details, sort of the current and future directions of CompuCell on the modeling and computing side. So something that we, at least I, became very interested in when working on that viral infection framework was thinking of new ways to use the steppable itself. In that when we use the steppable and all of the nice functionality that's defined on it for getting the cell inventory and automatically having access to the dimensions of the simulation, these are all very nice features. And we write our model implementations in these steppables, and I think the motivation has been because it's easy to provide all that functionality and make that available on a class. But something else that we do when we make our model implementations in the form of steppables is that essentially we're encapsulating them and encapsulating them in an executable Python class that, aside from the actual details of the model implementation, are not necessarily particular to the simulation per se. And when I say that, what I mean is that some of the model implementation details of a particular model may depend on the existence of certain things, like the existence of fields or cell types that have been declared. But this is very much in line with something like the dependencies of the execution of any other thing. Essentially what I suppose the way that I've come to think about these steppables in this sort of context is that the steppables present a way of actually taking a model and encapsulating it in something executable that is modular and shareable. And here's an example of this. This is something that I grabbed a screenshot of from the GitHub repository that Giuliano shared a link to. This is in the Python script that we really didn't spend much time on this week. The one that earlier in the talk, we talked about the steppables Python script, and then the main Python steppable script that we really haven't done much with this week. This is from that Python script where the steppables are actually being imported into this script, instantiated, and then they're registered with CompuCell. This is where the business occurs to tell CompuCell to execute the steppable as part of the simulation. And what you'll notice is going on here is that other things are happening with this particular steppable called cell initializer steppable. Other things are happening with it besides what you'll see Twetic generate, which is to import it, to instantiate it, and to register it. In this case, some very simple operations of setting a couple of defined attributes on the steppable. It may not seem like much, except that all of the steppables in this particular library are all configured to understand that as specifying the discretization of this simulation so that it's not necessary to go through and adjust all of the implementation in the steppable script itself. The steppables have all been written here to understand that when these attributes are set, the model parameters for this model implementation are scaled accordingly to these physical units. And it's possible to do this with other aspects of steppables. And if you go to that repository, you'll notice this, that maybe it's obvious, but it's also possible to then make model parameters settable, or say define other aspects of the interface of your steppable in such a way that it can be connected with other steppables. It can be designed to interact with other steppables according to whatever information is relevant to the model implementation. And so, the steppables provide a really nice way to take a model and make it reusable in lots of different applications. I always think of if you're interested in doing lots of intracellular modeling and then applying that in multicellular contexts, then it's not much work to take an ODE model and say instantiate an instance of it in every cell of a particular type name. And this is something that can be readily packaged as a steppable and made publicly available or injected into lots of different simulations. So if you have a model of signaling pathways with, say, apoptosis, probably that can be packaged to be used in lots of different simulations and probably in lots of different applications. So this is something that could be prepackaged and, say, submitted along with a publication as supplementary materials to see your work propagate and contribute to the development of lots of complicated computational models. Paul asked, can we write global parameters on this level? Yeah, a couple of ways. So the shared steppable dictionary, that's one way to make information available across all steppables. And then, of course, you can write module level variables as well. So we've done this a couple of times where we've gone to the very top of our steppable script, above our steppables and instantiated, floats or ints or whatever. But again, at the level of that module and at the same level that the steppables are defined. So it's certainly possible to do that. And of course, that's all readable and writable when that Python steppable script is imported into something else. In the case of multiple files with steppables, yeah, so a particularity about the shared steppable dictionary is that is a dictionary that is shared among all steppables that have been registered with the CompuCell simulation. In which case, if you were to import steppables from a whole array of Python scripts, each of those that's registered, irrespective of what script they were imported from, they will all have the same shared steppable vars dictionary. So, I mean, in that case, the best way to share, say, a global model parameter for a particular steppable script, the best way to make that shared in a CompuCell simulation would be to declare the model variable in the steppable script, and then in, say, the start function, when the simulation is actually being created, to say put the module level variable into the shared steppable vars dictionary, and then that module level variable would be propagated and available to every steppable that's registered with CompuCell. And you don't even need to know what other steppables are even being registered. It would be something like a feature of your steppable that if it's registered in a simulation, your steppable will make that data available to every other steppable. All right. I think this is super cool, and I'm really excited about this. So what I envision for this, I'm going to try to speed through the rest of this so I don't eat up too much more of hackathon time, but what I envision with this is being able to create sort of like particularized CompuCell modeling environments to specific complex multidisciplinary problems. But we've demonstrated this when building this framework, where it's possible for lots of groups to contribute, their steppables, implement their model implementations, and people can just selectively use the steppables that are available in some library. What I envision is being able to replicate that sort of architecture to be able to support solving very complicated biological problems. Most often, at least anymore, as we get better computers to do more number crunching, and as we learn more and get more ambitious with the sorts of modeling that we'd like to do, the models that we try to build inevitably will become more complicated. And inevitably that'll require more and more input from more and more diverse multidisciplinary teams. And frameworks like this are, in my opinion, well suited to support those sorts of collaborative and very sprawling modeling projects by enabling people to be able to encapsulate their models into something that's executable, even modifiable, loadable. So I'm very excited about this, and I would love to see this sort of architecture replicated to support other modeling problems besides just viral infection and immune response. My last thing, I just wanted to put in a couple of teasers for upcoming features for the next couple of CompuCell releases. So the first one I wanted to share was that for as much as we worked with the XML this week, the XML technically already is an optional way of doing model specification. There is a way to currently do that specification in Python already, though it's not a very intuitive way. In our next release, we will be introducing a new way of specifying all of the XML specification, but all in pure Python. You think of like the POTS CC3D elements, you think of like specifying, the dimensions of a simulation, the number of simulation steps, or say specifying details for the contact plugin or for the diffusion solvers. With the next release, you'll be able to, instead of using the XML, have a set of classes that correspond to each of those elements to be able to do all of that specification in Python. Now, the procedure will be a lot, very similar to the way that the steppables are registered and all of that. You can see an example here. So maybe by now you can imagine what this would look like with doing this specification in XML, specifying the dimensions and the neighbor order. And then this is just as simple as registering what I've been calling the core specs. Registering a core specs instance for all of the core simulation objects, register with that register that spec with CompuCell just like you would with a steppable. So those will be interactive for those of you who use, say, PyCharm or some other IDE. This will actually have built-in hinting for things like what information is available for each of these. So if you like working with the IDEs, this will make writing those simulations pretty straightforward with built-in functionality that we don't necessarily have to support. And it also makes these modular in the same way that the steppables are. So of course, the CC3D ML is perfectly shareable. This is, those are scripts that you can send to your friend or you can post in a repository and someone else can load them, in their CC3D installation, and it works all the same. This has the same sort of encapsulation as the steppables themselves, and that these can actually be instantiated in, say, something like a modular framework, and then data on them can be set interactively. And I think probably most importantly that the information that's available in these specifications will actually be settable from within the steppables. So we have the functionality right now to place some sort of ID tag on an XML element to be able to set it in Python later. That functionality will only be necessary when using the XML itself. When using the Python core specs, things like changing the contact plugin parameters or a diffusion coefficient or something like that, something that is currently specified in the CC3D ML. Instead, we'll be able to actually make those modifications in Python by actually interacting with the same objects that we use to register that functionality in the first place. And then my very last thing is what we call CC3D as a service. So this is functionality to build off of the current Python API. And this is for using CompuCell simulations as an interactive simulation service object. So right now, when you go and execute a simulation in Python using the CC3D API, you'll call the run function on a CC3D caller instance, and then that's a blocking call. You'll wait for the simulation to terminate, and then you can get data back and do whatever you please, and that's nice. This functionality actually takes that quite a few steps further, in that instead of creating an object that you can call a function on to do the execution of a simulation, instead you can do the simulation execution yourself, in that the start function that we have historically relied on CompuCell to call, or doing the stepping, calling our steppable functions step, giving us the Monte Carlo step. This functionality will allow you to actually do that manual stepping interactively yourself within a general Python environment. And if you're curious, we'll have a code snippet on the next slide. But this resolves down to actually making memory safe interactive simulation objects, irrespective of how many simulation objects have already been created or how many you'd like to create thereafter. In effect, this makes something like a CC3D simulation object. This creates lots of new capability when it comes to actually generating what we think of as a simulation service, and that you can have an executable set of code to create an interactive object that you can then interact with, both to simulate it and also to manipulate it as you simulate it. Pedro, has the comment that you can make an app to run your simulations from the internet without NanoHub. That's exactly correct. And in fact, you can do lots of things with this sort of capability, even to the extent of doing model sharing and things like that. It's one thing to make your code publicly available on, say, a GitHub repository. It's another thing to have your simulation executable and remotely hosted, and something that, say, someone could load into their environment remotely and actually interact with, but that's running on your server. So exactly as you said, to host it like NanoHub, but without NanoHub. Yeah, that's exactly what this would support. Now, there are a lot of aspects of this that I painfully have to just sort of neglect or very vaguely gloss over, but probably the coolest thing about this, well, one of the coolest things about this is the ability to actually be able to modify the interface of a simulation object from within the specification of the simulation itself. So we'll again see this in the next slide, but you can create, I'm just going to jump to the next slide so we can actually look at this. So we have, say, a function here called service underscore CC3D. And like the CC3D caller, this returns an instance of something. But in this case, when calling run on that object that's returned, all this does is just starts the simulation process in the computing sense, not in the CompuCell sense. And then thereafter, everything about that CompuCell simulation is available and interactive. So you can do the actual start call on all of the stepables that have been registered according to the simulation's scripts, the same scripts we've been writing. Everything is still according to that, except that now we have this interactive object where we can call the start function, and then we can call the step function as many times as we'd like, and at any particular simulation step, according to whatever our model is or whatever our workflow is, we can stop, not stop the simulation, but stop our integration of the simulation and interact with the things that are available on that particular simulation. Some of the interactions that are defined on the simulation are particular to just it being a simulation service for CC3D. Things like what the current simulation step is, what's the return object, like in the CC3D caller sense, things like that. However, one of the capabilities that comes with this work is for the, say, stepables inside the simulation can actually add functions to the object that's returned by service CC3D. In this case, you can see an example of this. There's just this function called service function. And when you call service function and pass a particular function that's defined in the simulation, whether it be a stepable method or some, just a basic Python function, that function then becomes available as a callable function on the service instance. So this can be particularized for all sorts of ways. I had an example here in the previous slide. I have one of the kind of mind-bending examples that I had a lot of fun with my testing of this was to actually run a CompuCell simulation within a CompuCell simulation. And actually, when this is released, this will come with a supporting stepable called a CC3D service stepable. And all this does is it just takes another CompuCell simulation that's been built either by you or by someone else, and it converts it into a stepable that you can register in your simulation. So you can do things like, say, work on the details of, say, immune cell production or, whatever you please, something that's particular to some, physiological function in some location. And then you can actually take that CompuCell simulation and convert that into a stepable inside another CompuCell simulation and use it as part of, say, some other model that you may be building. So, of course, everything applies concerning building, interactive simulations in a general Python environment. So this is not restricted to only having one CC3D simulation service in memory at a time. You can create as many as your hardware supports. Of course, when remote hosting capabilities, are implemented, then the sky is really the limit. Maybe the cloud's the limit, I should say. And so nothing then restricts us from, a sort of boom in modeling complexity of being able to create CC3D simulations that interact with other simulations. And I mean, it's hard for me to imagine the limit of the potential for this. So I'm going to stop at that. I think I've hit like an hour or so. Pedro asks, can you simulate a multi-cell system and call another model to simulate each cell separately? So this would be something like doing pots, but on individual cells. Is that correct? Okay, so the answer is yes. No. Because James could tell you much more about the particularities of pots that really wouldn't make that feasible, because at least in a very basic sense, because pots works with a three-dimensional field where the cells actually are. So probably the better way to do sort of distributed computing of the POTS algorithm would be with MPI or OpenMP, which we support. But yeah, as far as like being across different simulation instances itself, maybe that could be, I'm pretty sure that could be written, but no, it's not something we support, and probably not something that we would work to support anytime soon. As far as technical documentation for the classes, methods, and attributes, and examples in the docs. So yes, this will be documented when this is released. My goal is to do this in the next release. There is a branch on the repository, on the CompuCell repository, and I can grab this quickly. Because there are demos already available for this functionality on a particular branch of the repository. The classes and all of that are also documented. This in part leverages, excuse me, this in part leverages a Python library that I've developed separately, which I'll also include a link to, so you can check that out, because some of the underlying infrastructure is not at all particular to CompuCell. It's more with the message passing and things that enable like being able to do this service function capability. Those things are actually implementations of a more sort of elementary library. So I'll grab the link for both of those. Let me grab though the link for the branch on the CompuCell repository, because that branch does include a couple of demos, one of which is where these code snippets were taken from. So here is in the chat, this is the branch to the GitHub repository where this work can be found. Again, trying very hard to get this functionality into the next release. And then if you're interested in the underlying infrastructure behind how all of this works, then you can check out this additional repository, which is one of mine. This is a library called SimService. Then CompuCell implements some of the infrastructure in the SimService library. SimService library is built to support this sort of work and lots of simulation platforms that use Python. Okay, I think next question, Iman. Regarding having a simulation as a steppable or another simulation, does this mean that we can have a multi-physics simulation running in parallel, or simply, for example, a game of life in which each agent is a game of life? So coupling with for multi-physics simulation, that is one of the applications that this is intended for. And now, on that topic, probably what that will look like is using this service functionality to leverage built-in support for supported external tools. The examples that immediately come to mind being Antimony, Roadrunner, and Mabos. So, there are other packages that, we would like to see integrated with CompuCell, and using this service architecture would be a good way probably to do a lot of those integrations, because the Roadrunner and Antimony integrations currently occur at the Python level. The Mabos integration occurs at the C++ level, because CompuCell is written in C++ and then Python on top of that. And so doing integration with other packages, it tends to be very contextual. And so I think routing that through this service architecture for the CompuCell implementation of the sim service library, it might be a good way to be able to sort of divert all of the interconnections for doing, more realistic multi-physics based simulations. Pedro asks, are we going to learn how to build and change plugins? No, but we've been talking for months about doing a separate mini workshop with me and probably Giuliano on how to write C++ plugins and steppables. So CompuCell is set up to be able to write them and quite efficiently. It's pretty straightforward, but of course there's subtleties to it, being in C++ and all of that. And so, yeah, we've been talking for a while about doing this, and I'm thinking after the way that this workshop has gone, I think I probably have my answer on my opinion on that, and that we may try to work on doing something like a 1 or 2 day workshop, maybe in the fall or early winter.
Yep. One thing that I will say is that to edit, so there are several files for extra plugins or steppables, and they need to be in specific locations. And to edit has the functionality to create templates of those files. So it gets you started at least.
Yep. Yeah, thank you, Giuliano, for pointing that out. Let's see. Question, as it stands, the return object is available only in the finish function. Data are available only. Okay, so no. So the return object is available at any time once the simulation has actually been instantiated. So it's possible to do those operations with both. I'm going to jump back in the slides real quick just for reference. So it's possible to do these operations of working with the input object to get information from the Python space, as well as working with the return object to get things back to the Python, or the Python space. This is available as soon as the CompuCell simulation is executed. So this can actually occur even before the class definitions. The only thing about that is that it won't be available back in the Python space until after the simulation has concluded execution. Again, that's a limitation of the current CC3D Python API, and that's a limitation that will be completely eliminated with the release of the service architecture. So when the service architecture becomes available, then at any point you can just stop stepping the simulation, get things from the return object, set new things on the input object, and then continue stepping. Yeah, then it can be as complex as you please. Okay, I think that's all the questions. I see some positive feedback about the workshop from Pedro, from a couple of people. Wow, okay. All right, so let's make a note of that. To all my colleagues, I'm going to turn it back over to you, James. Thank you all for listening. I've been very excited about sharing all of that with you. Of course, any feedback would be great. I actually have to run for the day, but I will be here all day tomorrow, so I would be very happy to discuss this more with everyone, either tomorrow or via email or once the workshop is over. All right, James, back to you.
Okay, thank you very much, TJ. Appreciate your giving this presentation. So I'd like to ask our team members, Giuliano, did you want to do your demo of how to convert simulations to NanoHub apps?
Yes.
Okay, can I ask our other team member, are there people in the room now who need help in this room? Or is there anything we can do? I'd like to specifically ask our team members to join the breakout rooms and help people. I know the lateral line people needed some help, specific help, and any one of us could do that. So that would be very helpful if somebody could join them. Why don't, I don't know, Jim or Julio, actually, you probably are the best person for the lateral line people. The yeast people could also use your help, Julio, I think specifically. For other people, I'm not sure. The people who are in this room now, I'm not sure what, if you tell me what you need, I'll do my best to help you out. Okay. And beyond that, I'm trying to see, Giuliano, do you want to start? What time do you want to start? In 5 minutes?
Yeah, sure. 5 minutes.
Okay, I'll send out a broadcast. In the meantime, I'll tell you what, why don't you go check out the breakout rooms and see what's going on, and why don't we start at 3?
Yeah.
And
okay.
so you can do some breakout room assistance between now and then.
Okay.
I don't know, Tyrone, do you need anything? Are you? I don't know if Maciek is here or just logged in. You know, he said he had to run an errand. If somebody needs help in the main session, please come. Don't hesitate to ask me. Okay, sure. Feel free to unmute, but we can talk until Giuliano is ready.
Okay, thank you. I was thinking about, I don't know if it's been done before or even if it's a good idea. You know the alveoli in the lungs that are next to each other like grapes, and they are separated by very, very thin septi. And it's much easier to model a 2D system, but maybe it can be somehow extended to 3D. If let's say we have a micro city, and we have the position of its the center of mass of each cell, and then we determine the Euclidean distance in 3D, and we somehow assign to each pair of cells in a plane that distance. And during the simulation, say we take into account it somehow. Say if a macrophage secretes some TNF or something, then it damages the cells taking into account this spatial relationship, and it does some part of 3D with the computational cost of 2D. Has it been done before, or?
So this is essentially a compartmental model where you represent space by the distance between the agents.
Yes.
So that kind of modeling is done quite a bit in epidemiology, and I think it makes a lot of sense to do that. Doing the alveoli is complicated because when you have these very large aspect ratios, as you do, where you have cells that are very thin and very extended, in a simulation like CompuCell, which is lattice-based, you have to have the lattice size be smaller than the smallest length scale you want to represent. And of course, also in the alveoli, a lot of the space is empty or it's filled with air. And so having that discretized at a fine grain is probably not so good either. There are very detailed triangulated meshed sort of solids type models of the lungs where people use finite element methods to do that. The kind of network-based, technically Finsler space-based approach that you're talking about is very interesting, and I think it could be a very productive way of doing things. If you know that the risk of infection depends on the distance between the two objects, and you define a triangulation, then that's a very compact way of representing it.
Yes, for the coronavirus, I think it does not attach to the vascular pole, only to the apical, but I think there are other respiratory viruses that do, and it might take into might be of importance that the vascular poles are next to each other, perhaps. Yeah. And
yes, I think that's right. That I mean, simplifying the lung into a flat patch of tissue is a huge simplification, and it's probably not very realistic in terms of what it predicts in terms of infection.
Yes.
Yes, go ahead.
Yes, and how about the organ on a chip simulations in CompuCell? It's like you said, some 2.5 dimensional simulations.
Well, of course, organ on a chip can be quite complicated. They can be full 3D organoids, as well as bilayers or.
Yeah, the bilayers.
Okay, so I'm trying. I mean, we do a lot of those 2.5D simulations because they're fast, and they have a lot. They have a lot more detail than a 2D simulation, but they're a lot faster than a full 3D simulation. But is there a specific example that you were thinking of? Man, they were interesting questions. I'm trying to.
Yes, maybe I thought that maybe like a kidney on a chip, again abstracting away all the glomerular complications. Like there are always one layer of endothelial cells, one layer of renal cells, glomerular cells, and maybe if some immune complex or whatever damages the glomeruli, could be modeled the size of the holes that is done in a glomerulopathy, and perhaps predict what kinds of proteins pass from blood to urine and so on. This is an instance where spatial effects.
So you mean actually modeling the filtration?
Yes,
I
yes.
You look at neurons like a Purkinje cell, and they're pretty scary, but I don't think there are any cells that are as complicated as the podocytes in the kidney. They're probably structurally the most complex cells in the body. And I don't think anybody has any idea how to model that level. I don't think we really understand how that structure is generated. What are the molecular scaffolds that are giving rise to that incredibly complex interdigitation in those cells? So the fascinating problems. I mean, as a simple approximation, defining a membrane and defining transport across the membrane computationally is straightforward, but to actually build that mechanical structure that you see at the nanometer scale in the kidney, boy, that's hard. I mean, I think of all the cells in the body, those are probably the ones that would be the hardest to model in detail. Now, Giulio's Belmonte's kidney tubule simulations, those are very simple in the sense that the cells only have 3 compartments, an apical, basal, lateral compartment. But he did implement a pumping simulation so that there was an idea of the transport of material across the apical surface of the cells. And you could certainly define, if you know what the transport rules are, or you know what the ion channel behaviors are, then you can define a series of transport rules across those boundaries. But to try to implement that transport by actually doing holes and actually modeling that, then you're getting down to a level of molecular dynamics. And generally, molecular dynamics simulations don't have the timescales available to do it because they're too computationally expensive. So I'm not trying to be discouraging. I think these are issues, they're important issues. And I'm delighted to talk about them more. So if you have ideas about approaches to do that, I'm definitely very much open to that. I apologize now, I have to set up. Giuliano is supposed to give his short talk. And I'm happy to keep talking. I just, unfortunately, if I'm running the meeting, I have to do multitask because I have to keep monitoring the chat as well as working. So I'd rather talk science. The questions you're asking are excellent ones. Is your background then medical, or what's your?
Yes, internal medicine, but I'm interested in simulations and so on.
Well, I think we need people. I mean, the people who are the MDs are the people who know what's happening. You're the ones who know how to ask good questions, and so I appreciate your being willing to talk to us because we need building. It's mathematical biologists often solve problems of interest to mathematicians, not to biologists or MDs, and so it's critical to have the questions be defined by the people who need the answers. And so I do the things you're bringing up, I'm not trying to be dismissive. I really do think they're fascinating problems.
Thank you. Thank you.
Okay. Well, we can't start until Giuliano comes. I was a little bit torn about whether we should even have any informal talks, because really the hackathon should be focusing on generating the hackathon results. And so time spent giving talks, in a sense, is time taken away from projects. On the other hand, there were a lot of requests for these specific topics. And so I thought we'd take the risk of dividing our attention. Let's see what happened to Giuliano. In the meantime, please feel free to talk, ask questions, talk. Anything I can do to help.
Oh, yes, there would be another problem also. Importing an image, I saw the team with the muscle. They've modeled each pixel in the image as a frozen cell, right? Yeah.
Well, to begin with, they're going to wind up unfreezing them, but that was how we started.
Yes, they started that way. But would it be possible to start from an image, like a fluorescence image with some junction proteins labeled and so on, and with this outline of the cells, to start with the outlines of the cells, their membranes as such, not each pixel a cell, but you know. Is it possible to, in the setup, to do that? Or
so the answer is it's not built in, but it's quite easy to implement that. So if you have a segmented image, or then it's easy. If you want to use CompuCell to do image segmentation, it can help with it, but modern image segmentation is so good. ImageJ, some of those ImageJ plugins like WIDA are so good. And the 3D image segmentation has gotten to be amazingly good too. We were working with a group in San Francisco that's doing using SPIM imaging and has incredible image segmentation and cell tracking. They can basically see every cell in a zebrafish embryo and track it for 20 minutes, 30 minutes at a time. But they're only doing a nuclear label. They don't have a membrane label. So they only have the nuclear position. It's always harder to see into a tissue when you have a membrane label as well as nuclear label. So that's a trade-off there. Okay, sorry, Tin, what can I do to help you out before I turn this over to Giuliano?
Hi, we were hoping to get a separate break room or something just to show you some of the bugs that we're running into.
Okay, so let me get Giuliano. Can you record your own meeting? And if I make you host, then I can jump into a breakout room with. Do you want me to join? Do you want me to join your room, or do you want me to go to something like? I can jump into something like Open Discussion 1 if that works for you.
Oh, we can do the muscle regeneration room, Megan.
Okay. Okay, I will get Giuliano started and then join you. Okay. Right, so stop share. So, okay, so Giuliano, do you want to take the share?
Yes.
And let me make you host for a bit so I don't clobber things when I leave the room. And you'll have to make me host back when I come back.
Okay.
Okay, well, some people, I don't know how people felt about NanoHub, but some people expressed interest in understanding how to convert CompuCell simulations into NanoHub simulations. And that's something if nothing else, it would be good to show it and have it recorded for people. And so those videos are available archivally. So why don't you take the screen share, and once we get started, I'll join the other group.
Okay. So let's get started. So actually getting your CompuCell simulation deployed on NanoHub is not hard at all. It's somewhat straightforward, although can be a bit slow because some steps of the process are actually people over at NanoHub checking that you're not trying to insert virus into their systems or something. So it can take a few days. But for it, you need a few things. So you need a GitHub account, or I suppose you could also host it at some places like GitHub. NanoHub actually has a few options. So you need a GitHub account, which if you don't, there's GitHub. You need something to interface with GitHub, be it Git Bash or whatever other program you want to use. And of course, you need a NanoHub account. And that's pretty much it. So yeah, so the first things that you have to do is get this GitHub repository, which I made. This repository is a simple Python script to make your life easier, and some files that all NanoHub, CompuCell NanoHub tools need. So if on your Python projects, you have a folder with your simulation files and the CC3D file, right? When you have it go to NanoHub, it's gonna look a bit different, but similar. You need a few more files, and your simulation is actually gonna live on this folder main there, and 2 other folders with some interfacing files that you need. So you should download this repository here, which you can either clone it with Git Bash using this link or download it as a zip. Either works. And what you also need to do is to create a new GitHub repository for your tool later on. So here I'm creating a new repository for the vascular tumor demonstration that I did this week. I'm gonna actually go through the whole process here, and it will be a NanoHub tool sometime during the following week. So to create a new repository, you go to GitHub's main page, and there should be a new there. And then you give it a name, give it some description, select what files GitHub should start with, what license you want, and that's all. Now you have a new repository. Then you need to, this one you can't download as a zip. This one you actually have to clone it. If you're not familiar with GitHub, that's fine. GitHub is real simple to use actually. And Stack Overflow and Google will answer any questions you have. So now I'm gonna actually clone this new repository that I made for my vascular tumor. So I have, that's Git Bash open, and I already have it on my folder where I have all of my NanoHub tools. And I'm just gonna git clone this link here. And now on this folder NanoHub here, I have this new folder, which is this repository. So I'm actually gonna go into it for later. Okay. Okay, so steps 1 and 2 is, well, steps 1 and 2 after step 0 of having a GitHub, NanoHub accounts, and Git Bash is to create a new repository and clone it to your local machine. And also part of step 0 would be to clone this repository with the Python script. Then the next thing you have to do is to check out how to actually use this Python script here, toolmaker. Oh, and by the way, the instructions here are also in this toolmaker page here. They are not the best instructions ever, but I think they are serviceable. And if you need any help, please just, go to issues in this repository and tell me that I didn't do a good job in my instructions and how I should improve things. So in order to run this, you actually need to be able to call Python from the command line. And just in case people don't have Python in their path, what I've done here is I've come into the folder where I have CC3D installed, and then Python 37. And from here, I can actually open a command line by either shift right clicking here, I think, or was it control? I don't remember. But the easiest option is to just type CMD for command on the address bar. And that brings up a terminal on the folder you're in for Windows. Linux and Macs, you dealing with terminal is way easier, so I'm gonna trust that you know how. So from here, I can actually call Python, and it's gonna open the Python exe that is in here. How do I exit Python now? There. But I actually want to call the script. So the way to do that is to have Python and then oops, what did I do? Okay. It's to have Python and then have the path to the script, which is in my case is here. So I have Python, that toolmaker. So I'm basically telling Python to execute this. And if you execute it with no arguments, come on. There we go. It's actually gonna show you some usage text. So this script is expecting a short tool name that should be only letters and has to be 3 to 15 characters. The path to where your NanoHub tool is gonna live, which in my case is this folder here. And the path where your simulation already is. So the folder that contains the CC3D file. Okay. And the most important thing is actually the short name. Because that's how NanoHub is gonna keep track of your tool later on. And please feel free to interrupt me or tell me that I'm going too fast. Okay, so we got...
You are going fast.
Okay.
For me, at least.
Yeah.
And this is when I try to open a NanoHub account, how do I know that I did it successfully? That's very early stage question here.
Right.
But I'm having a lot of trouble with the gymnastics that you are showing later on, but that's a different story.
Okay. I don't know. I would guess that NanoHub would send you an email about your account. And the other option would be to try to log into NanoHub with the account that you made.
Yeah, okay, I understand.
Yeah.
Okay.
But I don't think NanoHub should give you any trouble. They are supposed to be open to new members from anywhere.
All right.
Yep. But yeah, so, well, you can go from the top. So step 0 was to have the NanoHub account, the GitHub account, and to have some sort of program to interface with GitHub. I use Git Bash. I'm familiar with it. But there's also an option for people that are not that familiar with command line stuff, which is GitHub Desktop, I think. Yeah. And this actually has a graphical user interface to do the cloning into your machine and adding stuff to the repository and pushing it to the repository and so on. Actually, when I started to use GitHub, I started with the desktop, and then I eventually got proficient enough that I thought just doing command line was easier. And then on GitHub, you can create a new repository, which is a simple process of giving it names and setting stuff. And then you have to actually clone the new repository, which I did it through here with the command of git clone, and then the link, this link, specifically, not this link, to the repo. And I'm already inside the folder that was created. So the folder name is the repository name by default. And so now what I did was I came all the way to my Multicell installation folder, and inside Python 37, and in the address bar, I typed cmd for command, which brings up the command line. And from the command line, I'm calling Python, and I'm telling Python to open this file that is all the way, in my case, in my D drive, NanoHub, where I cloned the tool maker into. Right. Yeah. So when you clone this to whatever path, tool maker is going to be in there. And the path that I'm passing here is the path to which I cloned this tool maker repository. And toolmaker is expecting 3 arguments. The first one is the most important, which is the short tool name, which I usually do cc3d avasc tumor would be the name I would give this one if avasc tumor is below 15 characters. Then I give it the path to the repository where my NanoHub tool is living at, which in my case would be this, and the path to where my cc3d simulation is already at, which in my case would be this. Have here the cc3d file and the simulation folder. Okay. So let me actually do that. So if I press up, I bring the command again. So I'm gonna call it cc3d avasc tum, I believe that should be below 15 letters. I said only then the letters, but letters and numbers are allowed. 4, 8, 12. Yeah, so I'm fine. Then the path to the new repository here. Oh, and by the way, if you are more familiar with Git and you would want to create, well, I'm gonna leave that to the end actually. So the path to where my two will live at, and then the path to where my simulation is already here. And if I hit enter, hopefully my script won't give me any troubles with me having spaces in my path, but I guess I'll find out now. Yeah, so yeah, I'll make a note to actually improve that. But yeah, you can't have spaces on your paths for now. I'm gonna fix that later. So what I'm gonna do is, okay, what I'm gonna do is I'm gonna copy these files here to some new place. With no spaces. And now it should work if I remove the second one. There we go. Several prints. Basically, the toolmaker is making sure that these extra folders are there with the files needed, and that your simulation is inside of main. So now if I check here, I see that there are, okay, something went wrong. One second. That's okay. I was copying the wrong folder for some reason. This is interesting. I hadn't seen this bug before. Let me check my own instructions to make sure that I'm not doing anything wrong. Oh, this should be fine. Huh. Okay. Yeah. Okay, good to know. Found another bug. I think I understand what's going on. So do not come into the CC3D Python 37 path with Python. Actually, I'm actually gonna come here where I have my simulation files, and I'm gonna have the command here. And if I had Python in my path, I would be able to call it already, but I don't. Really don't know why. I should really add it. So what I'm going to do instead is I'm going to copy the path to where I have CC3D installed. And then if I do Python 37 and Python exe, and then give it, this should open Python. And now I'm gonna give it the path to the actual tool script, which is here. Okay, still works. Well, now should work. It wasn't actually working before. And now I give it the short tool name of I've asked them space the path to where I want my tool to live afterwards. And finally, the path to where my tool, well, where my simulation already is. These errors always show up when you go live with stuff. Try deleting this again. Why? Okay, sorry everyone. There seems to be bugs that I swear weren't showing up before. Not sure what has changed, but this is somewhat embarrassing. Seems to be, what are you doing? Well, sorry about that, everyone. Gonna try to get this bug sorted, and I should be able to show this properly to you tomorrow or later on today. Okay. Okay, I found the actual mistake. So remember when I said I shouldn't call the toolmaker from the CC3 installation folder? I shouldn't call it from where my simulation is. Seems that now, for now at least, I'm gonna make this better. I have to actually call it from here, where the toolmaker is. So I actually need to open the command here. Sorry about that, everyone. So now if I come here and I do the path to Python 37, Python XE. And then I give it this path. Well, first the name, right? Then I give it this path. And then I give it where I want my tool to be, which is here. Let me just clean this from the files that were wrongly placed. Well, actually, let me double check the order of stuff. By the way, in case people don't know, Windows nowadays has this handy thing built in, which is the history of your Control C. And you access it by pressing Windows key V. Toolmaker, okay. Now short to name, I've asked them. Now this path. And finally, where my simulation already is. Now, yeah, now everything works. And we see things appear there. I already have some bugs to improve upon, which is good. And now we actually come back to Git bash that I already have open on this folder here, right? And if I do a Git status, I can see that there are several new things. So I actually want to add everything, I think, to, yeah. So I actually want to add almost everything. Actually, one other thing that I have to improve on this is that you should delete this spy cache folder that gets copied. If you don't, it's fine. The only thing that is going to happen is when you move on to NanoHub after a few days, when they're checking stuff, they're going to say you need to delete that folder from the GitHub. So if you forget it, it's not that big of a deal. So to actually stage everything to be uploaded into NanoHub, I git add dot with dot in the same sense as it's used in Unix systems. So dot references the folder you're in. So I'm basically saying to add everything in this folder. And now if I do another git status, I can see that things are in green where they were in red before. And now to actually have it go to GitHub to be uploaded, I have to do a git commit, because I'm committing something to GitHub, -m because I have to give it a message, and getting started. And it actually creates the stuff. And finally, I do a git push to push it online. And if I come here to where my tool is going to live, if I do an F5 now, it's still the same as before. But if I push and now do an F5, things appear. So this works kind of like Google Drive and others, but Google Drive is constantly doing this clone, commit, push, check for updates elsewhere, clone, etc. But Git, you need to be actually explicit with your steps. Okay, and that's pretty much it for the GitHub part of things. Well, no, actually, I'm lying. So one thing that my script doesn't do right is that if we come here to where it is, if I check here in bin, I have two shell scripts, which is what NanoHub is going to use to actually launch your tool. And I open one of them, I can see that it's an executable file. The same file with some slight modifications is also here in bin as well. Here's the sh. As you can see, it changed name. But in here, it doesn't have the executable there. So we actually need to add permission to it to execute. So GitHub allows us to do that with this command git update index -- change mod. I think that's what it stands for, equal plus x. So I actually need to do that for both the shell files in the bin. So git update - index - mod equals plus bin dash every single file in that folder that ends in sh. I'm actually gonna give you all this command in chat. Oh, my slides are wrong. Seems like, oh, I forgot to put X. That was what, okay. Okay, so that's for the shell scripts. And if I do a git status again, I can see that both of them were modified. And I also need to add execution permission to the file that lives in middleware, which is invoke. So I'm gonna do the same thing, but instead of being bin / etc., it's middleware invoke. If I do status again, we can see that the 3 files were modified. Now I have to commit this again. So git add first to add it to the commit. And then I do a git commit -m. And for the message, I'm going to give, say, exec permit. And now it's turning clean because everything is already inside of commit. Don't worry too much about it. It's actually easier than it sounds. When I got started with it, I thought it was really confusing, and I guess it is to start with. But there are many people online that use it, and at least some of them are good at explaining things. So by going into Google, you can easily figure out how to use it. Or again, use the GitHub desktop with the GUI, the user interface. Then git push. And now if so now it's saying getting started, and it was committed over 4 minutes ago now. But if I F5, we can see that the message changed to my new message of exec permit, and it was 1 minute ago, and it has executable file there. And if I go to the other ones, it also has executable file there. And now we're actually done with the GitHub part. Now we move to NanoHub. So to add a tool to NanoHub, you come here to resources, upload/publish. You want to upload a resource. and then scroll and select tools here. And you give it some info. So tool name. Tool name is the short tool name that you gave before. And that's why I said that that was the most important thing. It's imperative that they are the same. In my case, it was avasctum. So I'm pasting that there. The title is actually going to be what users get presented as. So if we actually, let me show you something. If we actually come here and go to CompuCell v4 main tool, we have this, which is the title. And if we look here at the URL, this was the short tool name that I gave it. So the short tool name is how NanoHub keeps track of what's what. So CompuCell 3D, avascular tumor growth and mutation. And one line description, vascular tumor growing on nutrient, self-limited, mutates. You can actually set what's the initial size of the box. You know, this box here, you can actually set it what initial size it would be. Set that here. Gonna keep actually I'm gonna make it a bit lower height, and I'm gonna increase this to 1,000. And then you tell NanoHub where your tool is hosted. You have two options that I don't know about, and GitHub. In my case, it's GitHub. I'm gonna bet that in your case, it's also GitHub. And then you actually need to give NanoHub what URL they should clone, which is this URL here. And for publishing option, the default is what we want. It is a Rapture Linux GUI based tool. And for access, you probably want it to be free for anyone. And register tool. In here, sometimes NanoHub hangs up and it can take a while. If it takes some more than 5 minutes, I would say to just leave and come back tomorrow and check that it worked. You should get a message on NanoHub about it. If I come to my dashboard and go to messages, well, I still haven't got a message because I still need to do the rest of the process. And what you need to do next is to actually tell NanoHub that your code is already on your repository. So now someone in NanoHub got an email or something telling them to clone this repository and get it installed and get things started. And what you will need to do before the tool actually goes live is to create a page describing your tool. So you give it an abstract. For now, I'm just gonna copy over what I had. You can add files about it. In my case, I'm probably gonna add my PowerPoint presentation, and I'll probably add a link to my lecture. And everything else is optional. Credits, citation, your funding, references, publications that use this tool. And that's it. So if you have a paper and you want to make the life of your if you have a paper using CompuCell and you want to make the lives of your referees easier, you upload it to NanoHub and you get your publication there. And NanoHub actually generates DOIs for its tools. So you could add it to anywhere you publish your DOIs. Okay, you add your contributors that are on NanoHub. Save and go next. Supporting documents, screenshots of the tool, more things to make the life of users easier. Tags. Here, I strongly suggest adding at least CompuCell 3D. Otherwise, people that are searching for CompuCell 3D won't find your tool among the CompuCell 3D tools. And since I'm not sure if NanoHub is smart about capital letters or not, I was trying to add both, but it seems that it is. And I also have 2 CompuCell 3D there. And I'm also gonna add, I don't know, cancer, tumor, bio. What else do we have here as suggestions? Biomedical engineering, sure. What else? Bioinformatics. Think good here. Let's see if it suggests something else with cancer. Yeah, cancer biology for sure. What else? What else? What else? What else? Yeah, okay. Think I'm good with the amount of text that I have. Save and go next. This is kind of a preview of the page. Finalize. And that's it. Now we have to wait for people at NanoHub to install stuff and approve it and have it go online. Questions? Do you want help with getting your tool started? Anything else? And again, the instructions are in this page here. Although I have some bugs to fix now and actually have to improve these instructions. And I'm gonna upload my slides as well. Okay, no questions. So that will be all for me. Thank you for listening to me for the past 40 minutes or so. And again, if you have any troubles with getting these tools going, you can either open an issue on the toolmaker repository or send me an email.
Yeah, probably the second option will be the one that I will pursue.
Yep, I'm
When
typing
I
up
get
my...
to the point.
Yeah, so there you have my email as well. And yeah.
Thanks.
That's it.
Oi, Ju.
Oi, Bar, tudo bem?
Tudo.
Como é que tem as coisas aí?
Ah, tranquilo.
Tá ajudando alguém agora? Ou
Ah,
antes?
não, agora, eu ajudei mais cedo. Agora de tarde eu estava arrumando a apresentação do demo 3D aqui,
Ah, sim, você vai
que,
dar mais tarde, né?
que surgiu de repente para dar, né?
Tá, tô vendo aqui as 3h45. Era pra ser agora. Aliás, era pra dar uma outra
Não,
apresentação antes.
né?
Era pra eu estar dando uma apresentação antes.
Era para ser tu agora, não?
Sim, mas eu tava no breakout room. Bem, o Guido disse que era mais importante ajudar as pessoas no breakout room do que.
Sim. Ô, Juliano, tá aí?
Estou.
O que a gente faz? Tem, tem 3 pessoas aqui que falam português.
Tem uma conversa secreta na frente de todo mundo. Sei lá, eu tava quase broadcasting uma mensagem para todo mundo avisando que o Júlio ia começar a apresentação daqui a pouco e torcendo pro James aparecer.
E o James está lá na.
Moscow Generation.
Ou vai,
Onde é que ele tá? Tá
ou
no
vai
Muscle, né?
um de nós catar ele lá.
E o Lateral Line eu tava lá agora há pouco.
Mas eu tava de manhã ajudando, dando pitaco lá no Janus, no East Colonies.
Sim.
O Juliano andou lá também.
É.
Mas então agora a gente começa a dar ou não? Acho que
Deixa eu broadcast uma mensagem.
Que nós três estamos aqui à disposição, né?
Eu não posso.
Não tem
Eu só.
muito sentido. Essas apresentações no meio da Hackathon não tem muito sentido. Em princípio deveria estar todo mundo. Né?
É que teve interesse.
Estou vendo. Tinha 6 agora no Juliano. Um era eu. O outro era ele.
Você fez o broadcast?
Sim. Qual é o assunto da tua apresentação mesmo?
A minha?
Subcelular Chemical Modeling.
Não sei se eu preciso fazer isso aí, sinceramente.
Unfolding, then?
Não, fala o seguinte, fala assim, tá nós três aqui à disposição, se alguém quiser.
Sim, na real eu não posso sair daqui porque o James me fez host e pelo visto o host não pode sair da principal por algum motivo.
Ah, tá. Mas...
Ok. Então vou mandar in 10 minutes, Julio will begin his presentation. How about that?
Não faz isso não.
Ok.
Diz que eu e o Gilberto estamos aqui à toa.
Ok.
E que, bem, Gilberto and Julia are here available if you need them in the breakout rooms.
O artigo da polarização, Júlio, já acho que vai estar praticamente aceito já. Sabe aquele que a gente fez de polarização?
Ah, legal. Onde é que vocês mandaram?
Para física A, né? Nós temos que mandar para onde a gente pode, porque o dinheiro está muito curto, né? E o dólar está...
Altíssimo, né?
Né? E a física A não está tão ruim atualmente, né? De fator de impacto, está 3 e pouco já.
Porque era menor antes?
Sim, sei lá, 5, 6 anos atrás era 2.
Às vezes mais pessoas estão publicando lá por causa disso aí.
Sim, porque qualquer outro é $2.000, né?
Eu sei.
Imagina, $2.000 é R$ 12.000.
Não dá, não.
Como é que nós vamos pagar isso?
O PLOS One, o PLOS diz que eles nunca baseiam a aceitação do artigo para publicação com base se você tem dinheiro para pagar ou não.
O Plus One é 1.350
Mas você diz,
dólares.
eu estou no país de terceiro mundo, é muito caro para nós, eles aceitam do mesmo jeito.
Pois é, mas acontece que os nossos contribuintes não são todos do terceiro mundo, aí eles ficam, né? Se fosse só gente aqui de Porto Alegre, lá, mas às vezes tem o François, às vezes tem o James, e aí é o primeiríssimo mundo, né? E eles aí não estão muito.
Pede para o James e o François pagar a maior parte.
Não, o James até do Biophysical Journal ele pagou aquele
Sim.
Da simulação. Que foi caro.
E o Biophysical Journal você pode escolher não pagar, mas daí fica.
Esse nós mandamos assim. Tu estava nele, né? No de simulação.
Sim.
Fica naquela quarentena, né?
Sim.
Eu não podia acessar o usuário, porque a gente não tinha aqui acesso.
Assinatura.
Aquele
sure.
que o.
Marco, yes, I can. What do you need, Marco? Sorry.
Hello. Well, I just have a couple of questions about detection of molecular entities in the microenvironment, in the environment outside the cells. I mean, how can I how can I do for to see if a cell is sensing certain molecular entities just in the nearby or in the center of mass?
Oh yeah, there are ways to do this. Julian, do you know by?
I don't, but my Control-C history should have it because I pasted that command earlier for somebody. But with if you have it as a chemical field somewhere, you need the secretor plugin, and then the secretor object has a function that is amount seen by cell or something like that. Trying to find it again. I lied with my.
Marco, you're probably doing that from the Python code, right?
Yes.
So if you go to the top menu, comes up with the Python.
That one is not there yet.
No, but there is the comes up to the Python secretion uptake.
Yes.
On the very last, and there should be uptake inside the cell, inside cell at boundary, inside cell at boundary, and
outside
on the cell. Or uptake inside the cell.
But the thing is that I don't want to set a secretion or uptake. I just want I just want to check if there is in the nearby enough of a certain entities, because I need to link the amount of molecules to a Boolean variable into the Mabos model.
Right.
Okay.
Just need to retrieve this information.
Right. So that command there gets the chemical field of the whole cell. I'm not sure if an equivalent exists for just outside or at the boundary. But if it doesn't, there is the cell boundary pixel tracker plugin, And with that one, you can get the list of boundary pixels, and then you can go through them in a loop and check how much chemical is in each pixel.
That's perfect.
Okay, so on the very end of the constantly Python, there is this visit, and there is a visit all cell boundary pixels. So you can use the option.
Perfect.
But you need to add the boundary pixel tracker at the beginning of your simulation on the XML.
Yeah.
Okay.
So
So it's a plugin, right?
yes. So you have to go to XML and add the. If you screen share, you can show you if you're.
Yeah, of course. Can I do it? Can I do it here or maybe in my breakout room?
Okay, sorry. How, Julianos? How long have you been done?
20 minutes, give or take.
Oh, okay. Sorry, I got. So Julio, the people doing the muscle the muscle degeneration.
Yes.
One of them. Did you talk to the people doing the lateral line?
Yes, I was there until now.
Okay. Because the people doing muscle degeneration, also one of them wants to do basically something that looks very much like the kidney tubule simulation.
Mm-hmm. Okay.
So they're eager to find out to learn about that.
Okay.
They're at University of Virginia. And I apologize if I interrupted. So do you want to go ahead and do, Gilberto, did you want to do a presentation, or Julio? Which order do you want to do?
I don't know.
I don't know either. Maybe Julio is talking, but there is so few people here. What do you think? Do you think it's worth to present now, James?
So Giuliano, do you want to make me host again?
I did already.
Okay. So I'm sorry if I interrupted the conversation. When you say there are few people, does that mean there's nobody left at all? I see a lot of people in the breakout rooms working.
Yes, but not here in the presentation room.
Well, did you send a message saying that you were going to do a presentation?
Yes, I think Juliana did.
Well, I sent a message.
I sent a message saying that we are available, and then Marcos is here. Okay.
He was going to send a message and he didn't.
Which of you is going to present?
I can do that now.
Okay, so I will send a message saying that at 4:15, Gilberto is going to present, and if you would like to hear his presentation, come to the main meeting. How's that?
Okay for me.
And then if no one shows up, you can record it and you'll have it recorded, or you can choose not to do it.
Okay.
How's that?
No problem. Fine.
And then Julio, if you can talk to the muscle people a little bit while we're doing that, that will be good. Okay.
Wait, which room is that? Muscle regeneration?
It is, sorry, hold on. This is the problem. Trying to run the meeting and also work with people to get at the same time is a little tricky. It is, where did he go? I don't know where they all went. I guess they're done for the day. I don't see them.
If the one led by Megan, there's no one there.
Yeah. Okay. Well, they can always join back. So what can we do for you? Did you want to? Did people come to hear the talk, or are you here for a question?
We came to hear the talk.
Okay, so I guess Gilberto, you were on next, right?
Yeah.
So let me send a message saying that Roberto will be. And Gilberto, you were scheduled? No, it was Julia was supposed to be next. Was that right? Or was it, who was announced?
Well, the order will be me, so it can be me.
Okay, so I better say that. I better announce it properly. Julia will present subcell structure and planner clarity models at 4:15 p.m. Okay, so I sent out a message to that effect. Let me stop and restart the recording so I have you recorded properly. If you want to queue up your slides, that would be, or whatever, however you want to present it.
Mm-hmm.
And then wait for 3 minutes and take it away.
Right. Okay, I have the slide here. I'll wait a few minutes and then I'll start.
The other people who might be interested for you to work with are the yeast colony people, because they also do buckling.
I was with them this morning.
Okay. Vignesh has left the meeting, I think, but Vignesh also was he's in India, so the time zones are terrible. But he was interested in the more the flock model type things that Giuliano has done. I don't know, Giuliano, if you got to talk to him or not.
To whom, sorry?
Vignesh?
No,
under wound healing.
No, I have not. Good.
But I don't think he's here. I think he's probably getting some sleep.
Yeah, he messaged me and I was looking for him on the people, but I couldn't spot him after noon-ish.
Okay, well, I'll turn it over to Julio then.
Okay, so hello everyone. I'm just gonna give a quick presentation on PCP modeling in Compusal 3D. So I didn't have much time to prepare those slides. As you can see, it still says Bloomington pre-COVID era. But basically the idea is that into the slide, you have seen this before in our developmental cells. The tissue grows, and one of the key things that they have to elongate, right? So because all of them start with a spherical symmetry and eventually breaks this symmetry and becomes elongated one direction. And we have already talked yesterday about that one of the ways that to achieve this elongation along one axis is by convergent extension, right? But what all those models of convergent extension assumes implicitly is that the cells themselves are polarized, right? So they know that they have to do something along one direction and something different along another direction. So these all assume that the cells are polarized, and all the cells in the tissue are polarized in the same fashion. So there must be a way to make all those cells polarized and make sure that they are aligned with themselves. Okay, so well, the cells have to break symmetry, right? And there are many ways that the cell can break symmetry when the cell moves and crawls, as Gilberto showed on Thursday or Wednesday. The cells break their symmetry, and there is a front and there is a back. When the cells become epithelialized, right? So undergo from mesenchymal to epithelial transition, they also break their symmetry and become they break symmetry along the apical basal direction. And usually the cells, when they are in an epithelium, they can also break symmetry in another way, which that besides this perpendicular apical to basal polarity, they can also have a in plane polarity, which is called planar cell polarity, whereas the cells in an epithelium, they have themselves know where there is a side to them to be the proximal side and another side which you can call a distal side. So usually this happens through some kind of signaling pathway. That's usually the PCP signaling pathway. And well, what I want to show is that there is a way to do that in CompCell. Okay. Okay, these are old slides. Okay, and basically what I'm talking about is what you see here on the right. So remember that we on simulation here on the left, we are seeing the cell in a cross section, and you have this apical and basal polarization, right? And to do this models, you have to make a cell not be made of just one compartment, but to be made of 3 compartments, right? So they have an apical side, a lateral side, and a basal side, and we group all of them together to be made of one cell. So one cell is not really a cell in the sense of the CompCell terminology, but is a cluster of domains, right? And those cluster of domains make up one cell. So this is one cell, this is another cell, maybe this is a little bit easier to see, okay? And in this kind of compartment, as well as in the kind of compartment that were used for the cell polarization, the location of each of those compartments was very well defined, right? In the case of cell polarization, you have a nucleus, right, in yellow. You have the cytoplasm in blue, and then you have the front of the cell, I believe, in green. Okay, so I think that these were the color scheme used by Gilberto. Here, you also have a very well spatially localized compartments. You have the basal on the top, apical on the top, the basal on the bottom, and this blue lateral or core compartment in the middle. Okay, so this is a way to use the compartments to represent a cell, and we have a non-zero internal energy between those compartments to make sure that they are actually spatially segregated. Okay, those kind of signaling that happens during tissue polarization, the PCP pathway, in principle, there's no spatial order to those molecules. They can be anywhere, and as the first row of cell polarize and the second row polarize and the third row polarize, as those cells polarize, then this becomes segregated. Okay, so if you want to try to replicate that in CompCell, there is a way. You'll be again using cell as a collection of compartments, but the thing that goes differently about it is that first, the compartment is not spatial location of the cell. The compartment will actually be representing regions of the cell with more of this molecule or more of that molecule, right? So in principle, they can be anywhere. And what you want is that at the beginning, you want them to be mixed and then sort out if they receive some kind of external input. Okay, so you see what I'm trying to refer to in this picture here, what we want to model is a cell that has 4 compartments. A compartment that sits on the center, which I will just call cytoplasm, and let's say 3 molecular compartments. I don't have a better word for that, which sits on the boundary of the cell, and in principle they are mixed. They cannot self-segregate or by themselves. So here you have this red, this blue, and this green. Okay. And then the idea is that this each one then is not a single molecule. Of course, we are not at that level of detail, but more or less represent, okay, maybe in this region there is a little bit more of this green molecule or green set of molecules, whatever that represents, and this other one has a little bit of more blue, and this other one has a little bit of more of the red group of molecules. And if you see the correct spatial hue from the outside, you start to segregate those molecules. So here on the panel B, you have those 2 of those cells together, and let's say that those green things here sitting at the boundary, or my pseudo boundary here, represents the catenins of the cells. Okay, so if the cell is just sitting alone in a buffer, it cannot really. It has those catenins on the outside, but does not know where to put them. Okay, but as soon as you have 2 of those cells together, right? This catenin is a transmembrane molecule that can recognize another catenin in another molecule. So we can say that, okay, if this green population represents catenins, and as soon as you have those 2 cells together, they will localize there and self-segregate automatically to form this boundary here. Not sure if this is making sense. And then the red and the blue can be other kinds of molecules that sit on the surface of the cell. So if, for example, this red means integrins, and the medium that you're modeling is actually made of lots of ECM, then what you expect that when you place the cell on that environment, all those green pixels will self-segregate to the boundary. And then because they are the integrins, and the integrins is the connection of the cell with the extracellular matrix. Or you can have other things that are more fun. You have this group of molecules called ephrins and Fs, which are transmembrane molecules, just like catenins, but they do not connect to themselves. They connect to the other type of transmembrane catenins. So ephrins connect to Fs and vice versa, but they do not connect to themselves. Okay, so let's say if the blue and the greens, they are like this. So when you put those 2 cells together, the green become in contact with the blue from the other side, and the blue becomes in contact with the green on the other side. And so on panel D, we have this thing happening at the cell-cell interface. So I do not know if you can see, but there is a black line here that saying that this is the separation between the 2 cells. And at the same time, we can also at the same time have my red to still represent the integrins. And so if there are 2 cells surrounded by some kind of ECM, you'll be automatically having this molecular reorganization at the surface due to this interaction with the outside environment. So of course, how you can do that, how you can make sure that the cells are mixing inside and the cells self-segregate on the outside, all this is achievable by just playing with the internal and external contact energies that you seen yesterday. Okay, so I'm not sure if I'm making sense here because I cannot see your faces, but is this making sense? Roughly the idea behind?
Yes.
Yes, okay. All right, so Basically, that's well, this is more or less what you require to do this PCP kind of modeling, and this principle is what's happening in this series of simulation snapshots that I'm showing to you. We start with a bunch of cells with all those molecules randomly thrown in there, okay, and they will normally remain randomly inside those cells, but because they have this preferential interaction of let's here blue to blue and green to red, they self-segregate, okay, and organize, and eventually you reach a situation where you can see this kind of pattern here, where well is blue ones inside each cell, the green is always to the left and the reds are to the right, and the blue is doing the transverse connection, just like as you see here. So for the Drosophila wing, that's what they say this is going on. You have an early stage with all those molecules, Van Gogh, prickle, frizzle, the shelf, and I forgot what the DGO means. Are randomly, they're not organized, but they kind of recognize each other, right? And they self-organize into this thing, so the cells become polarized on their plane that they are. So planarly polarized at the apical side. Okay, and all this is done by doing tricks with the, or make a very well guess choice of what the internal versus external contact of energies are. Okay, so well, basically these are all my slides, and so I can show a code that more or less implements what you see here, and I can walk you through. But before I do that, let's let's talk about what should be going on here for this to work. Okay, so if you want to have 4 cells, cell compartments, okay, and you want the cytoplasm to be in the center and all those things here to be at the boundary, what you have to choose is, first you have to make the cytoplasm contact energy to be very high with anything else that's not so the cytoplasm has to be a very high contact energy with everything that's external, while the blue, the green, and the red compartments, they have to have they should not care in principle what should be outside. They should not have this strong rejection, so you choose a lower J for all these other colors in what's outside. So that goes into the external contact energy. The other thing that you need is that you now looking at the internal contacts. If you want the cytoplasm to be segregated and all the other 3 to be mixed, what choice of internal energies you should choose? Does anyone have a suggestion how to get what you see on panel A? Yeah,
make the energy for the medium very high so that it doesn't drift into that and sticks.
Yeah, but you're yeah, that will make sure that those yeah, they do not drift, but how to make them to mix? Okay. So first, so we already set the energy between cytoplasm and the black region to be very high, so it's at the center. You can also add some positive energy of the cytoplasm with these other colors inside to make sure that they like to be segregated, right? Now for the blue, red, and green to mix inside in this boundary, what you do, you not only you have to set up a very low addition energy between them, contact energy between them, you actually have to make a negative contact energy between them. Okay. So when you make a negative, they want to have they they strongly want to maximize their contact energy between themselves. So those pixels start to mix, actively mix between them. Okay, so the energy between green and red, green and blue, blue and red, and blue and green, they are all negative. If you make those energies, internal energies negative, then those three compartments, they like to mix inside. Do you see that? That's the trick. When you do this, you make sure that all these compartments will be very well mixed. Because if you have any kind of positive energy between them, they will segregate from one another. Making the energy zero will also lead to some mixing, but if you make the negative, you guarantee that they will be really mixed. So I know that you have not used negative contact energies before, but this is something that we use in the here. Yes, j equals -10 will be induce more mixing than j equals -2, for example. Okay, but when you do this model, you don't want to be that negative, because if you make them too negative, they will never sort out when they come in contact with something else. So you just want to make it negative enough so they mix, but not negative, too much negative, so they will never sort out when they see other cells. And then, okay, and then for the C situation, you still have a negative value for all things inside, but the red compartment has also a low energy with something that's outside. Okay, while the red and the blue and the green, they have a more positive contact energy between them and the medium outside. So, and then, well, then to induce those sortings is whatever choice of contact energies you have on the with those compartments with the external world. Okay. So that's basically it, right? So we are not doing anything fancy. We are not in the sense that we are not using an extra plugin. We are just using the native plugin from Multicell, right? From the pots. So in my thesis, I call this a subcellular pots modeling. It's just a new way to use it. Okay. So how about we? No, the pixel comparability will not be the same, because both things are divided by temperature, and one will be drive the minimization of the energy further than the J with equal -2. Okay. Well, if they're both driving the energy down, right? They should be accepted with the same probability. It's just if something else comes that erase that mixing, there'll be a higher cost of erasing it if the j is equals to -10. Okay. Okay, so let me do a new share and show a code for that. So are you seeing my tweeted? I hope you do. So let me see. So this is the what I call an extra module, PSP signaling. So this is a simulation. So this is a standard XML code that you see. It has a metadata here, a pots here. I made 100 and 100. Okay. I make periodic bound conditions on the X, right? And I created 4 compartments, a core compartment, which will be the center of the cell, a proximal, a distal, and a lateral compartment have volumes, and I make all those energies here internal to be either 0 or to be negative. Okay, so here you see -1, -1. So maybe it makes more sense that I show the simulation before I talk about the code. Let me do this. Just give me a minute to organize myself. Okay. Let me do a new share. Okay. So are you seeing my desktop?
Yeah.
Okay. So here's simulation, right? This is the initial condition. I start with all those cells, and you cannot see that what I did at the very beginning. I start with my cell made only of this core compartment, and then I add all those other compartments randomly inside the cell. And because I chose the energy such that the core compartment hates everything that's from the outside touching it, what will happen is that the core quickly will go to the center, and all those colorful compartments will go to the outside. So if I play, you hopefully see that happening very quickly. Okay. So, okay, can you see this? Okay, it's kind of segregating. And what is also happening is that I have medium here, I have this red region here, and the green likes the red across membrane, and the red likes the green, and the red also likes the medium. Okay, and the blue compartments, they like everything, right? They don't have specific preference, but those two preferences here and across membranes ensures that over time those cells start to become polarized. So I draw a vector from distance. So this vector is one vector for each cell, and it basically measures the direction from the center of mass of the green compartment to the center of mass to the red compartment. And initially they are all randomly oriented because I start with no order, but because they like to align with themselves, and there are these external cues here, over time you should see that those arrows will start to align. And if I wait a very long enough simulation, and you should see all those arrows to more or less pointing in the same direction. Okay. So of course, here I made a very big simulation. I can make a simulation with less cells, and the takeaway is that the less cells you have is the easier it is to actually ensure the quicker the whole tissue polarize. Okay. So let me show in the code what's going on. Okay. So are you still seeing my code here, my screen?
Yeah.
Yes. Okay. Good. Thank you. So I set my simulation to be 100 by 100, and I make my X to be periodic. Okay, because I do not want to have interactions with the two sides. I define those three compartments: core, proximal, distal, and lateral. And I set the contact energies and internal contact energies, and And here for my, here you can see that the energy of the core with everything else is very high, is 20, okay? So it wants to be at the center of the cell. And all these other things with outside is usually smaller, okay? Here you can see that everything interacts with medium with high energies, except the medium and D, so that the distal compartment. So that's a slightly preference for the distal compartment to face the medium, right? And here the proximal. So all here is across. So is from one cell to a different cell, right? So this is a cell to neighbor, and here is internal to the cell. Okay, so proximal to a different cell they do not like, so it's very high. Proximal to lateral they don't care, but proximal to distal, so the two sites that should be touching each other across cells, they like, so I made a low energy. So they like to segregate. So the P likes to be next to the D of the next cell, or the red likes to be next to the green of the other cell, right? And then goes vice versa. And likewise, the D do not like to be with the D of the other cell, and the P do not like to be with the P of another cell. Or red with red don't like each other, and green from the other side they do not like each other, so I make those energies high here. And everything with the lateral is again, the lateral do not care. Okay, so by default 10 is going to be my middle value, and the middle value means it's neutral. Okay, now inside internal energies, you have okay, everything that's the same thing can be 0 because it doesn't matter. The core has 0 energies with everything, but it kind of likes the lateral side. And proximal to lateral, they well, P and L, D and L, and they like to mix, so this is to ensure mixing. But what I have said here is that P and D they do not like, so everything inside the cell except for the core they like to mix, except the P and the D. Those two actually like to segregate from one another. So you may revise this, you may make this 0, but because the green and the red they like to be on opposite sides, I made that internal energy to be positive. I'm not sure if that's a good choice or not, but it's something that we see, so I just put it there to facilitate the process of cell polarization. Okay, so this will kind of drive an internal polarization, but this is not enough by itself to say if they should be like this or this will be just random. Okay, and then here I just set the initial layout of the cells. So on this model, I just draw core cells at the beginning, right? You see that there's only core, the cells are 10 by 10. So for this model, I want to have a very big cell to make sure that there's enough room for all those molecules to be on the membrane. And I do but of course I have to also add the other compartments to it. And that is done on the Python level. So here on my start function, this is what I do. I do a loop over all the cells of type core. Okay, so all the cells that I just draw in the beginning. So if you go back here and see how it starts like this, and then you see the other compartments appearing, right? So let me show that again. So at the beginning it's just the yellow cells, and then you see the other ones. Is that when I just hit the step here, what you see first is what I did from the XML, and what you see next is what comes up from the Python code. So the XML only draws this, and then the Python code draws the other stuff. So let's see how this other stuff is drawing. Okay. So I only have the core cells square side by side, and then I go under each one of them, and I just use this command, and this command can be used from here. Cell manipulation, create cell. Okay, I create a cell of type P, a cell of type D, and a cell of type L. So that just creates a cell that yet does not exist in the lattice. And then I assign volumes to those cells. Okay, I assign lambda volumes to those cells. Okay, but I still have to draw those cells, right? And I also tell the code that they should be part of the same cluster as the core cell. Okay, so here I just create and define other compartments. Okay, so now I have to draw those cells. So what I do is I actually get the center of mass X and Y from this cell, which I'm going over. So that's going to be one of those square yellow cells at the beginning. And then I'm going over those pixels inside the cell. Okay, so I'll go up and below the center of mass in X, up and below the center of mass in Y. And then for each one of those pixels that I'm visiting inside the cell, I'm just basically getting a random number between 0 and 3. And if the random number is 1, I draw on that pixel that I'm going over the cell P. If it's 2, I draw at the distal compartment, and if it's 3, I draw the lateral compartment. Okay, basically this. Okay, and that's why you are seeing this this kind of random assign of pixels here. Okay, and I don't care that they are random because I chose my my pixels energies, the energy between compartments inside and outside, such a way that it's guaranteed that they will sort out to their correct positions, right? And after this, well, which means they will sort out to the boundary, and because of this energies contact energy between the cells and also the cells in the medium and what's here in the bottom, I will also ensure that hopefully they also align into the correct orientation as the simulation goes on. And then the last thing I do in the code is I kind of find out where's the minimum cell, how low the cell is, and I just draw a very big red compartment at the bottom. Okay, and one of the things that I forgot to do here is this compartment at the bottom does not have a volume. So what I can do is I can define a cell type we call bottom. This will be the bottom, and the reason I'm doing that because I want to assign a target volume to it, and I want it to be exactly equal to the current volume that the cell has. And then I have to assign also lambda which is the string of the volume constraint for that cell. So let me check that to be 1. Okay, and that basically draws the cell for me. Okay. So and the reason I made this to find where the bottom cell is and then draw later is because I want to be able to go here in the code and specify how many cell layers I want. So here is from this y minimum and y-x is how many layers it has, right? So from 10 to 80 at 10 time step is going to be 7 layers. You can go here and count 7 layers. I can go here and make this smaller, right? Just 4 layers. And when I restart the code, you should automatically get your 4 layers. And you should see that in this simulation, you should get all the cells to align quicker. Let me just play. There it is. You see that self orients, and so let's watch this cell here if it can find its way. So those 2 cells are not properly polarized here at the bottom, on the top. Here on the bottom, they're all kind of properly polarized. There's still some defects here. And this side of the embryo is already all polarized. And well, we basically have to watch and keep rooting that the whole thing polarized quickly, right? So, and of course, this will depend on wherever I made a wise choice of contact energies at the beginning to ensure that this will happen efficiently or not. So this is an old code. I do not remember anymore what I did here. If this is really the optimal parameter, it doesn't really help that those cells are moving so much and exchanging shape, neighbors. And they're not really tied in the space in a hexagonal way. If they're nicely tied hexagonally, that will also help things a lot, right? But okay, now this cell here that was not properly polarized is now polarized. Okay, you can see here, and this one here still have not found its way. Those 2 cells here, those 2 ones, they are kind of lost. But well, eventually, if I wait a very long enough time, the hope is that the tissue will polarize. But basically, that's how it's working. So I did not quite prepare this talk, but that's basically what I have to show. Do you guys have any questions, comments? I'm here. Okay. Okay, there's a question. In the biological context, do some partners that interact between cells also mutually exclude cohabitation on the membrane rather than mixing randomly as in the model? Okay, that's a biological question. I don't really know how to answer. Maybe. We do have things like protein segregation. There's a lot of studies there about going on in the cytoplasm, right? That's one of the things that Amy Gladfelter does here in UNC Chapel Hill, and I know that they're having lots of model on liquid-to-liquid phase separations in biology, so that is a hot topic. And usually it's on cytoplasm, but I guess that if it happens on cytoplasm, it must be happening on the membrane as well, right? Okay, in this simulation, it's possible to rate time scales. Okay, this one is a little bit harder. A priori, I don't think there is. If you are trying to model maybe the wing polarization, and you know how fast those cells polarize, and you have a model, and this model also have a time scale, then the thing will just compare the 2 time scales and then set the conversion. Okay, I think on this kind of model, this has to be done a posteriori than a priori. And then you can change parameters and see, okay, if you do this kind of thing, that should double the time or half the time. What are the blue sparks in the vector graphics? That's a very good question. I do not know. It's okay. Let's look at the let's look together at how those things are set. So let's click here. This is something that goes in the tab field. I set all my vectors to have a fixed length of size 4. Okay, so that should be 4. I do not know how that scales here in the graph, but it should be 4. If I make this 2, I will be look shorter, right? I can also fix the arrow color, and let me choose a color here to be strawberry. Okay. Okay, now you don't see those blue things here. So what I think is that for some reason, okay, let me tell, you can make those arrows to either be bigger or smaller from the code, right? And if you have them to be bigger or smaller, they will be, the bigger ones will be red and the smaller ones will be blue. Okay. So you have this rainbow gradient. So I guess that for some reason in the code, arrow happens to be smaller for some reason, then just change color from red to blue. Okay, but well, okay, now I fixed that in the code, and that now should be okay. You can also have a minimum and a maximum range for the magnitude of vectors. Okay, that's something that I did not show in the code. Did you learn how to do these vector plots?
No, not yet.
No, okay, so that's a good opportunity for you guys to see. So here I create a new steppable called vector visualization, and I strongly encourage you that you do not have all your code within the same steppable, but that you have a separate steppable for each kind of logic task that you want your code to do. Okay, and that's especially for the everything that you are doing to create visualizations to your program. It should be a separate steppable, and you have more than one visualization, should be each one a steppable. And why I say that is because then you also have this other. So remember, you have the XML code, you have this steppable file code, but you also have this other code here, which actually calls your steppables. Okay, and one thing you can do is that if you have each function of your simulation in a different steppable, you can easily turn them on and off by just doing this. Okay, so if I do this now and play my simulation again, I'll see the cells and on the cells. Now I'm not spending time doing the vectors. And then I can go back here and uncomment, save, play the simulation. Okay, I still miss my vectors. Maybe I have to create a new graphic window. It's like here, PCP vector is back there. And as you can see, remembers that you want to have your colors to be pink. Okay, but let me go back to showing in the code how that's done. So it's basically this plugin here. I'm doing this in a step function. I do not want to, well, after Monte Carlo step equals 100, let me organize my thoughts here. Okay. Yes, so on line 53, writing this initializer function that you always have by default, I create a field, okay, using the command self create vector field at cell level pi, and I call, that's the name of the field. So this name here is what appears right here. Wherever you roll there is be one of the options here, and the default option that you always have in Awesome Merge is going to be the cell field. The cell field is the view of the cells, and the color of the cells. Okay. So I create this PCP vector. Okay, and this is the name of this thing here. Okay, so this is the way I can grab it on the step function. So the first thing I do in my step function after checking the time is I clear up this field so there should be no vectors in it, and then I go for every cell in the self core and I get the list of all the clusters, right, or the list of all the compartments inside that cell, so you have to pass the cluster ID to get that. And then I define P and D to be 0, and then I go over all the cells or all the compartments in my cluster. Okay, and then if it's a proximal cell, I store which cell it is. If it is the distal cell, I store that cell, and then if I found the proximal distal cell for that specific cell, I calculate the vector distance between them. Okay, and then I calculate the angle that they have with respect to the x-axis, right? So remember, you are using this A tan 2 calculation. So in order to use that, you need to have import everything from the math library. So maybe I can do this. And okay, oh okay, that's what I'm doing here. Okay, it seems a little bit redundant, but this vector can be any length, right? So I got the vector, then I take the angle of this vector, and then I convert this angle back to a vector, and it's okay. Maybe that was not the most beautiful way to do it, but that ensures that this back and forth here ensures that all the vectors will be of the same size. And then once I have that, I populate the cell field. So this object here is storing the field that I'm using. And you can add as an argument the cell that you're plotting, and then I add in the vector there, and that's what makes the arrows. That's what's draw the arrow. So we draw one arrow for each one of those cells. So I don't know. Does this make sense? Let me see the chat. So basically, that's what I'm doing to plot the arrows. So I can also comment this and just plot the vector directly, okay, and save. And I can go back to simulation, stop and play. So I can. So this is not behaving very properly. I do not know what the issue. It's because there is I know. Okay, for some reason that did not work as I expected. Let me try something like this. So you can also, when you use the get the invariant distance vector between cells, you can either get it as a tuple, or you can get that as each one of those elements separated. So let me try to fit like this. Okay, now you see that each cell, each vector has a different color, and the reason it has a different color is because each cell, some of those vectors will be longer and some will be smaller, right? So I did not normalize them. That is what's going on here. So I can also make the arrows, instead of being all the same length 40, we can scale the length of the arrows, and you see the big one is red and the smaller ones are more blue. Okay, so now we have two things to tell you can see the the bigger arrow also have a different color than the smaller one. So that's how the visualization of vectors by cell works. Okay. Okay. Any question before before we switch over to Gilberto? I will put this code on the student material so you guys can also play with it and maybe use on your projects if you wish. Okay.
Okay, wonderful. Julio, thank you so much. That was great. I think there are a couple of people who probably would like your help if they're available, if they're in their meetings. I think Suvik maybe would like it under glassy monolayers, would appreciate your help.
Okay.
Gilberto, if you want to queue up and give us a brief presentation.
Okay, I can do that. Can I share my screen now?
Yes, you should be able to share, and then we'll have our final check-in as soon as you're done with that. So that'll probably be about 5:30, 5:40.
Okay, guys. It's late already. I'm going to shorten the presentation and basically to introduce the model, the 3D model, and I will show you the simulation running with some extra movies at the end. Okay? The basic of this simulation is a continuation of that 2D simulation that Pedro and I showed last Wednesday. We extended this model. Actually, we started the simulation with the 3D model, and then we make a simpler 2D model to present as a toy model here for you guys to show you how you can make a cell to move. And now we are extending these 3D simulations to multiple cells as well. Okay. Just to remembering what we introduced last Wednesday, that our biological model is the Abercrombie model, where the cell moves by protruding this lamellipodium, and inside the lamellipodium there is a complicated network of actin monomers and fibers, and the basic components of the cell or the system better is the medium where the cell is inside, the substratum now where the cell crawls over it, the proper cell, which has three parts: nucleus, cytoplasm, lamellipodium, and the actin cortex. Okay, in no focal contacts for now. Again, this is our cell profiling in the 3D simulation. Now, remember, in the 2D, we only have a upper view in a XY plane. And here we have a cut in the Z axis of the simulation. The components are here: nucleus, cytoplasm, lamellipodium, substratum, medium, and the actin field just underneath the lamellipodium. Actin field, this will be the responsible for the creation of the polarization axis that makes the cell move away from it when the symmetry of the spatial symmetry of the cell is broken during the simulation. So since we have already in mind that we want to go to 3D, to multiple cells in the simulation, we are going to start now with compartmental cells, as Julio has just explained again to you. I mean, we have the same slide that Pedro showed last Wednesday, where the cells respond different. The energies inside the cell are different from between cells, among cells. So the physics for the motion, for the model is this one. We have the total energy now an extra term, which includes the internal contact energies, the actin field being solved by a diffusion equation solved that comes with Multicell. This I'm going too fast because I already explained that to you last Wednesday. So now our model will be the following. Our initial state will be instead to be only, instead to be 3 squares, one aside the other. Here I will have an initial cube compound by cytoplasm, and beside the cube, the nucleus. Okay, so we will have the 3 components. The lamellipodium is created when the simulation starts. Okay, is created underneath this cube and go outside because of the polarization axis that is formed together with the lamellipodium. So we have now one observation to make is that this simulation, the files that I'm going to present to you, doesn't have the XML file. This is another way to build a simulation. And this choice is maybe in the simulation wizard first screen. When you choose here simulation type, you have Python and XML or Python only. I'm going to the Python only files. That means that I will have 2 files at all, not 3 as usual. Let's see the files then. Let's see here. I uploaded the file already in the website, the Multicell website, in the, let's see here, right here, in the demos. I shared the simulation project as a zip file in the demos for students, demos for Hackathon Day 1. It's there. You can download and play as you want. Okay. So I'm gonna go to the files to explain you. So when you open the CCD3 project, you have only 2 files: the main Python one and the steppable one. Everything that you use to come inside the XML file comes here in a rapid way. See, this part here, we have the Potters block usually present in the XML file, but it is written in a different way. It's a function of the Multicell engine that translates that XML lines in Python lines and put in here. So you have here the Potters part, dimensions of the grid, steps, temperature, everything. We have here the energies, the cell types, the plugins, the energy, the contact energies, and the internal energies for the compartmental cells. Down you have the steppables, the uniform initializer, and the diffusion equation solver here. is basically the only difference between this build a simulation in XML plus Python and only Python is that the final project will not have this XML file. But you follow the wizard in the very same way as you did before, choosing the behavior, choosing the cell types, choosing the plugins, and everything is equal. The final project is different. Doesn't only have two files, the main and the step. Okay. The advantage of this procedure is that here in the Python file, you can define global variables that you can change from one simulation to another in only one file. You don't have to go to the XML, edit the XML, and come here to start the simulation. No, you define the variables here. For example, here you have the cell rate. Cell rate is the size of the radius of that a cell would have in pixels. So this cell rate is used in the simulation to define if I want a cell 10, 20, 15, 5, any size in here. The dimensions of the grid, for example, is here. Ly, Lx, Lz is automatically adjusted to the cell rate. I mean, if I have a big cell, the grid will adjust itself to have this bigger cell inside it. And everything is adjusted in this file. And these numbers are passed to the XML file. Here, for example, in the POTS element, Lx, Ly, Lz. So if you have a number here, this number comes automatically to inside the simulation, passing to this POTS element command like that. Even the energies, for example, the simulation is parameterizing with only one value of energy, J0. Look, here when I defined the contact energy between cells, everything is written in terms of J0, J0 over 3, or 5J0, 2J0. So I only have to change only one number here to adjust everything here in the simulation. Okay, this is why we chose to do without the XML file. The steppable is a little bit longer, but you see, this is the copy of the simulation I just uploaded to the students' material. It's fully commented. Every line of the code has a comment. Then if you go over it, you can read what's going on and find out what each line, each block, each loop is doing. So we have the creation of the cluster of the cell here. We have the calculations of actually not the calculation. We have the graph windows here at the beginning. Another interesting here that you can follow is how to create output data, output files for data from the simulation with names that contains the variables you are using in the simulation. For example, here in this line, I want to write a file name which has in his name the values of the temperature, the size of the cell, the size of the lamellipodium, and whatever you want. So you have this kind of mechanism here. It's a Python stuff that you can transform your numbers in string variables here and build a long string that we can use to define your file name, your output file name. This output file name, let me show you here, have this kind of name, CC3D Demo 2020 project is the name of the project we are using. The data, the data when the simulation run is the last year one, as you can say. The time where the simulation starts and the parameters of this simulation. Cell radius, amount of lamellipodium, chemical lambda, and time interval between storage data. And the data file has this configuration here: time, x, y, z position of the cytoplasm, x, y, z position of the lamellipodium, nucleus, and combined cytonucleus, x, y, and z position. This is center of mass, of course, the position of the center of mass of each one of these quantities. And the second file that comes out from this simulation is the data where you have some symmetry break information. I mean, how much contact between cytoplasm and lamellipodium have, the amount of cytoplasm, amount of front end, and so on. So it's well explained here in the text. Okay, so everything is commented, so you can understand if you follow the simulation, if you follow the file. So now I can show what happens. Varying those parameters, you can easily reproduce some different cell phenotypes in the simulation. See, here we have a cell with this set of parameters that doesn't move at all here, because in this light blue color here, the cell symmetry didn't break at all with those parameters. I mean, the lamellipodium was created and it was surrounding the cell. If the lamellipodium is surrounding the cell, there is no force, there is no polarization axis being created in this situation like that. However, if you change the parameters, you can see, for example, here in the gray area, the symmetry is broken and the cell moves with those trajectories here presented. In particular, see, this is a phenotype where lamellipodium is being formed in more than one part of the cell, and here lamellipodium is formed in just only one part of this, one side of the cell. So here, the cell moves much longer, no? The trajectory is longer than here, because here there is competition between two lamellipodiums, and here there is only one. And in this salmon kind color here is where the parameters start to break the cell. So we don't have anything working very well here. Okay, this is a good simulation because we could validate this simulation with experimental data from 5 different laboratories that we could find published data about cell trajectories and mean square displacement for the cells. And we make a comparison. We published this this paper last year. Okay. Now I can present you the code. The simulation running is, let me see, where is that? Here. I put it to run early this afternoon. And you can see here in this window, the cell moving. You can change the angle. And here you can see the trajectory of the cell. And in this window here, you can see the distance between the center of mass of the lamellipodium and the center of mass of the rest of the cell. I mean, the rest of the cell is the nucleus and the cytoplasm combined. So this is a measurement of the polarization axis, because the bigger the length, the distance between these two centers of mass means that the cell is more polarized. So it moves forward in that direction. And in this window, you can see the trajectory being plotted during the simulation. Okay, so okay, this is the simulation we have in 3D, which is the basic, the base of the paper I have just presented. But now we are going to multiple cells. This is a work in progress. The code is not ready yet, but it's already working in a way. See, I have here many cells moving in a flat substrate. I have here the same graph as I had before for one cell, the cytoplasm front contact, which means the amount of cells, the amount of lamellipodium type cells that are in contact with the cytoplasm for each cell. Here I have the polarization axis for each cell being stored during simulation. And here I have the trajectories for each one of the cells. You can move here a little bit. This is where a graph when I put all the cells starting from the same point, from the same center, and here is the laboratory view, each cell moving in a different way. Okay, and then you can, now we are going to take measurements from this kind of simulation and see if we can, from here, to adjust parameters to try to reproduce, for example, collective motion. I mean, if the cells start to secrete something that is signalized to each other to see, well, we have to move together, then let's bump with each other and move together to somewhere. I mean, it's we can see if you auto-organized motion can show up from this kind of simulation here. This is our goal from now on. And I think that is what I have to show. I try to be short because it's too late already, but I think I could illustrate you the progress of our work with this cell crawling in a collective motion right now. Thank you. Any questions?
Okay. Yes, there are several questions in the chat, I think.
Let me see the chat. I have to go to this meeting. I lost the meeting window. Where is my meeting window? Meeting controls. I have the meeting controls, but I don't have the meeting window. See? Oh, here. I have to stop sharing. Okay, let's see the questions. What happens when the two of the cells collide? Well, with those energies that we have start the simulation, the cells doesn't touch each other. I mean, they can touch, but they don't like to stick to each other. The cell-cell contact energies are such that they almost repel themselves. What features does the 3D simulator use? Well, for example, if you want to make a more realistic simulation, I mean, to reproduce a cell crawling inside a fibronectin mesh, for example, you have to go for 3D. No? The experiments show you a projection. You can compare the projection of the 2D 2D cell scrolling with the projection of the 3D. But I think the 3D can make turn your nucleus more important for the motion. And the nucleus is some rigid structure that makes your simulation more realistic when you go 3D. And another thing is with these 3D simulations, we already know how to compare this simulation, I mean, in silico cells with in vivo cells. We just have to find the natural units of your simulation and compare, for example, time for both. There were very many questions during the workshop asking about how to connect real time with Monte Carlo step. Actually, you cannot directly. You have to find the natural units of your system, and then you say, well, the natural units of the system are those, and are those for in silico and in vivo. Then you can compare both. This is what we have done in that simulation paper I have shown. Okay, no more? Okay, so thank you again. I hope I have been helpful.
Okay, thank you, Gilberto. I mean, maybe it's worth explaining again a little bit more about, well, I guess people could look at the code. I was going to say a little bit more about how the simulation actually is structured in terms of getting the cells to stay the nucleus to stay in the right position, those kind of things.
Oh, okay. This is the structure of the cell. I mean, is almost the same as we did in the 2D. We have to build a cell that's nucleus is always surrounded by cytoplasm, and the lamellipodium surrounds the cytoplasm. So we have to adjust the energies to build to have this structured form. So this is why those energies are within in a only one only one parameter scale, which is the J0 that I showed. And also we have when we choose that value of energies, we take into account also that we need to have the right profile. I mean, the hydrophobic and hydrophilic stuff in the drop of some liquid over substrate. I mean, the contact between the drop and the substrate must obey some kind of angle, or either I don't know, acute or obtuse, so the cell doesn't spread all over the substrate and get some interfacial tension that keeps the cell as an hemisphere over the substrate. We did those calculations to adjust those parameters, to have the cell with that shape. And then you're using the contact energy, cell-cell contact energy. Is that clear, James?
That was very helpful. Thank you. Okay. So in another minute or two, we'll do a final check-in. I think people are tired, but let's at least catch up with people. I hope this was helpful, having the talks, and thank you, Gilberto, for giving us the extra talk. I appreciate it very much.
Thank you for the opportunity.
And I know people, it's recorded, so people will be able to see it. And I know the code will be very useful for people too.
Yes, the code is there already. I hope it helps. I don't know if I put the code in the right place, but you can change it if you.
Okay, so I sent a broadcast message to people, but I think people are so busy working, they don't want to do a check-in, perhaps. So let's give them another minute or two and we'll see. I can leave this Zoom session, turn off the streaming and the recording, and I can leave the Zoom session running. At some point, it will run out. It will stop, but it should be usable for people, and I can start it again tomorrow. Maybe we should just go through the people who are here now and start. Does anybody want to report on successes, problems, issues before we break for the evening?
I'll just say we got a lot of very good help from Julio, and we are making progress and having fun. Thank you.
Okay. Do you want to show something tonight, or?
I don't know if Abhishek or Kato have something, but We'll show something tomorrow for sure.
Oh, you can certainly. Okay. Marco, how's it going?
Great, actually. And so I have something to show if you want, if it's
Great.
okay.
That'll be good. Yes, please.
Okay. So I managed to make my boss work with Compusel, and I'm really happy because it's amazing. And so for now, I implemented oxygen extracellular matrix here. Of course, I will have to adjust the initial cell position. Still, also, I have to add. I will show the code. I have still to link some of the input nodes. For now, I just linked the cell contact nodes, which are those two nodes here, and these nodes for detecting DNA damage. And I linked the node to some cell types. And now, if yeah, exactly. So now the cells are in acquiescent states, and they will stay in acquiescent states until they reach a phenotype, and then until my boss reaches stable states and change, and so that the phenotype of the cells will change. And as you can see, at certain point, yeah, the phenotype is changing, and so the types of the cells is changing. And there are some cluster forming of quiescent cells, and the more the simulation go on, yeah, exactly. So of course it's not perfect. I have to refine some parameters, etc. Also, I have to introduce many other parameters, but I think that it's something. I mean, most important thing is that I managed to link my boss to the simulation, and so that's great for me.
I think that's wonderful. I mean, you may need to help some of the other people who are trying to get these Boolean models running in for other applications.
Yeah, I mean,
now that you've gotten it working, you and TJ are the only people who've done it. So
I'll be glad to help. It's super fun, and I could do this all night long. So please.
Okay, so let me make a note to everybody. Okay. Anybody else would like to present any material? Kato, how's it going? You're working
okay.
with
yeah, I haven't made. I'm working with AJ.
Right, AJ, yes.
We have. I mean, yeah, we've had a lot of help, and I am just trying to implement some of the FPP links and get some kind of more dynamic behavior. Yeah, it's coming along though.
Okay, Lorenzo, how was your day?
Yeah, it was good. I worked a lot along with Jonas and with the help of Pedro, and we work on the tumor model. I'm not sure Jonas is here. Would be the best one to talk about it, but if he's not here, I will tell about it. So we work on two fronts. One was to make one particular tumor cell to proliferate in certain particular way. So to proliferate in certain case and eventually to differentiate in certain other cases with a certain probability. And then to import maps of derived from histological slide of tumor cell with lymphocyte, etc., and to make them appear into the simulation as tumor cells and lymphocyte and tumor cell of one kind rather than the other. And so tomorrow the aim will be to probably integrate the two things and to see if some damage can do something differential according to the different parameters.
So the people working on muscle regeneration, we're interested in how to convert their histology slides into initial conditions. And I worked with them a little bit, but you have better ways of doing it. So that would be good. Do you have anything you wanted to show? Okay, there are a couple of people coming in now. Let me just ask people again. Okay, so anybody who just joined us that would like to talk about their work for today?
Hello, Professor.
Yes, go ahead.
We kind of worked on the model, and the problem that we had, we didn't know if the anatomy model or SPML model that we are working, there is just one model, okay? And that model, it applies for every cell, or it applies just for one cell in a loop.
I'm not sure I understood what you just said.
My question is that there was a self-time step on underscore SPML function.
Yes.
Yeah, when we use that just for once in the step function, so, and we have a loop for different kinds of cells, does it runs for different kinds of cells, or just how does it work?
No, you have to have that outside of you don't put that in a loop. It time steps all subcellular models at the same time. That call once, that single call steps everything.
Okay.
So if you put it inside of a loop, you've time stepped 20 times, 50 times, 100 times.
We put it outside the loop, but
yeah,
we don't really know why.
Well, because it's a solver, so it steps every model forward. That is every subcellular model forward. Now there are ways of telling a thing. There are ways to tell the. I'm trying to think about the best way. I'm tired. We're all tired. I'm trying to think about the best way to say this. That it doesn't make sense to time step separately. What you need to do is to say how long in your subcellular models you say what one Monte Carlo step's worth of time is, and then you time step all the models that much. So the solve that SPML solver will advance all of your subcellular models and any other SPML or antimony models you have forward in time, 1 unit of Monte Carlo step time. So you only call it once. It does all of them at the same time.
Okay, my question is that, for example, I want to give some input to the model, like some TGF beta or whatever.
Yes.
Then I want to extract for every single cell and put it inside a specific dictionary.
Well, it already is in it. I don't understand. The TGF beta you're reading from a chemical field?
Okay, we imagine that we have 10 cells, and
yes.
For every 10 cells, we have different TGF beta that is extracted from a diffusion field. Okay, so I want to assign these values to these values go to the model and process and gives an output for me separately for each cell.
Yes.
So I wanted to make it in a loop that get the values and assign it to a dictionary for the cell, and then process it in the antimony model, SPML model. That's why I was calling inside the loop. Then extract the values from that and assign it to each cell.
So you have to think about, this is a general issue. You have to think about things happening in parallel. Even though execution in compose is serial, in fact, you have to think about things happening in parallel. You have all of the cells read the chemical field concentration. Then all of the cells have their SPML model step forward in time, a certain amount. And then you do something with the outputs of that. It's not allowed to go in within a time step and do that, because that's not what happens biologically. All the cells behave all the cells do the same thing at the same time. And so you have access to those SPML values once per Monte Carlo step. So you can write into those values before you advance the time step. So you can read the chemical field concentration, write it into the SPML models. Then you time step all the SPML models forward. Now you have all the new values internally and you do what you need to do. So Berta, you've done this, right? Before. You've done this kind of thing with antimony models or SPML models.
Excuse me, James, say again, please.
You've used subcellular network models, yes?
No, I don't.
Not so much, okay.
No,
so
no.
I'm trying to think who we can hook you up with that would be able to help you, because this is effectively, I think I'm happy to work with you on this, but I think it is going to take some time. It's not something we can do in a check-in. So tomorrow I'd be happy to sit with you. But if you look at any of the published models we have that use, say, the viral infection models, those will give you very clearly, I think, how to do it. Or the examples that Julio showed of either the cell cycle or the delta notch, because those show you how to do the interactions.
Okay.
I mean, I don't want. I understand if you're frustrated, and I'm sorry, but I don't know. I don't have a simple way without looking at the code and walking you through it. I don't have a simple way. But there's a conceptual problem here, which is that I think you have to think somehow the way you're thinking about the structure of a model isn't the way models work. And it's tricky. I mean, it's not easy because biologically all the cells have their networks running simultaneously. And the issue with CompuCell and any of these kinds of solvers is that you have to alternate the steps of what you do. You do a diffusion step, then you do a movement step, then you do a subcellular network model step. And those steps act on all of the cells at the same time, or all the fields at the same time. And so you have mathematically stale parameters. You're not quite synchronized. And so when people ask, what does the time step represent? What does a Monte Carlo step represent? You have to set your time scale so that things don't change too much during one time step, so that the fact that you're using slightly old parameter values isn't a problem. And that's tricky. It's not a simple thing. So I'm happy to talk about that with you, work with you on that individually tomorrow.
Okay.
Because I understand that it's not easy to make that work. But I'm just trying to think who else is online. Lorenzo knows how to do it. Julio certainly knows how to do it. TJ and John know how to do it.
Yeah, currently the model that I have is a little bit complicated. So when I change the values or whatever, it makes kind of complex. So for tomorrow, I'm thinking to make a very simpler model to just focus on this one to see that how it works.
So something we didn't talk about much in this class, and it would have been probably worthwhile taking a session, is actually how to build models. And one of the principles that one should use is that all of the model components should be able to run separately. So if you have a subcellular model, you should be able to run the subcellular model by itself and make sure that it works. If you have a diffusion model, you should be able to run the diffusion model by itself and make sure it works. If you have cell movement model, you should be able to run that by itself and make sure it works. And you build the models component by component as pieces, and then you connect them. And hackathons, in a sense, are not a good way for doing that because one is in a hurry. And when you're in a hurry, you tend to try to do everything at once. But for research code, it's really important to build models piece by piece, and we have them be able to run independently of each other. Yeah. When I build a computer simulation, I always do it that way. I'll start with, say, just the subcellular model, and I'll say, if these are the inputs, what outputs do I get? Run that by itself. And then I'll say, here are my chemical fields. If this is the secretion rate and the absorption rate, what do I get? And then I won't couple them until I've got the two pieces working independently. And that also will help because then the synchronization will work. And it's not something that's something that's a general issue, sort of what I'd call principles of modeling. It's not something that's trivial to make work. And so I'm happy to talk to you about it. Okay, anybody else want to talk? Janos, how did things go today?
Yeah, thank you. We have some preliminary figures. Maybe Kona can show it. We have cells, and now we're playing with the gradients. So how can we implement them and handle them? And we just got some pretty promising advices from Julio.
Great.
Yeah, about how to handle the different gradients. Maybe here the figure at the right is the most interesting. So dividing cells that consume some nutrient. The bottom layer, they have more nutrient, while up they have less nutrient. And later we try to make the cell division dependent on that nutrient level. So those who don't have enough nutrient shouldn't divide and switch in a passive state when they just sit there. Yeah.
Okay, that's great. Where is the nutrient supply coming from?
It comes from the bottom layer, that green layer.
From the bottom layer, okay.
Yes, and with the oxygen and the other gradients, we're still playing how to handle them in the best way. Yeah.
So you're focusing on doing the diffusion limited growth.
Diffusion limited growth, yes, it will be that diffusion limited growth, and then those cells who don't divide, they will stay, and the cells who divide will be at the edges of the colony. So yes, it will be a diffusion limited growth, and after that, those cells who divide and secrete the extracellular matrix component, those cells, we try to change the contact energies and the mobility of those cells. So if they are actively dividing, have this extracellular matrix, they should behave in a different way than cells without that. So what we see now is the baseline for example, some yeast colony in the lab with a lot of nutrient. But if we get less nutrients, so starving cells at the middle, it would make hopefully a different colony shape. And if the cells can have this extracellular matrix, so they can in the nature, they can protect each other. Here in the model, they can reach higher mobility. It will also change the shape of the colony, hopefully to a more lifelike shape, a more irregular shape, what we saw in the microscopic images. Yeah, so that's what we have now, and we had a lot of good advice also from Giulio and Gilberto.
Great. Great. Okay. Does anybody else have anything you want to report?
Yeah, so we here.
Oh, great. Thank you. Go ahead.
Yeah, can you hear me? Okay, so let me share my screen. Yeah, can you able to see my screen? Yeah, so I was trying to characterize the glassiness in confluent cellular monolayer with the in presence of cell cycle movements, which is cell division and apoptosis. So at the end of today, so what I did is basically I basically build up the model where I have implemented this cell division and apoptosis. So in my model, I have 400 cells, and to keep the cell number constant. So what I did is basically I took the division rate is exactly equal to the apoptosis rate, which is the death rate, such that the number of cells remains the same in the medium. And among these 400 cell, I took 100 cell as a tracer cells, which I will trace, and the data of that cells will help me to characterize the mean square displacement of the cell. So so this is how I calculate the mean square displacement, which is the position at time, the cell center of mass position at time t, and that is it's basically the difference between the average mean square displacement between the cell center of mass position at time t and at time t equal to 0. And so now the rate I define like this. So when a cell in terms of the Monte Carlo time step, and this basically KD denotes basically the rate of division, and Ka basically the rate of apoptosis, which is the cell death. So these numbers basically denotes after which time step I basically implement the this cell division and apoptosis. So as you can see, at a low rate, cells this mean square displacement is look almost like straight line, and this is how the okay. So something happens. Yeah, so this is how this cell. So this is at a low rate, which is let's say low rates in the sense that these events are rare. That is at after each and after 50 time step I implement that, and when I increase the rate, that is I basically at every five times step if I implement this this cell death and apoptosis, so there will be more okay. So there will be more cell division and apoptosis happening, and these deep blue cells are basically okay. So this is some problem.
Maybe not play it from the video, from the slide, just show the.
Yeah, so this is basically these deep blue cells, deep green cells are basically the divided cell, and the red cells. So red cells is not so not much red cells are showing here because of the animation, I think.
So because of the animation, because I am saving at each 1,000 step the animation video. So this is how this shows basically that there are lots of cells which are dividing, and this is at a high rate. And if you increase this thing, so you will see a plateau type behavior, and which is basically the characterization of the classiness in this type of system. So tomorrow what I want to study is basically so also I have studied this self overlap function, which is defined as this q of t, and this is basically the window function. So I have choose a particular value of a, and when this quantity is less than greater than equal to 0, it's basically gives 1, and when it is less than 0, it gives 0. So so for two set of rate, I basically calculate this self overlap function, and so these two quantity are basically used to define this used to characterize the glass transition, glassy dynamics in this type of cellular system. And so tomorrow what I like to study is basically this thing, this in context of the polarity of the cells. So I slightly build up the model today, so I'll give the runs tomorrow, and yeah, so I'll let you know tomorrow about the stuff.
I guess my only question is, do you want the cells to be so under so much pressure that they align their borders the way you have very square cells?
Yeah, because I am at a so low value of p naught, means this p naught in the sense like the surface area in 2D if you say it's perimeter, so I'm at a low region of the perimeter.
Okay, so you want it to be you want them to be stiff. I mean, that's fine. It's just a question of whether you want them to be, I mean, your cells are very square, which means that their motility will be very low.
Yeah. So in the context of in terms of the experiment, so this the low p-naught regime is more relevant, and so we have studied one with the cellular POTS model, and there we basically characterize the glassiness in the low p-naught regime. So that paper published in PRE. So yeah, I'll share the reference in chat box.
Great. Okay. Good. Well, I'm glad that that's working. I'm really pleased.
Yes.
All right. Okay. Is there anybody else who would like to present something today? We're at 6 o'clock. Everybody's tired. Anybody else would like to present? No. Well, in that case, thank you everybody for working. If people's teams would like to continue to work, does anybody? I could leave this Zoom running. I don't know how long it will go for. It may time out at some point. But I will. Okay, sorry.